I didn't say anything too important, so you didn't miss anything. Basically was just saying how awesome this workshop is going to be, which it will be. So yeah, we have an awesome set of speakers, both from academia and industry, two places where a lot of cool research happens, which I think is the nice thing about AV research. It's a very direct path to application and to the real world. Just to give you a rough overview of what's going to happen today, so you can see the agenda. Mostly we have a lot of keynote talks. We have lightning talks of paper presentations, and we have poster sessions during the coffee breaks. There's a small hiccup, namely that the actual posters will be in the other building, and we have only 45 minutes scheduled for the poster sessions. It is how it is. Please try to rush over there and spend a few minutes. Maybe you can also, already start talking on the way. Also, to get you prepared, we have all the posters and all the papers on our website, so you can also check them out there. And also importantly to note, we have more posters than just the lightning talk. So we have some orals, but we have additional posters as well that are on the poster sessions and the website. And yeah, that's gonna be from my side. With that, I would like to introduce our first speaker. Felix Heide is a professor at computer science at Princeton, where he leads the Princeton Computational Imaging Lab, and he's also the head of AI at Torch Robotics. And I'm very happy to welcome him to the stage. And thank you very much for agreeing to talk.
Yeah, is this coming through? Is this coming through also online?
Yes. It is, yeah.
Okay, perfect. So thank you so much for the kind introduction. I am super excited to tell you a little bit more about how we devise generative AI for simulation. So a little bit of a history lesson. So I came to Torque about a year ago with the merger of Algolux. And Algolux was a startup that I kicked off during my PhD with the focus on end-to-end imaging and perception. And Torque, we're thinking this story a little bit further, and we're building autonomous trucks with Daimler Trucks under the Freightliner brand in the US here. And Torque hasn't really been too popular with technology in the past, and I want to take some time at the beginning of my session to change that here and give an overview of the problem and our technology stack that we're building. So before I go into the meat of our learned simulation, let me start by going over the modern AV stack that we're building. So we're building a stack that I'm showing you here at the top. For sure. That is separated into a perception and prediction and a planning module. And learning is used in all stages of Torque. This is a modular stack with the parameters of all models and of all modules in that entire stack being learnable, independently of them being neural networks or conventional algorithms. And we do quite some work to mix that stack and make it as efficient as possible, because in the end, we want to build a product that fits onto an embedded stack and actually allows us to scale in the end. We make this possible by making that entire stack differentiable. So specifically, throughout the stack, we build differentiable modules or introduce differentiable proxies. So that concept of differentiable proxies is found throughout our entire stack because of the specific algorithm choices that we make, which in the end brings us to that overall differentiable stack. So let's look and make this a little bit more concrete on specific module, which is the BEV stack here, which performs perception in the bird's eye view. So we rely here on a multimodal BEV stack that directly operates on raw data. Just giving this as one example of an interesting modular stack where you can learn something, we can learn parameters in the stack that you otherwise wouldn't typically learn. So we use raw data here in a different way than you might be used from, for example, the Tesla stack has been very publicly disseminated, and directly include the ISP here and the camera parameters in our BEV model. Also online calibration, pose, and feature detection. So this is really one branch here that goes through a model that is truly end-to-end, all the way down to the photons. So here's an example of a proxy pipeline that I alluded to early on, with a differentiable proxy for the image processing pipeline. So using proxies both for the image processing pipeline as well for post-processing blocks, we're then able to optimize directly for downstream metrics. In this case, we stop at the precision and recall metrics that we can directly optimize. With the optimization time lap, you see these going up. And what's interesting here, as a motivating example, is that you find images then here output by the ISP that are not really pleasing for human viewers, but are favored by a downstream detector. So something that you can really only learn with end-to-end. That's why we embrace this. We extend this then really broadly to our entire BEV stack, where we rely on wide baseline stereo depth to place our features in the bird's eye view at ultra long distances, up to 1,000 meters with high resolution, almost double-digit megapixel cameras, which is critical for long-term planning. So driving on highways for autonomous trucks, very different in many aspects than driving for robots. So to make this work, object detection is really not the only struggle that we have to solve. So to really get accurate depth and be able to use such a stereo camera rig that I'm showing you here at the bottom, we have to solve more problems. And that is because of the unique challenges that we have in trucking. So there's a cab that is not super stable. We have vibrations on potentially rough roads. So it can be challenging to really get a stack that has a very smooth pose that we can simply use traditional methods for to optimize. So to tackle this vibration, we actually have to integrate an online calibration into our method that runs at the same time with our stereo depth estimation and cross-image feature correlation volume. And this works out to be extremely well, and even with off-the-shelf depth networks for stereo matching that I'm showing you here, we can get substantially more of this. And then in our production vehicles, obviously we won't have these vertical bars, but it shows you that the problem is something that's relatively unique and we have to solve. And this then also allows us to solve some of the unique challenges, such as lost cargo, which I'm showing you here, where there are small objects placed on the road and our vehicle has to react to them at ultra long distances. So a small rock or a tire at 200 meters is something that we can solve then all of a sudden with these double-digit megapixel stereo pairs, allowing us to give enough pixel density at these long distances. So 8 to 10 million points, which you won't get from any LiDAR, to be able to detect this. And there's also an interesting paper later this week, a cool highlight paper on lost cargo at nighttime. The previous stereo approach is also a paper at the CVPR, and hope you can check it out. So in the prediction and planning stack, to move on, we also rely on a fully learned prediction and planner. This is essential for us to allow plans that are robust to high ambiguity that multiple futures can offer. And planning takes this into account. So our planner runs alongside a conventional analytic planner that formulates safety constraints in an EBM style fashion. And then at relatively high throughput, because it's a learned planner, so homogeneous computation, we get an understanding of these multiple futures and can select the best plan within those constraints. So that works really well as an effective learned planning mechanism without a safety net. So let's look at predictions in detail. So we predict the modes of multiple future trajectories of multiple agents. And here's an intersection scenario that I'm showing you here, where light blue was the past, which was seen, and pink is or purple is the predicted. We predict the ground truth. We predict here also a potential danger, which is one of the modes that we're outputting by our model, and a few other modes here. This is an example that is a transformer-based prediction module that works on a set approach, which is something that we have published 2 years ago. So we take this one step further and then include learned scene context, both in the prediction as well as in the planning stage, and notable future predictions used in all planning stages, both in short term as well as in long term. So it gives you a rough rundown of the modern stack that we're building. And so using these multiple learned planners can rely on agents that are aware of each other throughout differentiable prediction and planning. And as I hopefully motivated at the beginning of the talk, does not only benefit these stages, but really benefits the entire stack, tracking persistency, occlusions, potential fusion of blocks, such as tracking and prediction. These are all blocks that are. So the after simulation thing, the key thing is that for this entirety of the stack, which is differentiable, and to train it and validate it end to end, we need data. We need it at scale. So for the remainder of the talk, I'll describe our world simulator that allows us to generate this data at scale. So to generate data already at the sensor level for training and validation, we use a joint approach of high quality generated data using neural rendering and generative methods. So generating large scale and high quality novel trajectories for AVs has become possible with really an exploding amount of work on neural rendering in the last 2 to 3 years. So not only can we generate photorealistic views, but also these methods are starting to give us additional labels that you were only in the past able to get by traditional rendering techniques, such as geometry, lighting, material estimates are starting to become possible. So we can start to use them as a drop-in for traditional rendering techniques. And at Torque, we bring this to ultra large scale, so entire routes, which requires a lot of engineering. And there's a lot of really cool works at the SIGGRAPH that also touch on some of the technical problems that we're tackling. Because scene reconstruction is not enough. What we want to do with this, and what we're doing at Torque, is to build novel scenes and novel scene trajectories, right? So this can be supported then with these neural scene reconstructions, hinging on our work from 2 years ago out of my lab on neural scene graphs. We're able to generate entirely novel scenes, novel trajectories for these scenes that we have driven through before. And then the scene was only observed once. These are a bunch of new observations here that we have never seen before. So we mix this, that's one of the key things, with layout conditional, fully diffused generated models. So of relatively complex highway scenes or city scenes that we haven't seen that are not in our data set. I'm showing you our own layout conditional approach that can generate really diverse scenes for our training and validation. And the key thing is for this to work in our training and generation approach is to mix 3D consistency from neural rendering approaches and diffusion models. So supervising them in an almost cyclogon-like approach is essential to make all of this work. And really not only excited for generative methods as a way to generate training data and validation, we think that this can actually go one step further. So what do I mean by that? So here's some exciting opportunities that I think are there for explainable vision using these generative methods for inverse rendering. So I'm showing you here a few examples of inverse rendered scenes for object tracking, where we synthesize the image that best matches a given observation. So we blend here between the input video and the inverse rendered scene. So the cool thing is that this allows you to solve tracking as an optimization problem, which we find tremendously powerful for generalization. In fact, all of the data that I'm showing you here has been unseen. So none of the trackers that I'm showing you here were trained on it, have seen that data. So just to go into a little bit more detail, we formulate re-identification or matching in tracking as an inverse rendering. So let's start with these two consecutive frames in BEV. And for a given time step, we assume that we have image-based 3D detections. So given this set of detections, we can then try to generate pixel regions that best match the observed pixels in the image. And to do this effectively, we use a generator that was trained on large-scale synthetic data, specifically Get3D is what we use here. And this allows us to do test time optimization over texture and shape latents by backpropagating pixel losses all the way at the end from the generated regions that we output. And jointly with this, we can also optimize the pose and the scale of the respective objects. So let's look at that process in a little bit more detail for the example image. So let's say we have this particular input frame here. Then we gamma correct this for a little bit better viewing. And here's a bad initial guess overlaid that comes right from a detector. We initialize this here with per class average latents. So then if you optimize over the texture latents using perception loss, just again, only looking at backpropagating all the way from the image loss, perception loss to the latents, this already works because the partial overlap as the generator was trained on uniform texture. So next, let's optimize pose in addition. As we can see, our method is able to recover from relatively bad pose as initializations.
I think you can continue because Zoom, like okay. In the back, it's maybe a bit quiet. But
does this work?
No. We also had this yesterday in some workshops, and it just randomly came back. Maybe
this
is this working? No. Okay.
Okay, I'll try to speak louder. Sounds good. So hopefully I'm not screaming at the Zoom audience too much. So yeah, so let us optimize pose in addition, and as we can see here that the method is able to recover from relatively bad pose initializations. And finally, if we add shape, this completes our joint optimization method, which is purely generative, and we run backpropagation steps until this thing converges. And this was for an extreme example with a bad input, and over time, as we average the latents and we get really decent predicted poses, we can reconverge into a few steps. And we found this extremely robust to generalize well. The key thing here is that we can show results on completely unseen data. So here the method performs on par in terms of quality with recent transformer-based trackers that were trained on this data, but as it is generative, it is also interpretable, and we can actually output what the method sees, what the method has synthesized in order to perform that tracking task. And so I hope that this generative method can allow us to be an effective prior for generalizable vision pipelines, both. So for the rest of the talk, I want to show you how we generate behaviors in our world simulator. So to evaluate behaviors in an AV stack, typical simulation methods in the industry involve replaying driving logs and to generate more diverse scenarios. But agents replayed from offline data do not react to the AVs. They only see the data that they have recorded, and their behaviors cannot easily be intuitively controlled to simulate scenarios, which is what we talked about as well. So our approach to tackle this problem at scale is offline RL. And there's an approach that we call control sim. So specifically, we focus on the problem of controlling agents, altering captured drives into a wide range of agent behaviors, including both good and bad driving behaviors. So extremely good and extremely bad driving behaviors. To motivate this a little bit, let's look at this example that I show me here on the right side of the slide. I'm showing you here an example for a lane change, where ego is pink and the other agent that we want to control is blue. Note that there's more agents here in yellow that all react to each other, but we do not control. So here on the left side, I'm showing you the nominal behavior, which was what we captured, which was a lane change for the pink AV planner. So this was all fine, and the blue vehicle followed the traffic flow around, right? Now, here's an adversarial behavior that we generated, where the vehicle sped up and caused a crash scenario, so it did not follow the traffic flow anymore. So this is an interesting scenario that we want our planner to see that we have actually never captured in our driving logs. So as I mentioned before, the key thing that we found works well to generate these scenarios is to hinge on offline RL. And specifically use exponential tilting to enable controllable simulation. So at the sampling time, we simply need to move a bunch of knobs, tilting values for each axis of control that I'm illustrating here on the right. So let's say on the right, we have this illustrated scenario where we have two vehicles passing each other. Then we can change a few knobs to perform tilting. The first knob is tilting vehicles to vehicles. So that controls effectively the distance of vehicles to each other. So we can tilt the vehicles to bring them closer to each other in their plans. Tilting vehicles to the edge of the control map is another tilting input that we can perform. So we can drive them off the road edge, or we can change the goal finding behavior and can tilt them off their goal. So with these knobs adjusted, we find that tilting provides a really simple and interpretable mechanism for control at scale. So to make all of this work, the first step in control sim is a data set of multi-agent driving scenarios with state actions and factorized rewards. So to enforce physics-based behaviors and the constraint, we pass the driving data set through a vehicle physics engine. We show you an example of logged scenarios from Waymo that are replayed through the nocturne environment, which is a physics-enhanced environment. So given this physics-enhanced data set, we now want to learn per agent policies in this multi-agent world. So we do this by modeling a factorization over the joint distribution of multi-agent future states, actions, and factorized returns. And so this joint distribution is conditioned on the current state and the goal of each agent in the scene. So we choose this specific factorization that I'm showing you here in future state prediction, return policy, and return prediction, so that it would allow for test time controllability of the policy. At test time, we use then exponential tilting, what I intuitively illustrated on the previous slide, for the sampling of individual return components towards whatever desirable values we want to get, low or high values for a respective component. And so this makes then the return condition policy to be conditioned on the tilted value to generate a controllable behavior. So our model to achieve this encodes the initial scene using a transformer encoder, performs cross attention between the individual elements on the map and the individual agents. We use a polyline map here. During training, the decoding starts by embedding each agent's states, actions, and returns at every time step. And this is kind of similar to the embedding that natural language models use. So next then, for every agent, at every time step, we auto-regressively decode the agent's return components, followed by the next action it should take. And to really make this work, we need a temporal masking strategy where we ensure that an agent only really attends to the past stage of all other agents, as well as its own states when generating the most likely returns and the most likely actions. So as an additional learning signal, we do future state rollout, which we also found essential to make all of this work. So then at inference, we follow this autoregressive decoding scheme with the states of all agents given here. So given the states, we predict the return to go, and the return to go predicts the actions, and the actions predict the next states. And then we leverage tilting in order to control the individual agent's behavior. So here, the policy distribution over agents can be tilted at inference time then towards desirable or undesirable behavior by changing different values of the return. So this can be intuitively understood as pushing the return distribution towards high or low values, depending on the sign of kappa C in this exponential tilting equation. And for kappa C of 0, we actually recover the base distribution, so we can perform imitation learning. So qualitatively, we can see that tilting can yield some really interesting scenarios. So let's look at the top here in the center. I'm showing you here the nominal behavior. Nominal didn't play, but the negative tilting example causes here a crash. The positive tilted example causes an overly conservative behavior of the blue agent, which yields very, very early. So in the bottom, I'm showing you here vehicle to edge tilting. I'm not sure where these are not playing. Yeah, some issues here with the videos. But what you would see here is that we have a nominal scenario where the vehicle stays on the road. For a vehicle edge tilting scenario, the vehicle drives off the road. And for the positive, it drives out the road. And for the positive tilting, it stays very much inside. The cool thing is that one of the advantages of control thing is that exponential tilting can relatively smoothly control the agent's behavior. So we have 3 axes of desired controllable behavior: vehicle-to-vehicle collisions, vehicle-to-road edge collisions, and goal achievement. And as you can see, as we smoothly increase the tilting values on the x-axis, here the metric of interest shown here as collision rate, off-road rate, and goal success rate smoothly changes. So we can generate a bunch of adversarial behaviors too. And again, these videos are not playing. Let me actually restart it really quickly. Okay, so here you see, yeah,
You also need to share it again on Zoom.
Oh, that may crash it. Okay, so here was the no tilting scenario. Here we have the negative tilting from before, where we created crash scenario. And here we have the positive tilting scenario, where we perform a yield, shown here on the top right. Now, if you look at the bottom, what I mentioned before was the vehicle to edge tilting, where this was here a nominal scenario, so a driving situation in a very narrow confined space. Vehicle to edge tilting leads to the vehicle to drive off. So it actually collides with the vehicle edge here. And positive tilting leads to a very conservative behavior, where the vehicle stays very well inside of the road drivable area, much more than before. And again, this all was generated as tilted behaviors that have not seen before. Okay, so let us show this adversarial scenario. Nominal here on the left side, where this is an unprotected left turn, where the blue vehicle yielded and waited until it could perform the turn. And then we were able to generate an adversarial scenario where the vehicle drove more aggressively and caused a crash scenario. Again, completely unseen scenario. A really interesting case shown here on the right side is a lane change, where the nominal behavior was actually that both vehicles stay in their respective lane here, as also indicated by the goals, which are in their respective lanes. Now, we were able to generate an adversarial scenario where the blue vehicle actually performed the lane change through vehicle-to-vehicle tilting and rear-ended the other vehicle. This has never been seen before and was a scenario that we have generated purely by this tilting. So with this approach, we can fully simulate the agents of the scenes, or all agents of a scene, or choose only to simulate a few agents. We can see in this video that this can comfortably scale to scenes with an exploding number of agents. The method is much faster than other comparative methods, where each of these agents have their own respective goal. So the agents are aware of each other and are able to interact with each other, shown here the bottom left, bottom middle left, for example. And we can automatically generate an almost infinite amount of long tail scenarios with this approach. So that's close to my time. So summary, I've hopefully excited you about generative AI for perception and planning, given you an overview about what we do at Torque Robotics. And to allow us to scale scenarios for the long tail, just in perception, not only simulation is needed, but also the entire stack, all the way from photons to behaviors is essential. I'm showing you just a brief overview of some of the other projects in my lab at Princeton that also explore this cross-disciplinary directions here for hybrid radar or LiDAR sensors, neural rendering, and computation in the optics. So there's a bunch more projects on my website, and we're presenting 9 papers at CVPR. If you have questions about torque, please reach me after the talk. I'd like to thank you all.
So we do have some time for questions if there are some.
Yep.
In the generated scenes, you don't seem to care much about, I think, if the ego is at fault or not. So any comments on that? So, for example, the actor is just running into the ego, which may or may not be actionable from ego perspective. So I'm curious to hear your comments on how to generate scenes where the ego is at fault.
Where the ego is at fault. Well, we can also control that, right? So that affects we can effectively learn, and this is also in our paper, a very aggressive planner that is super aggressive on performing actions that are really goal driven. So that's also possible. It will generate more crashes, right? On average, if it reacts very aggressively.
Yeah, I guess what I'm trying to say is that your planner is what your planner is. You're not changing it that much, but then you're kind of creating these things where you're kind of finding the gaps.
No, we're actually training it with this. We're training the planner with the scenarios that we generate, right? So we can use control sim also as a planner. We can use it as an aggressive planner or a conservative planner, depending on what we're doing, right? So you can use that at inference time, the predictions of the behaviors as a planner itself. So, which means that you can generate a super aggressive one or a very conservative one, or you can affect the plans on the behaviors of the other vehicles that your vehicle is reacting to. Yeah.
So, other than the behavior of the other vehicle, sometimes the environments will cause of issues. For example, probably is the shade of the bush in San Francisco, something like that.
Yeah.
So my question is, you actually is to deal with behavior of other vehicle around you. What's your thought on how can you generate other factors? For example, the shade on the ground, or the weather condition, how to deal with that in the generative.
Yeah, this is a really great question. Right? So what I showed you early on was our sensor simulation stack, right? Which essentially stops at the behavior side, right? And this one here starts at the output of the perception, right? So we have the agents, right? It goes on from there. And obviously those have to come together, right? So that is the ultimate stack that we're building. Those ones have to be fused together so that we really are able to do end-to-end simulation and an end-to-end stack. These are currently still separated, but those stacks exactly need to come together. Yeah.
So do you have any plan or any idea to generate those?
Yeah, absolutely. So this can go hand in hand. Right? So this is in fact one of the current directions that we're working on. That we're bringing this generative sensor simulation from the beginning all the way into the behaviors as well, right? You can generate the respective sensor readings that you would have gotten to get the particular input behaviors, which is a really important task, right? Because then at that point we can train and learn, for example, on noisy outputs, right? So right now we assume sort of pseudo ground truth behaviors here for this part of the simulation stack. Right now it's still separated, but as soon as you generate noisy ones, this becomes very interesting, and then you can update your perception stack or other modules in the entirety of the stack as well.
I think we have time for one or two more.
If there are questions from the very back, either you can come up front or maybe you can repeat that online.
Okay. So maybe one question over there.
So when you control the tilting mechanism, do you have a way to evaluate how realistic it is? Or like when you control the return, do you constrain the range that use that reward to achieve adversarial behavior?
Yeah, so we measure various different metrics, right? So again, depends on what you're doing, right? So if you measure collision rate, for example, for these adversarial behaviors, that's something that we measured, which goes up expectedly, right? But the cool thing is that if you actually learn a planner on this doesn't forget to be a good driver effectively, right? So if you give it a lot of condition, we fine-tuning it on collision data, it learns to produce more collisions, be much more aggressive. But if you tilt it back towards more conservative behavior, it can still do that.
Okay, so I mean, like, do you have a way to like ensure that the adversarial behavior
is adversarial? Yeah. So absolutely. So for example, measurements like collision rate, for example, right?
like collision rate with respect to other agents?
Exactly. Yeah.
Okay.
Yeah. At some point, whether a scenario that you generate is like you can think about sort of the analogy of an FID score or something else, right? But at some point, it becomes also subjective whether a scenario is a realistic one. You would have because you haven't seen it, right? So there we can only measure these planar metrics, or we can actually test it as well and see and compare it to manually curate scenarios, right? What the traditional approach would be to curate a lot of scenarios, which is also something that we have done. And there's a comparison there as well with a small sample set possible, but the indicative metrics of collision rate and other metrics of the planner are more indicative, I think, of this.
Thank you. I think we have to move on. Thank you very much again for the talk. That's right around that.
Okay, testing.
Yeah, that works.
Well, okay. Okay, now test is good.
Yep.
All right.
Oh, yes, that works.
It works.
Yep, I can see it in Zoom.
All right. Great. Great. Thanks. Sorry for the technical difficulties. Good morning. Thanks for the introduction and to the organizers for organizing this workshop. It's really cool to see a specific session dedicated to data-driven simulation for self-driving. Today, I'll be talking about generative AI for developing and deploying self-driving systems safely. So it's already been talked about in the past, but the reason why we're all here today is that deploying self-driving vehicles safely in the real world is extremely challenging. It's especially challenging if you try to do most of your testing and development strictly in the real world. And the reason why is we can see here on the images on our screen, there's a lot of rare and unusual situations that can happen in the real world. This only captures most of the things you might see from a perception standpoint, but if you think to your everyday lives when you're driving, there can be some very unusual actor behaviors and crazy drivers out there you need to handle safely. Even last week, I think I was driving to the airport and some random metal obstacle fell from a truck and then came and hit the car, and we had to pull over to the shoulder and check the damage. So there are a lot of rare things that can happen, and it's not safe nor scalable to take a real self-driving vehicle, put a particular autonomy release on it, and then just drive for millions of miles to hope to see some of these situations, only to find out whether or not you can actually do safe maneuvers around them. So the main question we have to ask ourselves is, how can we expose the self-driving system in a safe way to all these situations so that we can make sure we can handle them during learning and that we can prove it through testing? And we're at this workshop today because we believe that data-driven simulation can be a tool to help enable safer and more scalable development. So I know many of folks might here already be very familiar with the types of simulation used in industry, but it's good to do a quick recap just to see how the current ways that we use simulation doesn't really help address this question. So first, I think Felix already mentioned this, there's log replay simulation, which is where you have a self-driving vehicle equipped with a set of sensors. It drives around in the world and you capture a bunch of data, and then you kind of play it back to your time system. It's sort of like watching a movie. This is also known as open loop evaluation. And actually, it's also been shown, I guess, like at this CVPR, and I think there's a paper called like Ego State is All You Need, or at this workshop as well, that shows that open loop evaluation is not very indicative of the full system level performance of your autonomy system in the real world. And additionally, with log replay, you can only really see the scenarios that you've collected and you can't really change it. Then you have motion planning only simulation. This is also a very standard technique in the industry. This is closed loop evaluation. So you can actually control all the agents in the scene from a behavior standpoint, and you generate ground truth perception and prediction outputs such as bounding boxes and trajectories. This, of course, assumes that your autonomy system is modular so that you can only run the motion planning module. But the other downside of this approach is that you actually capture the multimodal nature of the scenes you might encounter and the errors you might have in your detection and prediction perception stack. So that's another downside of the motion planning only mode. And then, of course, there's data generation, which is not as common, but used still, where you have procedural content that you can generate through synthetic, like physics-based rendering systems to generate data to augment your existing perception training data sets. This can be used to say, like, augment, say, fire trucks to increase your detection on emergency vehicles. But the downside is that through these synthetic environments, there's often a drop in realism, and you can't really use them to test the full system as well. So existing tools may not be that effective for answering our question of being able to test our system in closed loop for evaluation of these safety critical scenarios. So we need to ask ourselves then, what are the aspects we do want in a self-driving simulation system? So first, we already want it to be diverse to capture all these scenarios. We want it to be fast because there might be millions of different situations we need to test ourselves in. We want it to be controllable so we can say where all the actors are in the situation, how they're going to interact with the SDV. We want it to be realistic, and this is not just image reconstruction error, but also how realistic are your agents, and can you actually do counterfactual scenarios in simulation and be confident that it's indicative of performance in the real world. We want it to be immersive. This means kind of like spatial temporal consistency. You test the full autonomy system, including the perception system. Reactive, basis the closed loop nature of your simulator. Basically, you respond to the other actors respond to the SDV. And then you want to be able to provide feedback. This is like metrics, say comfort, safety, collision, being able to really understand how you affect the other agents around you. And of course, we want this to be scalable. So having low cost helps us make this happen. So I've already talked about the other tools that we've used in simulation in the past, such as log replay. Doesn't provide you closed loop simulation. motion planning only mode, you can't test with the perception system, and synthetic data generation, which is also preventing full system evaluation. And recently, there's been a lot of exciting progress and developments in generative AI. This is through, like, say, diffusion models and transformers. These type of techniques have been applied to develop world models. World models are typically trained on large corpuses of video data and text, and they try to implicitly encode the dynamics of the real world in their simulation along with appearance. And recent results have shown really exciting and cool videos of appearance and dynamics for self-driving scenes, but there's still some limitations that they have that prevent them from being used for high fidelity closed-loop simulation. And I kind of walk through this a bit for more detail. So right now, they're not that fast. For example, stable video diffusion takes a couple of minutes to generate several seconds of video. There's partial controllability at a course level. You can provide text queries to kind of interact with this generative world model, but you can't really control exactly how the actors are maneuvering in the scene and what's the exact performance of your self-driving vehicle in the system. They're somewhat immersive, but there's still difficulties in spatial temporal consistency. This kind of blends into the fact that it's hard to get truly reactive behavior. There's action conditioning available, but it's not really clear yet for world models. Like, for example, if you have a very heavy, dense traffic scene and you accelerate abruptly into that scene, the world models might kind of like make those actors disappear or hallucinate something to present something more realistic or more common in this data distribution. So you can't get true system performance and actually also like metrics and clear feedback about how your autonomous system is doing. And they can still kind of be expensive to train. So the main goal at Waabi World is that we're trying to develop a simulation system that hopefully can have the physics explicitly modeled and exact 3D representations to build a high fidelity closed-loop simulation system. So we can still borrow and leverage a lot of the generative AI modeling techniques to generate realistic assets and behaviors, but we can also use computer graphics and animation to get speed and controllability. We can use machine learning to generate intelligent and reactive actors and learning-based feedback. So having kind of like this modular approach can hopefully achieve the high fidelity closed-loop testing that we're aiming for. You can kind of think of this as like a video game for Waabi driver or any autonomy system, but it's data-driven in all aspects so that you can get the realism and performance you want. So with such a simulator, at Waabi, we try to do most of our development in simulation. So we try to do many scenarios and evaluate our autonomous system in simulation and do the moderate amount of testing on a closed-loop course test track or in the real world. And the bulk of your real-world development is actually to collect data to build assets and to create realistic agent behaviors in simulation. So here's the Waabi World engine. I'll briefly go over the different modules that are involved in a simulation system. So first, there's your simulation specification. You can specify this in a variety of ways, but this kind of specifies where the actors are in the scene initially, what they plan to do to create your scenario, and also it specifies the vehicle platform, what type of sensors you want to simulate, where they are in the vehicle. This generates a world state that specifies what's happening in the scene. We can then use that to load in different assets of our world for the different actors, the background, and simulate the sensor data according to the sensor configuration. We generate then the LiDAR, camera, radar, etc. outputs and feed that to the Waabi driver or any autonomy system. And then the Waabi driver will run and generate particular actuation outputs, such as say steering and acceleration. We have a vehicle dynamics model that then determines what's the next state of the self-driving vehicle. And this is going to be kind of challenging, especially if you're using, say, autonomous vehicle trucks, because you have a tractor and trailer, there's mass distribution you need to take into account that makes it a bit more challenging just than standard cars. There's also the agent dynamics model. This controls the actual agents' behaviors, reacts to the SDV and each other. And then this finally updates the world state. Another key module that's not often talked about that much in the computer vision community is latency simulation. So there was recently, I think, a paper at ECCV in 2020 called Streaming Perception that kind of brought it more into the forefront. But latency simulation is all about the reaction time of the autonomy system and how long it takes to process the sensor data before it generates an actual autonomy output. That type of delay is important to model, especially on the actual truck compute or vehicle compute that you run your autonomy system on. And you typically want to run your simulation in more low-cost consumer or cloud compute. And so you have to model that latency through some models. Cool. So that's the closed-loop simulation system. And of course, the last component is an evaluator to provide feedback based on the world state to your autonomy system. And just a quick recap is that this is like more a streamlined format of the same Waabi world closed loop simulation diagram. But just wanted to quickly say that we can do full closed loop evaluation, but we can also do many of the different approaches to simulation that were talked about earlier. So you can still do closed loop, but you can also feed in a real world log and directly replay that sensor data to your autonomy system, similar to open loop evaluation. You can still do motion planner only closed loop simulation, where instead of having a sensor simulation module, you generate the perception and prediction outputs to your motion planning system and still have behavior models control the actors. And of course, you can still generate perception training data for offline training. And with this type of modular kind of game engine style approach to simulation, we can choose a variety of ways to specify our scenarios. So you can initialize the scenarios from a log. You can choose heuristic-based actor models or reactive intelligent actor models that are trained with machine learning. You can also have human-specified scenarios if you want a very specific test you want to evaluate for. And this type of a variety and diversity of scenarios and actor behaviors also allows you to not overfit to any particular behavior model that affects the data distribution from your simulator. So you can kind of get more insights into the different types of ways your time system can have difficulties. And this enables different types of applications for scenarios and simulations, such as adversarial scenarios or coverage testing to make sure you can handle all the different situations you might see. Cool. So there's different parts of the Waabi world. I'll probably primarily talk today about the side of sensor simulation. So this is digital cloning, LiDAR simulation, camera simulation, this particular talk. So I talked earlier about how Waabi world can kind of be thought as a video game, but for self-driving. And the key aspect of it that is added to every single module in Waabi world is that we want to be data-driven. So this enables us to achieve like realism and diversity and scale compared to standard procedural content and artist-created approaches. Because we can now take any real-world data that we see in our self-driving vehicle and convert them into virtual worlds. We call this digital twin reconstruction. And this enables the speed, controllability, and realism we hope to achieve. So there are 4 aspects of digital twins and sensor simulation I'll be talking about in the second half of this talk. Diversity, speed, controllability, and realism. And I'll talk about recent efforts in our team to achieve these types of attributes in our sensor simulation system. So first, I'll talk about diversity. So I'll first talk about how we actually go about creating digital twins. So there's been a lot of progress recently, as everyone really knows well, is in the neural rendering community and scene reconstruction. So you can do very high quality novel use synthesis. And last year at CVPR, we presented a paper called Unisim. So with Unisim, you basically decompose the scene into neural volumetric feature grids of static background, foreground actors, and a sky region. And then you can model the scene in this decomposed manner in a controllable way. And then you can reconstruct the original sensor data that you train on. And with some additional networks, you can achieve a bit more generalization, robustness to achieve better extrapolation and novel views for closed loop simulation. So this is kind of the overall approach to creating digital twins. And I'll kind of show some results now from that work. So here we can take these type of digital twins that we reconstructed by training on the original sensor data, and we can modify the actors' locations. We can remove actors. We can place additional actors. So we can now create new scenarios and then just the original log. We can also simulate new locations. So here we show an SDV performing a lane change, or we can also change the sensor configuration by increasing the sensor's height. So this allows for kind of the interactive behaviors you might want to see in a closed loop simulation system. So here's some results at scale. Basically, any type of log we observe in the real world, we can run scene reconstruction on it and decompose the scene for controllability of the actors and the SDV. And here's some closed loop simulation results. So the top is the original scenario, and in the bottom, we can modify the actor's behavior. So here's an actor performing a lane change into our lane, and we can see that the self-driving vehicle slows down and moves into another lane. So this is the kind of closed loop testing we're trying to aim for to achieve good performance signal on our autonomy system. Here's a couple other scenarios. We have a hard brake when an actor lane changes into our lane. Oh, some internet issues. And then another vehicle is coming into our lane, and we have to kind of brake and move to the side to overcome it. Okay. I wonder if I'll have more internet issues in the rest video. There are more videos, so we'll see. All right, and then that's kind of on like urban scenes. Here we're showing some results on some highways in Texas. So you can see here the simulated LiDAR and camera data on fast, high-speed scenes. Play one more time. Cool. So that's how we build digital twins from real-world sensor data. Now talk about speed. So previously, we've seen that neural volume rendering approaches with these dense feature grids can be sometimes expensive to evaluate and slow to render. So this might be on the order of like 1 frame per second or so. And this doesn't make it very scalable for evaluation and training because you might want to run thousands and thousands or millions of scenarios at a very high frame rate. And there might be also very large and complex sensor setups on your self-driving vehicle with multiple LiDARs and radars. We want to still be able to fit all of this rendering and evaluation on low-cost cloud compute to enable scale. So there's been a lot of work in the neural rendering community to try to accelerate volumetric radiance fields. And one approach that we took was to convert this implicit volumetric representation into explicit representations that can then be leveraged with graphics and rendering engines. So you can see here, we can run neural scene reconstruction to create a high-quality mesh, which has a good geometry of the original scene. And then we can also have learnable UV neural feature maps that we can then perform rasterization with to kind of reconstruct the original sensor data. And we can then leverage the computer graphics rasterization pipeline to achieve very high speed and parallelism. We also have some skyboxes here to leverage the faraway regions in the scene. So here's kind of like the overall pipeline. You'll have geometry and learnable feature maps. You can perform rasterization to get feature buffers. And then we have a neural MLP shader, similar to like previous work in like mobile nerf, that can then take into account view direction and kind of appearance changes that are view dependent to generate more high quality images. And then we can composite the foreground with the background to generate the final image. So here are some results. This is again showing that we can get pretty similar quality to the original volume rendering approaches, but with much higher frame rate, but not with internet. Yeah, anyways, but so we can get pretty high frame rate and rendering realism. And also this is with a lower memory footprint than typical volume rendering techniques. All right, and then here's kind of like a side-by-side comparison on the same truck log from before. We can then achieve like a pretty high frame rate. And this is now extending the neural scene rasterization to dynamic actors in the scene. So we can now model the dynamic actors and a static background for more scalable closed-loop evaluation. All right, so now we'll move on to controllability. So the previous kind of volumetric rendering approaches that I've talked about so far, they typically bake the radiance into the feature grid so that the outgoing radiance is already kind of stored in your location. And this kind of prevents us from doing the full controllability we might want to have in a closed-loop simulation system. For example, when we move the actors around, the shadows are sort of baked into your scene representation. But you might want to be able to control the shadows based on how they cast on each other actors, or be able to change to say the sun direction. This can create more variation and like diversity of the sensor data that you generate for autonomy testing. And additionally, kind of with current approaches that do this neural reconstruction, you're kind of limited to the actors that you reconstruct from the original log. And you can't really take actors from other logs or say leverage CAD models, which are still a good source of assets to use, and insert them into the scene. So the type of modifications we can do for these digital twins is still limited. And we might want to still be able to relight the scene entirely to a new condition, say from sunny day to a cloudy day. So in our recent work, we tried to tackle this problem. And this problem of being able to modify the lighting scene conditions is just a standard inverse rendering problem where we want to decompose the scene into geometry, material, and appearance. But this is quite challenging in large-scale self-driving scenes where you only pass by the scene potentially once in a single lighting condition, so it's very ambiguous what the decomposed attribute should be. So we try to tackle this in like 3 parts. So the first part is we try to run neural scene reconstruction to get initial estimates of the geometry, appearance, and lighting conditions. We use recent lighting estimation techniques to estimate the location of the sun based on, say, GPS and timestamp, and the overall appearance of the sky using panorama images from our self-driving vehicle. So given these type of relightable digital twins, we can then create an augmented reality representation. So augmented reality representation here is we can take actors such as CAD models or other actors from scenes we reconstructed and insert them into this new scenario and also modify the locations of existing actors. Given that representation and some target lighting condition, we can leverage existing physics-based rendering techniques such as the ray tracing engine to generate lighting relevant data. So the idea here is that we don't need it's not necessarily required for the network to learn all these components. We can instead leverage standard algorithms that have been used in the past to get the lighting relevant data, such as the shadows and the general appearance change. But the challenge with these type of algorithms is they often require perfect ground truth materials, shadows, and lighting conditions and geometry to achieve high quality results. So the third step that we do is we add a neural deferred rendering module. This basically takes the lighting relevant data from our scene representation and then tries to bridge the gap between the real lighting data that we observe for different scenes. This allows for targeted relighting given new lighting conditions. So I'll now show some results. So here is an example of some of the relightable digital twins that we have that you can reconstruct. So we reconstruct the scene, geometry, appearance, and also the lighting condition. We can move the sun around and change the shadows for the different actors. It's a little bit slow, but we can basically, as you can see, we manipulate the locations of the shadows based on this. All right, I'll move on. Cool. And then here's another video showing with these relightable digital twins, we can also insert new actors into the scene and simulate their shadows and have them realistically blended into the rest of the scenario. And we can do this from all the different camera views, so we can have it to be spatially and temporally consistent. Cool. All right. And here's kind of like a zoomed in view of this, where we basically have these relightable digital twins. So compared to prior works, we're able to also reconstruct the dynamic actors of the scene. So you can see here, for example, the dynamic actor we've reconstructed is able to cast a shadow on the inserted actor to create these kind of intra-object occlusions, which helps improve the realism of the camera sim. And here are some like simulated variations that we now can add additional actors, such as construction, into the scene, and also change the lighting condition compared to the original scenario. All right, PowerPoint next time, not Google Slides. All right, and then here's another variation. So you can see here, we added new actors into the scene. We have the construction elements and remove the original actors, again, in different lighting conditions. Okay, so say we have diverse reconstructions, we can have fast simulation system, and we're also very controllable. What's the question now is whether or not our simulator is realistic or not. So the main question we can ask ourselves is, how do we evaluate the sensor sim realism? And the typical way we do this actually in the computer vision community is this term called domain gap, where we often think about domain gap from a training perspective. We might train our data on simulation only and then test on our real world data and see the gap. And we might do the same thing by training on real world data and then testing on simulation and seeing the difference. But we're actually talking about domain gap here in a very particular situation, which is if I generate a new counterfactual scenario in simulation, is it indicative of what the autonomy system would do compared to what it would do in the real world? And that's an evaluation type of domain gap that is different from what we really think about usually. And the other aspect that's interesting is that once you have a way of evaluating the domain gap or realism of a sensor simulation system, is how do we identify what aspects of sensor sim are most important to a domain gap for a particular autonomy system under test? And the way we do that here is that in this approach, we take advantage of the idea that we build digital twins in the first place to reconstruct the original scenario. So the idea is that we can take real world sensor data, we can build a digital twin representation, and then given the same scene representation, we can simulate the original sensor data, in this case for a LiDAR simulation system. And this creates like a paired scenario setting. We can basically compare for the exact same scene location, SDV position, and other actors, what does a simulated LiDAR look like, and how do we compare that to the real LiDAR? And then we can, I won't go into too much details here, but the idea is that given that same scene representation, we can take the autonomy system, run it on simulated LiDAR, and look at its outputs, and then do the same thing with real LiDAR and look at the autonomy outputs. And then we can compare the differences. And we have some Oracle enhancements here where we can kind of make modifications to our simulated LiDAR and see how different modifications affects this domain gap. We cover a variety of domain gap metrics for autonomy evaluation. So we can do, say, detection agreement. For the same scene, do we generate the same detections of the actual actors in the scene? And we also make the same mistakes in the real world compared to simulation. So this is not the standard average precision and recall you might think about in computer vision. Is actually our pseudo ground truth is not labels, but the outputs from the autonomy system on the real sensor data. We're actually comparing, does the autonomy system generate the same outputs in sim versus real? The same thing for prediction, for match detection between both sim and real. Do I generate the same prediction outputs? And also for the motion plan, do we generate the same motion plans between simulation and real world data? And you can check the paper for more details, but we do several analysis of different types of phenomena we might see for LiDAR simulation, such as rolling shutter, motion blur, having multi-returns added. So you can see here, if we add multi-returns to the simulation, we can detect the vehicle in front of us better and match with the real world. And we find that there are like a couple of aspects that are typically not modeled in standard sensor simulation systems that need to be addressed by the community to improve the realism for autonomy evaluation, such as multi-returns, material modeling, and motion blur. Cool. So in conclusion, I kind of talked about the different parts of a closed-loop sensor simulation system, and in particular for sensor sim, talked about different explorations we've done, such as diversity, speed, controllability, and realism. So yeah, thanks for your time today. Really appreciate it. I'll take any questions.
So we're right at time, so I would suggest we take 1 or 2 questions while I set up for the lightning talk.
Cool. Thanks.
Do you mind if I already plug in?
Yeah. Sorry?
So how do you assess the cumulative error? For example, you from your driving dog.
Yes.
And you run your planner inside this river and also from the real data in a kind of open loop fashion.
Right.
So how do you assess the cumulative error?
Oh, that's a great question. So
Could you repeat it?
yeah. The question is that in the previous effort I just talked about for the sensor simulation system, most of the evaluation we did to compute the realism was in an open loop setting. For the exact same scene configuration, we compare simulated LiDAR versus real LiDAR and compare the autonomy outputs. But the question is then, how do we actually check and understand the closed loop simulation system's domain gap, which is actually what we care about at the end of the day, which is, does the autonomy system get to the same location or same state at the end of the scenario? And you can compute that type of domain gap when you have your full simulation system running in closed loop, and you can actually compute the difference between your self-driving vehicle and simulation in real world over time. And that's how you kind of compute closed loop error. In this particular paper, we focused mostly on the open loop, but that's because for sensor sim, you typically care only about a single state. You can kind of think of sensor sim as a stateless system, and that's why we can match realism there. But with behavior models and vehicle models and latency, you want to compute the whole error over time. So yeah, I think it's a good effort to do domain gap in a closed loop setting. Yes.
Thanks for sharing. First question I had, or actually the only question I had, is how resilient is this entire approach to changes in sensor set? So just coming from the industry perspective, sensor sets do change. How resilient is this? Can you do sensor evaluations with this approach before you use selection? Interested in sensor.
Yeah, great question. So for sensor simulation, if you can build like pretty high quality digital twin scene reconstructions, you can then test new sensor configurations, such as new cameras or new LiDARs. It just matters if whether or not you already have access to that data or if it's completely new sensors you're testing. If you're using sensors you already have collected real world data, then you can take the original digital twins you've reconstructed and apply adaptation techniques that kind of learn the new noise that you might expect with your new sensors. Or if you have like completely new sensors, there might be a small drop in like realism because you don't know the true like real distribution of that noise for the new sensors you have that you haven't really done development with in the past. But the more decomposition you can build into your digital twin representation of geometry, material, lighting conditions, the more robust and generalizable it is to new sensor configurations. If you just bake the radiance, for example, into your scene representation, you are kind of also capturing directly the ISP and like all the direct attributes you capture from the original sensors that you can't modify then if you have a new camera sensor, for example.
Yeah, thank you so much.
Thanks.
And with that, we go to the 5-minute lightning talks. Before that, just a quick announcement for the people who joined since the beginning. The poster sessions, unfortunately, are in the other building. So we'll have to hurry a bit to get there in time and back. Also, all the posters and all the papers are actually on our website as well to download. So please check that out as well, because I think the time will just too little to check out all the posters. And there are more posters than we have lightning talks. So just to be aware. And yeah, with that, I would like to introduce the first speaker. Yeah. That's yours, right?
Yeah. Okay. Morning, everyone. This is Howie. I'm from University of Michigan. So this is a previous published paper before, like 1 year before, and featured the cover of Nature at March 23rd, cover 2023. So I'll just briefly discuss our newly research update here. So this paper is called Dense Reinforcement Learning for Safety Validation of Autonomous Vehicles. Specifically, we are trying to answer one question. When we are talking about safety validation of autonomous vehicles, we want to know, like, how many miles is required for us to generate one crash, injury, or fatality? So that is two different questions. We want to get this answer accurately, but with small number of testing miles. That's the reason why we are proposing the architecture. You can see it from the picture. Up front, you can see there's autonomous vehicle driving in a simulation environment. We have all the background agents, traffic participants, trying to learn how to intelligently challenge the autonomous vehicle to maximize the evaluation efficiency. So this is what we call naturalistic and the self-driving environment. Basically, we can formulate it as a reinforcement learning problem. We just want everyone to learn how to challenge. So basically, we use the Markov decision process to formulate this problem, and with the designed reward function. So I will not go into details here, but the thing I would like to say is that maximizing the reward in the reinforcement learning problem essentially means maximizing the evaluation efficiency. However, the normal deep reinforcement learning algorithm cannot actually be trained under such environment setup because of the problem we call curse of rarity. That means that the valuable information in our training data set is so rare. We're talking about the safety critical events. So that the normal deep learning algorithm cannot learn from such unbalanced data set. That's the reason why we are proposing the dense deep reinforcement learning. So basically, the first part is the dense learning. We have the sample data, a large scale of data set, and only a small proportion of them is actually safety critical. So we can use some data processing or filtering method to filter out the data that is really safety critical, that is really important, and utilize that to train our model. We can mathematically prove that this will give us the same expectation of the training results with much smaller variance. So that can enable the deep learning algorithm that is originally untrainable to be trainable. So extend that to reinforcement learning is what we call dense deep reinforcement learning, or D2RL. It's pretty simple. So we have the neural network who is making the decision at each time step. We can expand it as a decision tree, and we have the metric or the indicator to identify critical states from uncritical states. Then we just simply remove all the uncritical states and reconnect the critical states. That will be a train or a shadow tree, and we just train our reinforcement learning algorithm based on this train tree. So this is numerical studies and field experiments. So in our experiment study, compared to the what we call ND or naturalistic driving environment without any modification or like the NAD algorithm, we will require 1.9 times 10 to the power of 8 number of tests. With our algorithm, we only need less than 10 to the power of 5. So that's about 2,000 times faster. So I'm coming from Michigan, from MCT. So we have some field tests in American Center of Mobility and MCT, 2 test tracks in Michigan. So we achieve up to 10 to the power of 5 times faster than the naturalist driving environment. So yeah, long story short, this is quick. So we have the paper available at this link, and we have open source all the source code available as this GitHub repo. And we are building our simulation, the generative AI powered simulation toolchain based on all the algorithm we propose. It's called terracing. We want to accelerate the AV development cycle. So you can see, you can check out the link here, and this is our we're spinning off an autonomous driving company called Safer Drive AI. So if you have interest, please come to me. And we also have several posters just in this session, and one is called the D2RL, and another one is no mode transformer and RACL. So if you have interest, please come to me as well. That's it for me today. Thank you.
You can come, but you sent me the keynote, right?
Hi everyone, my name is Controllable, and I'm very happy to present our paper here, dynamic LiDAR resimulation using computational neural fields. So manual creating LiDAR scans with also the driving annotations are very expensive. So enabling LiDAR simulations for the driving scenarios are very crucial for training self-driving vehicles. So in previous work, LiDAR sim has leveraged a surface representation which is explicit, it's fast, but the reconstruction quality is behind state of the art. And the recent neural fields for LiDAR has leveraged NERF to focus on reconstruction quality, and also focus on the LiDAR essential properties like the two-way transmittance to further enhance the geometry reconstruction of LiDARs. However, this work only supports the static scenes. So the goal of our work is we try to resimulate the LiDAR scans in dynamic driving scenarios, and we try to enhance the geometry reconstruction. And we also want to lower the domain gap between the real and simulated LiDAR. And also we want to provide very rich scene editing capabilities. So given the collection of LiDAR scans, we will first, so given with the poses and bounding boxes of the vehicles, we'll first decompose the static and dynamic parts of the LiDARs. And we will train N+1 neural fields. So the N here is the number of the dynamic vehicles in the scene. And then we, for the volume rendering, we derived our own dedicated formulation for the SDF-based volume rendering formulation. And on the left side, you can see a classic news formulation. And on the right side is our new modification for the active sensors like LiDARs. So in the test time, we will perform a ray box intersection test to acquire K+1 LiDAR measurements, including LiDAR, including the range estimate intensity, as well as the ray drop probability. So the ray will be classified as dropped if all of the LiDAR measurements has yield dropped, so the probability is greater than 0.5. And if at least one of them has not dropped, then we will select the closest range estimation as our final estimation. As you can see here, we'll provide a very simple example here. So the first vehicle that yields the non-drop probability will be selected as the final estimation. So for the evaluation protocol, we have designed two evaluation protocols. The first one is called Waymo Dynamics. So we select 4 things from the Waymo open datasets, and we keep every fifth. So we have in total 50 scans, and we keep every fifth scan for training. So basically it measures the interpolation performances. And for the Waymo Dynamic MVS, we use the same things, but we incorporate a different evaluation protocol to measure more focus on the novel affinities performance. So this is a quantitative evaluation of a method in both evaluation protocols. So you can see our method has outperformed Unisim and LiDARsim in terms of both the range estimation as well as the intensity recovery. And this is the qualitative comparison of the range estimation on Waymo dynamic dataset. So we have zoomed in the dynamic vehicles, and the points are color-coded by the range errors from the -1 meters to 1 meter. And this is the domain gap evaluation performed by of the detection results. So we showcase the detection agreements for both ours and the other methods. So the detection agreement basically measures how similar the detection results acquired from the ground truth and between the results acquired from the simulated LiDAR scans. And you can see here our method has also outperformed the LiDARsim, which yields better domain gap. And this is an evolution study of the active sensing formulation. So the green numbers here is improvements of when we adopt the active sensing formulation and we can compare with the passive formulation. And finally, I want to show you the scene editing capabilities that we did. So we have provided 3 use cases. So the vehicle removal, trajectory manipulation, as well as the vehicle insertion, and compare it with the original scene. And in conclusion, so the NFL presents a novel neural fields composition method for LiDAR resimulation and excels previous art in both of geometry reconstruction and domain gap. Meanwhile, it offers very powerful scene editing capabilities. However, it struggles to synthesize the vehicle from unseen angles, and it also relies on the bounding boxes annotation. So thanks for watching. Yeah.
Okay, morning everyone. I'm Yi Liao from Zhejiang University, and unfortunately my student is not here due to visa issues, so I'm presenting our work HUX, Holistic 3D Scene Understanding by Gaussian Setting. I guess all of us are in this room because we believe that data-driven simulation for autonomous driving is very important, and we are also one of them believing in it. And except for rendering photorealistic images, what we also want to provide is a multimodality output. This, for example, also enables evaluating like perception models in a closed-loop fashion, right? And of course, there are also previous works, very nice works in this direction, like NSG or Mars. And these methods, they use nerve as the representation, which prevents real-time rendering. And moreover, they require ground truth 3D bounding boxes as input. This is quite expensive to annotate. And the goal in this work is that giving a single RGB image, single RGB video as input, we would like to first fit this into pre-trained networks to get noisy optical flow, semantic, and 3D tracking predictions. And from those noisy input, what we aim for is a holistic understanding of the 2D and 3D world. And in terms of both semantic, mobile synthesis, semantic synthesis, optical flow rendering, and depth. And this is the overview of the method. We first extend 3D Gaussians with model information. So not only modeling appearance, but we also model semantic and optical flow. And secondly, we decompose the scene into static and dynamic regions with multiple rigidly moving objects. And to tackle the issue for requiring 3D ground truth bounding boxes, we use a unicycle model. We introduced to use the unicycle model to regularize the motion of the objects, allowing us to reconstruct the dynamic objects from noisy 3D bounding boxes. Okay, so some more details about the method. We first extend the 3D Gaussians to multimodality. So we add semantic logics to each 3D Gaussian. And for optical flow, we don't actually need to introduce additional parameters, but just tracking the center of the 3D Gaussians, how they move. And with this, we're able to render all of these modalities together with a single neural rendering pass. So the rendering time does not so we don't add too much extra additional time on top of 3D Gaussian, and we still enable rendering all of these modalities at more than 100 FPS. And as we mentioned, we will aim for like holistic understanding in both 2D and 3D. So not only we are able to provide photorealistic rendering, but we are also able to extract semantic point clouds from the reconstruction. And what we also observe is that while the naive way is to you simply extract the 3D Gaussians using the semantic label of each Gaussian, right? But what we want important is that we should perform softmax in the 3D space instead of in the rendered 2D space. If we simply apply the softmax in 2D space like previous work did, then we get quite noisy 3D Gaussians. So actually,
there's nothing we can do.
Okay, so I will just shout. So yeah, that's by applying the softmax in the 3D space, we get a quite clean 3D point cloud. So this actually also, like in some sense, the semantic labels also help to improve the geometry in the 3D space. And we also perform scene decomposition, and as illustrated here, And as I mentioned before, we do not rely on 3D tracking ground truths. And on the left, we show if we do not have the ground truths, and if we simply use the original noisy bounding boxes, this is what we obtain. On the right is the naive way of optimizing the 3D bounding boxes using the rendering loss. And this is what we obtain. Okay, so what we introduce here is this unicycle model that constrains the moving trajectory of the objects. This allows us to avoid the local minimum and being able to obtain good results. And this is how it's implemented. And we also show how the noisy trajectory evolves over time. And this is a comparison to the baselines. And here are some more results for holistic urgency understanding. And we also, this method, of course, also generalizes as well to other data sets like NewSync, Waymo, and Panda dataset. And if you're interested in more details, please find us in the poster session. And we're also presenting this on Friday at the poster session in the morning. And please come to talk to us. Thanks.
Thank you very much. Yeah, apologies about the sound. We were told that there's absolutely nothing we can do. That's somehow the building. It's slide. This is you, right?
Okay. So hello everyone, I'm Tobias, and I'll present multi-level neural scene graphs for dynamic urban environments. This is a joint effort between ETH Zurich and Materiality Labs. So as we all know, today driving data is really available at a truly unprecedented scale, and this gives us the opportunity to build up-to-date digital twins of entire cities, but also poses unique challenges due to the characteristics of the data. That should actually be a video. Yeah, so like here you should be able to see like the same intersection covered in the Agverse 2 driving dataset in very varying conditions. So basically this limited scene coverage and the varying lighting, weather, season, and even geometry through, for example, dynamic objects. And these captures makes building neural scene representations from this type of data extremely challenging. And while dynamic radiance fields have made great strides in recent years, they are still somewhat limited to certain scenarios, meaning that the training data that these approaches are trained on usually contain either teleporting cameras, where you have multiple views for the same time step, or quasi-static scenes where the camera moves much faster than the object itself, creating a similar effect to the teleporting cameras. But when we deal with the wild captures, we often have fast motion and like limited viewpoint coverage. So like how do we deal with that? And like previous works often basically just neglect the dynamics of the scene, yielding good but incomplete reconstruction results. And then there are also some works that deal with dynamic scenes, but they are either limited in terms of scalability or struggle to represent dynamic object instances. And therefore, the goal of this work is to make dynamic radiance field scale. And for this, we represent a scalable multi-level neural scene graph representation for dynamic urban areas that scales with 10,000s of images with hundreds of dynamic objects. And to efficiently train and render this representation, we propose a composite ray sampling scheme where the key idea is to estimate the density along the ray jointly across all nodes with efficient proposal networks. Okay. It looked different in my presentation. Please come to my poster, then you can see how it really looks. And finally, we propose a benchmark for radiance field reconstruction of dynamic urban environments from heterogeneous vehicle captures. So we basically choose common geographic regions of interest from the Agverse 2 driving data, and then basically have dozens of captures in different conditions where we jointly estimate one scene representations from. And if we compare this to the state of the art, well, let's see if that really works. We should be showing a normal trajectory here with a slow motion effect in the middle, and see that our method actually represents the statics and the dynamics both much better than previous works, and also like here we can change. So like basically, okay, maybe you can see it a little bit, right? Like here's the first sequence and here's the second sequence, which is it's the same model, but in completely different conditions. So it represents the scene in different conditions from one model. And also, if you would change now the sequence basic latent code, the object appearance will also change. So like the car that you would render in a sunny conditions looks different than in rainy conditions, right? And that's also a property of our method. And so overall, basically, we present a normal scene representation that is scalable, that can be trained on large-scale heterogeneous data, and allows for flexible de- and recomposition of both objects and the scene conditions. And however, it has some limitations still, which we actually tackle in our follow-up work, which has recently released on archive, where we use 3D Gaussians as an efficient geometry scaffold and Nuro fields as a compact but flexible appearance model. And well, here you should be seeing a demo. Maybe check out the project website here on the bottom if you want to see the demo. It's really cool. Yeah, and I look forward to the postal session. We also present this on Friday, also in the morning session at 10:30 a.m. And yeah, thank you for your attention.
Yeah, apologies about the videos. I don't know what went wrong. But I learned that you can't just copy Google Slides together.
Hi. Hi everyone. I'm Shanlin Sun from UC Irvine. Today I'm glad to present our CBR 2024 work, LiDAR RF, which I mostly done during my internship at INSEE Lab America. Okay, so we aim to create a. Why is doesn't move? We aim to create a futuristic 3D simulations using data from RGB cameras, LiDAR, and sensor pulses. And our simulations can accurately reconstruct the 3D scenes with minimal artifacts, which is crucial for developing and training the autonomous driving systems. It should be a video. I would like you to see the details and realism we achieved. You can go to our project pages maybe afterwards. So okay, we are considering how can we go beyond just take the LiDAR as the lab does. And in this work, we have three main contributions to improve the quality of nerve factors in the 3D scenes with the LiDAR data. And first, we framework lens geometric representations with a sparse convolution, and which is then fused with a great base of representations for radiance decoding. Second, we are considering to develop occlusion-aware depth distributions to use a more densified depth maps. Third, we generate the augmented training views from the LiDAR points and to further enhance our performance, especially for the lens shifted settings. Okay, inspired by the 3D perception framework, we developed a 3D sparse convolution network to encode the 3D features of the 3D scenes in the context of the local and global point clouds. However, LiDAR doesn't cover the whole scenes due to the limited field of view, especially in the vertical directions. So we fuse the LiDAR features we obtain from the sparse convolution with the hash grade features to combine the strengths of both for high quality and the complete scene rendering. Let's look at the effect. With our LiDAR encodings, we can model more high quality sharp textures. For example, here like the power lines, and also we presented our sparse convolution based methods is better than the other designs like MLP or 0.9++, or just doubling the hash rate to its size. And we also use LiDAR for depth distributions. But since the LiDAR points are sparse, we accumulate points from nearby frames to get a denser depth maps. But these depth maps can have the occlusion issues due to the displacement between the cameras and the LiDAR sensors. Our robust depth distributions apply the curricular learning to gradually filter out the bulky depths during the nerve trends. And also our curricular learning can be applied to any types of specific depth loss. This figure compares the different LiDAR depth distribution settings. Let's focus on the regions highlighted by the red and the yellow boxes. So the single frame LiDAR depth distribution is accurate in texture-rich regions, but struggles in the with the thin structures. And the accumulated noisy depth LiDAR depth shows noticeable noises in these middle columns. And our proposed methods effectively use a denser depth maps for precise reconstruction, and at the same time can generate relatively clean depth estimations. And our vehicle-mounted camera generates sparse training images with limited view coverage, posing the challenges for nerve reconstructions and rendering when we do the land shiftings. By colorizing, accumulating, and projecting the LiDAR points to the novel views, we augment the training data. We also applied the same curricular learning strategies to filter out the occluded signals, RGB, including the RGB images and depth points during the nerve training. As seen in the example on the right, our proposed augmented view supervisions can significantly improve the rendering qualities when it comes to the land shift settings. We evaluate our methods under interpolations and interpolation settings. For interpolations, we subsample frames and test on every fourth frame. For extrapolations, we shift the lens. Here we present the visual comparison between our methods and the other state-of-the-art methods. And our method shows enhanced visual realism, particularly in rendering the fine structures in the lens shifter settings. Currently, and in the future, we are developing more applicable appearance simulations that supports real-time rendering, dynamic object compositions and control, and on-scene reading imaginations. Stay tuned. Thanks for watching, and see you at today's poster session and both on the Friday sessions. Thank you.
Thank you very much. And for the last talk.
Good morning. Good morning, everyone. I'm Tianbiao Zhao. Today, I will be presenting our first place solution for Waymo Agent Sim Challenge 2023. Our multiverse transformer adopts a transformer-based motion predictor into an autoregressive generating model for closed-loop multi-agent simulation. Our multiverse generator generates a multitude of parallel universes. Each one mirrors the locked real-world driving data. Here's the overview. In this challenge, the simulator is supposed to simulate states of the agents at 0.1 second intervals of the oncoming 80 timestamps, and the simulator must be closed loop and runs in an autoregressive manner. All agents and ADV must be conditionally independent. The traffic agent simulation is closely related with motion prediction. We use agent-centric and autoregressive approach. The simulator is a learning-based generative model and closed loop. Our work is inspired by traffic sim and MTR. And MBTA utilizes encoder-decoder transformer-based network. The encoder uses agents, ADV, and maps to produce scene context features. The decoder produces multimodal predictions to simulate the oncoming 0.1 second. Our training is end-to-end in a closed-loop manner. In the training, we randomly pick a point to separate a trajectory to history and the future components instead of using the fixed history. For the loss, we use a negative log likelihood loss and the regression loss for velocity and heading. In the decoder layer, the prediction horizon is 1 second, but only the waypoint of the initial 0.1 second is utilized, and the rest of the prediction is discarded. This is to promote multimodal diversity and reduce the compounding error. This also introduces more flexibility in the inference setup. In the inference, we use top K sampling to promote multimodal diversity. To strike a balance between realism and diversity, top K sampling is applied at periodical intervals. Here's the example showing case the autoregressive rollout. Here are 10 frames. Here's the V0 lead board. As you can see that our model MVTE reached the highest score for the realism mathematic. Here's the V1 leaderboard. Our method maintained the leading position till February 14, 2024. The video is not working. Okay, here's an example. I would like to share with you some results produced by our method. In this example, there is a vehicle waiting to get on the main road, the brown one, and the car can turn left or right, or keep waiting. In this example, the vehicles pause at the intersection, and it's not moving. And the vehicles are ready to make an unprotected left turn, waiting for the oncoming traffic to be clear. In this example, you can see that ADV makes a slow right turn, forcing this purple one to slow down or stops. And here in this example, the pink car behind the ADV attempts to switch lanes, overtaking the ADV and the remaining slow traffic. And on the left side, the ADV slows down to allow a car merging onto the main road. But on the right side, you see that ADV proceeds straight instead of waiting. To wrap up the presentation, we proposed a transformer-based generative model for closed-loop traffic agent simulation. We proposed a novel training, sampling, and inference strategies. We were the winner of the Waymo Open Sim Agent Challenge 2023. In the future, we plan to explore large language models and the scene-centric and diffusion-based approaches. Thanks.
Yeah, thank you very much to all the lightning talk speakers. Yeah, like I said, the posters are unfortunately in the other building from 157 to 181. That's the poster location. As an additional motivation to go there, I've heard there's free coffee. And yeah, we'll be here back at 11 for Drago's talk. Thank you very much.
Easiest way to get there, just walking down the street, or is it?
Yeah, there's no
one
out.
Yeah.
Do you know if it's at like the 7th Street entrance, or any idea where?
I haven't been there yet. So
the thing is, once you go out the building, there's like circles on the ground, like directing you to
follow.
Yeah.
Because on Monday I started over there and they sent me over here.
Yes, and
the building was like 2 blocks long. So I'm like, I don't want to go over that building and like start searching all over.
Yeah, so I would hope for these circles to guide you.
Yeah, I'll start on one end and walk over.
Hi.
Yeah, so we also have a few videos in our presentations.
So yeah, let's check. So it wasn't the copying, it was the sharing, I think, because on the original slides that I got from them, it also didn't work. I just checked it. But we can just check now if you want.
Yeah, we have PowerPoint. So we're wondering, did you convert them to Google Slides?
No, PowerPoint is PowerPoint.
Okay. So that probably will.
That should be fine. So you can have a look.
Yeah.
I guess Max, you can mute.
All right, can you hear me? Can you hear me now? Yes, the echo was because I had you on speaker. Great. Sounds good. Let me check. I mean, I do have some videos.
for the
What about video? We don't need my video, right?
yeah the video. You can if you want to.
Then
but you
like
don't.
online people see you, but I mean, it's more important that they hear you clearly.
What do you guys want to do? Okay, well, let's do it later.
Yeah, up to you.
All right, present the view. Okay, rock and roll.
Yep, works perfect.
And does this one go?
You
No.
can switch on here.
Okay. Test, test.
Oh, yeah, and you probably know it from yesterday. Sometimes the sound cuts out, but there's nothing we can do.
Yeah, that's fine. I can talk loud.
Sounds good.
That's the one thing we can do, actually.
Yeah, how's it been in NVIDIA?
I like it. Yeah.
You in Zurich or where are you?
Yeah.
That's closer to home.
Yeah, no, it's which was a large part of the reason as well.
Yeah, well, I mean, also
Closer to family.
yeah, with more publishing, right? So,
yeah,
I think, I mean, Marco team, I would say, yeah, bigger proportion of their work gets published. Yeah. That's how we drive cars.
Yeah,
Only for you, they're far away.
That's the
Well, for us.
Then share.
And the video shows. Yep. Shows. Cool.
Yes, you can reduce, but that's actually not much use.
Do you want me to say a few words? Do you just want
That's totally your call. I'm happy either way.
up to you?
I'm fine starting unless you have some. You're almost there. 10:59. Turn off my phone so it calls me. What I said. Okay, maybe I should start. So we made it to 11 o'clock. My name is Drago, and yeah, the screen still works. I lead the research team at Waymo. And today I will plug the cable hopefully correctly. And what happened?
I don't know.
That's beauty. Let's see. Okay, there we go. Okay, let's hide this and proceed.
You have to share again though, because the screen was disconnected. Zoom stopped the sharing of the second screen.
Oh, okay. So 1 second, guys. So I need to disconnect.
Just share the screen on Zoom again.
You know, just
where do I go find it?
At the bottom right of the taskbar.
This one?
No, at the command. Oh, it was just here.
Oh, no way. So
I think we just
I just say and show. And then, all right. Then I think that screen we need to re-add it again. Displays. What does it say? Down mirror. Is this one? That's the main display now. Okay, well, stop mirroring. Okay, now we're good. Now I need to go to Zoom. Join meeting, where am I?
I think aren't you still in the meeting? You're still in the meeting.
You are still in the meeting.
Okay, so I'm in the meeting.
But this you exactly expand this.
Okay, well, let me start first. I actually had to do this first, right? Where is Zoom? Where did it go? Here. Okay,
Exactly. And then
share, desktop, share.
and now start the presentation.
Okay, let's go. This time, well, maybe we'll be more lucky. 1 second. Ta-da! Okay. I lead the research team at Waymo, Alphabet's autonomous driving technology company. Thank you for having me. I will tell you some about our work on the topic of simulation and applying machine learning to simulation. So we are Alphabet's autonomous driving technology company. This is our standard kind of interstitial, but maybe the new point is by now, autonomous driving is deployed in several cities in the United States, major cities. It is real. And you guys, if you come to those cities, you can experience it. And maybe the new fact here is that the 50,000, over 50,000 trips by paying customers by now in Waymo's doing autonomous driving. And we do this in the following cities: San Francisco, Phoenix, and LA. San Francisco is around 45 square miles. This is the full limits of the city. You can ride the Waymo to all parts of the city. Phoenix, this is the latest area. It's 315 square miles where we provide service. And this is our current LA territory, which is launched and also with driverless operations for customers. This is around a bit more than 50 square miles today. And yeah, in some of these cities, San Francisco and LA, we still wait lists, but we are gradually working through them. So it should be hopefully soon we will have those as well. And our next city is Austin, Texas. We already started doing driverless operations in around 50 square miles there, but it's still in a limited amount. Looking forward to bring this more widely soon. And of course, autonomous driving is challenging. I think I don't need to convince people, right? It's a safety critical application. There's real-time latency requirements. And the thing I think about a lot is the complex high-dimensional input. We have a vehicle with many sensors. They can have hundreds of millions of sensor readings per second. And, you know, often you need long-term context to understand the scene and what you should be doing on a high level, especially in the scene. And so I think of this as some big tensor of inputs that now needs to be processed and understood to generate the otherwise simple outputs of steering and acceleration. And so it's a difficult task, and the inputs are really complex and diverse, right? And nevertheless, we've made significant progress. Waymo is around for 15 years. And now I'll show you a short clip of our recent driving in the cities that I described. So here's an interesting situation in San Francisco. There's a truck in a narrow street, and we understand that we need to unblock the truck. So we back up and park. This is all in driverless mode, right? And then we let it go, and then we continue on our way. This is an example of a complex intersection in terms of construction and human traffic. How would I say? There's a person directing traffic, and we deal with it. Here is ubiquitous, I think, San Francisco, if I recognize correctly, construction that we see a lot. And this is us, you can see in the scene on top, this is our LiDAR sensor and segmented into objects. And you can see how we parse and understand the scene. This is an interesting case where a fire truck blocks several lanes. So we need to understand what is permissible and still make progress. This is an interesting case where someone swerves in our way, and we actually need to know to exit to the side quickly. So you do an evasive reaction to mitigate an otherwise very unreasonable driving by oncoming traffic, right? So this is just a few, but the list goes on and on and on, right? It's a big space. And as a machine learning person, I mean, in a lot of the talks in these workshops you see is you say, okay, so we want to do machine learning for autonomous driving. We want to build this driver. So, well, we want to learn as much from the data we collect. That's kind of the mission of a machine learning person in our domain. And of course, maybe others have collected on the web or otherwise. And so, you know, we want to be able to understand and predict the environment, so leverage the data collected to do this. And of course, we have this big crutch of there's all these human driver demonstrations of driving, and we want to leverage and learn that, right? So by and large, the challenge is generalization, how to learn the most from our data. And there is a second problem that we don't talk about that one works just as much on, I believe, or potentially more, which is ML for autonomous driving testing. And it's kind of a sibling problem to the original problem. And right, it's difficult to just evolve your system and test it with miles in the real world as you make changes, right? Sometimes it takes very many miles to encounter the things that you're addressing. And so simulator is an invaluable tool. And so you need that for scalable system validation. And there are certain use cases that it's good for the simulator to support, such as realistic scenario replay, scenario generation for especially risky or rare things. And of course, last but not least, I'm not sure that's a feature or not, but it's a multi-agent environment with agents populating and reacting to our actions in different ways, which we need to also address. And so as a machine learning person, it's kind of a sibling problem to the original one. I want to learn as much as possible a realistic simulator from our data, right? Real to sim, also known as a topic. I think real to sim is great. It's another way, a great way to, again, leverage your data to even test better your original system. Uh-oh, I should never touch my laptop or, okay, let's see, maybe it works.
But Zoom stopped again, so you'd have to share the second screen again on Zoom.
Okay, so I'll just share.
Yeah, here, exactly.
Okay, share. How is it now?
Yes.
Yeah.
Hey, we're getting more efficient. That's awesome. So we want to do this. And again, let's see if, yeah. And again, the similar generalization challenge. I want to learn the most from the data I have to build the best simulation environment I can. And today I will tell you about some of our work towards this goal on a few different topics. So first one is sensor simulation. That's a key capability, right? If you're testing your full system, you should be able to generate the perception inputs in a closed loop environment. And we have been working on this for a while in the whole field. We were actually, I believe, the first to publish work using NERF to map large areas. This is a paper of ours from CVPR 22 in a collaboration with folks from Google Brain at the time. And what we did was we showed how to extend NERF such that we can do sensor simulation of entire city blocks. This is Alamo Square in SF. You can see some non-trivial part of the city. And we could do things like this, right? So we could just, well, fly or drive in this virtual environment and go for a long way. So it's actually having a neural simulator. In this case of the static world, as we remove the dynamic objects, potentially to reinsert them later. And other cool things you can do is also we could model the environment across different conditions. So this is our NERF model capturing various lighting conditions during the changes during the day, including even different traffic light colors potentially. So this is all great, but there were some drawbacks. I think one is that if you look really carefully at these videos, they're still quite blurry in a few cases, an artifact of the NERF technology of the time. And the other part that is worth pointing out is that it's actually quite compute expensive to generate these NERFs. So it takes a while. It can take over a second on several GPUs to generate an image. And that does not predispose you to developing this or trying to leverage it. If you're driving billions of miles, do you want to generate, well, maybe a dozen images for billions of miles? That's not necessarily the ideal proposition if it takes a second or more. And so in 24, right, we can show a more recent work that tackles these challenges head on. And it is based on 3D Gaussian splatting. I think a lot of you probably know what this is. This is a seminal paper from SIGGRAPH that we well, noticed and appreciated, right? So this, unlike NERF, it's an explicit representation, maybe a bit more old school. The scene is made of these anisotropic 3D Gaussians with appearance information associated with them. The beauty is that that representation is compatible with traditional graphics engines, so you can just leverage the hardware as is, as it was designed for efficiency. So you can try to render comparable quality, but a lot faster. And so this is maybe for those that want to know more about Gaussian splat. I will just say there's some pipeline where if you think of these 3D Gaussians in space and you sort them by depth, and then you can project them on the image space and blend front to back, you can do differentiable ring and adjust, optimize your Gaussians as a learning problem. And then we're back. Given this, right, there's a lot of very exciting approaches out there by now that do 3D Gaussian splats, and people have, of course, applied them to our domain. There's just an example of a great work, Gaussian Pro. They show a normal city street. Now, the interesting thing for our use case is if you want a simulator, you want to drive closed loop in the simulator and potentially diverge significantly from the poses you initially captured. And so for a lot of these approaches, when you do that, you start getting various artifacts. It's a great approach with great outputs, but if I visualize the underlying geometry that the authors themselves were very kind to share, right? You can see there is maybe better to be desired potentially, right? And I think this geometry artifacts, the more you deviate from your original viewpoint, the more they will become noticeable. And so this is, in contrast, our work, we paid a lot of attention to doing this in high quality. And this second video, if I can click it, let me click it, is our 3D Gaussian splats. And you can see now we're gonna take a little bit of a zoom and we'll show you the actual fidelity of everything that we have reconstructed, right? And in this environment, it looks even great from, well, bird's eye view. So how do we do that? We use, well, 360 cameras, which helps, but also LiDAR, which is a great source of accurate 3D geometry, especially at longer ranges, and also, of course, in less well-lighted conditions. And now, how do we leverage it? There's two main uses. It's really helpful to initialize the splats, after which we do this differentiable optimization process. And it's also very useful as a geometric regularizer. And so when we do this, we do scene pre-processing, we aggregate the temporal points, we colorize them, we estimate the surface normals. We do panoptic segmentation in both the 3D representation and in the images for the masks. Then we pick the objects we would like to reconstruct. We keep the corresponding 3D points and estimated information, and we bootstrap the process from there. All right, and that's what, and for now, I'm going to show you guys mostly the static world. So that's what we do. And this is what you get. Again, this is maybe if you're familiar with Waymo open data set, we have the first 5 cameras. Here's full 8 views, 360 around the vehicle. And this is generated from a 3D Gaussian plots. And now the good news is, I mean, you can see the quality is very good and accurate. And also, we have a benchmark of what did we achieve in terms of speed since we started motivating this. So unnerv implementation, not necessarily block nerve, but more recent one, takes about a second plus, runs less than 1 hertz for images the size I'm showing on 8 GPUs. And with our 3D Gaussian splats, we can run at 40 hertz on 1 GPU. All right, so that's really good. And we also can run actually on CPU. So it's still 8.5 times faster than nerve on GPUs, which is also very appealing, right? So that's something was achieved. And then, of course, this is the original trajectory, or closer to the original one. Here is a virtual trajectory, just to demonstrate that something quite reasonable was achieved. So we're doing a happy sinusoid wave drunken driving, and the drunken driving looks good. So that's what I wanted to say about sensor simulation. Now let's focus on a different task about the traffic in the scene. So there are key tasks as well. I think a lot of the testing relates to how we behave in relationship and in interaction with other agents. And so, right, and these are scenes like populating a scene realistically or modeled agent reactions. And we've given a lot of talks on agent modeling, and I think if you even came to our Waymo talk by Song Lee yesterday and the workshop on autonomous driving, you would have seen a method called motion LM. So there is a lot of interesting things you can do with these autoregressive transformer decoder models, and including fine-tune them with reinforcement learning and other things. But today, I will actually talk about a different area of research that we have been doing, one that I think particularly suitable for simulation. And this is diffusion modeling. And so today I'll present some results from research work that we did. It's fresh and submitted, and it's based on a work called Scene Diffuser, which is a unified approach to address 2 key stages of traffic simulation. So one is scene initialization, so populating traffic layouts on the scene. So you may not be able to see too well, but there's a road graph, but then you can see the diffusion process populating a scene with a bunch of agents, and these are their trajectories. So this is also the future that kind of gives you an idea of their velocity and so on, how they go, right? And the dark spots are the position, initial position, so the vehicles and pedestrians in that case. And then, of course, once you do this, you also have scene rollout. These guys get to move and generate, joint futures. So this approach addresses both. And now, for those that are not particularly familiar with diffusion models, right, this is a key recent generative AI advance. So if you have an image you may like to generate, you train the model by applying noise model, in this case, maybe Gaussian noise, and iteratively denoising it. And then you train noising it, or then you train a denoising model that recovers the structure from the noise. And then as you sample noise, you get diverse images from this process, right? And so this example is actually standard, I think, from some of the first papers, but you can also do this to trajectories, such as those produced by sim agents. Here is maybe agent trajectory diffusion in action visualized, right? So you start with high noise, and then structure emerges at trajectories that you may recognize as reasonable. So, okay, so we have diffusion. And scene diffuser represents this whole diffusion tasks as in-painting on the scene tensor. So what is the scene tensor? Imagine on vertical line you have agents, 1 to n, and including the autonomous vehicle, if you want. And then on the horizontal line, you have time. So blue is the past, second column is current time, and then the columns that follow is future times. And last but not least, you have the features. So there's a set of features associated with each of these tensor cells that correspond to agent state at this time. And so when you have this tensor and think about it, then creating scenes and evolving them is related to just impacting on this tensor. So you can imagine you preset parts of this and hold it fixed, and then you get different tasks that you might be familiar with. So this first one is behavior prediction. You have the past and the present, and you want the future. You can then do intent conditional behavior prediction, where you have the past and the present and the intent or the future of some agents, and then you play others. You can just do, of course, different variants. You can fill in agents, or you can just generate the scene from scratch completely. So all of these things are possible, right? And you can input variants of these and get the full scene. And in terms of features, the features are generic across all object types. So you have some kind of position, orientation, a type, and dimensions, right? Which is typically what's a bounding box. It's a reasonably compact feature representation, and we do the diffusion model over those. And here's the applications, maybe just to give you another look. So if the log scene is on the left, you can add noise to this log scene and apply the diffusion model and perturb it. You can inject new agents to test counterfactuals like this magenta thing. You can also just generate new synthetic scenes using the same intersection as you wish. So we can do all of these. And the model itself is a variant of Perceiver AO and uses transformer backbone and is trained with a single L2 denoising loss with the popular now representation called deparameterization. And one of the strong advantages of using diffusion is that the framework allows us to explicitly specify constraints on the denoising process at inference time, right? So natural constraints for scene generation would be non-collision or be on the road, or in the Waymo open data set, maybe don't generate agents that are over 75 meters from ourselves anymore, because we knew that by then that's the visibility range that we modeled in the first place. So these are constraints that you can inject, and they can be added in the process as you're denoising in the various iterations interleaved with the model. And so that actually has positive effects. So if you have no hard constraints, it actually can generate scenes where vehicles overlap, which is not good. And if you just run the process all the way and then apply the constraints, you get unnatural parking, I would say, distributions. People don't park behind each other much in parking lots. And here, then you have a lot more reasonable as you iterate with these constraints in the scene. And for the specific definition, when we put the paper up, you guys can see more of the details. But the constraints are effective. And here's some results. Maybe first to give you an idea, there's a scene on the left with some traffic. We remove the traffic and start generating new scenes, and you can see a whole diversity of situations get generated with various vehicles in reasonable places, in some cases even doing U-turns or being stopped or moving, making left turns, and so on and so on. Right, so we can generate a very reasonable diversity of initial conditions. And you can study this and more quantitatively. So one of the things you can plot is, if you look at the green dots, this is the ground truth dimensions of agents that we had in our test set. And in blue, we show the dimensions of the agents our model generated. And you can see that the coverage between the two is reasonably good. And also there are these nice clusters implicitly merging where it learns the dimensions of cyclists, pedestrians, and cars. And you can go even further and create a metric for unconditional scene generation. And these are based on the Waymo open dataset sim agent challenge, which just concluded last week and was presented yesterday, where we mostly test the motion of the agents, but you can adapt some of the same metric to scene generation. Essentially, you're doing distributional comparison on the realism of the scenes across certain attributes. And in this case, you can average all the properties per scene, not per agent, and compare as it's done there. It's a slightly more diffuse distribution metric, but captures still significant amount of realism that is relevant, time to collision, how far agents are from edges, and so on, how often they're collided, and other things. And then the findings is, when we run these metrics, is they're very intuitive. So if we add the hard constraints, there's significant increases in realism. And also just doing a larger model without the hard constraint, also there's significant increases in realism according to these distributional metrics. And the log is the best possible you can have. This is the log itself scoring against the distributional histogram metrics we have. So it's actually, these are quite reasonable numbers. And this is maybe model scaling chart. I'm not going to go into too much detail, but larger models and models with more temporal context do better, as you would expect. So this task has very good scaling properties, even in the Waymo open motion data set, which is nice. Now, some of the nice things you can do with diffusion, which make it relevant to simulation, is controllability. So one of the things that you can do is you can specify constraints on this scene tensor. And these constraints can come in a nice protocol buffer form where you can say, hey, I want this actually, say, bicyclists to cut in front of us, right, in certain way. So if you know how to specify your constraint, the diffusion process generates the rest of the interaction, and you can generate things like push agents to do cut-ins or potentially tailgate other agents and so on. So you can add this to this tensor. So you can create interesting scenarios that maybe if you sample agent's ID, you will not get. And what also is interesting is you can go one more step and experiment with even more, I would say, language-derived notions of controllability. So if you have the right-hand side here the same, but now we give state-of-the-art LLM a prompt of examples of, well, traffic patterns and constraints. It can be zero-shot predicting pretty reasonable constraints actually for our scenes. So you can just then prompt LLM with language with these prompts and get behaviors like this. So you can say, hey, generate for this agent, I think on the side of us, an S-shape behavior. And you can see it makes an S-shape, and this is LLM provides constraints for that. Or here you can say, hey, generate surrounding traffic around our red car here that drives on all sides throughout this intersection as we turn. And it can, in many cases, it succeeds, and then occasionally it does not succeed, but it's already pretty great that you can get such nice cases from just language prompts. So that's what I wanted to say about scene generation. Now let's move on to motion generation, right? And we have past work, and also this work confirms it too. So if you want to do motion generation in open loop setting, like behavior prediction style, and you test it on some of the metrics we have, diffusion is competitive to state-of-the-art. However, efficiency lags behind autoregressive decoder methods like MotionLM. And also, what we found is that as we switch more and more to closed loop behavior with very tight, maybe 10 hertz frequency, then a closed loop behavior can significantly degrade performance in this model. And I think you can see this here. So you can see our model, scene diffuser in open loop. That's actually a great score. This is a composite score for our SimAgents challenge. A larger model is even better. That's all great. But the very same model run at 10 hertz at iterative fashion. So you still plan 8 seconds ahead. You move up, take a motion, you plan again, dream 8 seconds ahead, and you do a motion. The realism of those autoregressive outputs falls significantly. And of course, it's also expensive to evaluate because now you have, you know, 80 times you need to, for 8 seconds at 10 hertz, you have 80 iterations, you have 16 diffusion steps. That's a lot of optimization to get this result, right? And so we want to improve this. And in the paper, we propose a solution, which is called amortized diffusion. And this is inspired by an archive paper called PEDI below. And the idea is like this. First, we warm up the model. You start with the initial position, and then you have increasing noise into the future. Every next particle there is for the same agent, some more future timestamp. And so the way this works is, so then this noise, we run one denoising step, which decreases the noise of the process for this agent. And then we pop the pose. At current time, we append the next pose also with significant noise, and we just iterate between every step. Essentially, denoising decreases noise, but it's noise that is modulated, increasing into the future. And then as you append new scenes, this way they have a lot of the past context and continual state available for future steps. So it looks a bit like this. So this is an animation of this process in action. So you see when it starts in the top right, there's a lot of noise. And then over time, as we run this process, the noise iteratively decreases. And in the end, we generate the full closed loop trajectory, the diffusion process. And a few things to point out. So, future steps have larger noise, as described on top. And then we do denoising as we go, one step at a time. And as we pop things off from this stack, once we've popped all of them, the traverse steps are fully denoised to get your trajectory. And this significantly closes the gap in closed loop performance for the diffusion model, which is very cool. So it still doesn't match open loop. I think that's actually not necessarily even reasonable to expect, but we close the gap and significantly improve on naive autoregressive application of this diffusion model, which is very cool. And the last point is bottom right corner. It's a lot cheaper. So now we saved a ton of diffusion iterations because we just do one per step. And this is some big matrix of results compared to state of the art. Now I'll show, this is our new models. So two things. One is if you run in open loop, so generate all 8 seconds, then it looks competitive to most methods there. And if we run our amortized version, I would say it still does not quite reach state of the art. But this is the main metric. This is the composite metric, what I'm pointing to, right? Like state of the art. So these are diffusion methods. And they're all open loop. So we're best in open loop. And we are competitive to state of the art in closed loops, which is also pretty good. And here's some scenes. For those of you far away, you won't see, but there is different futures being generated in complex scenes and populated and so on. And maybe a little bit of a zoom in, you can see some diverse outcomes through sampling through our model. So if you look at this guy, in the first case, it never turns right. I think it lets everyone pass, very conservative. In the second case, 2 cars pass it, and then it finds a gap and goes. In the third case, lets even the third car that's a bit aggressive go before it merges in. So you can generate all kinds of interesting scenarios. And that's what I wanted to say about our traffic simulation work. Now, one more topic, I think that underscores maybe my choice of diffusion as a modeling approach for simulation is let's look at modeling rare agent behaviors. And right, so here I'll describe something that I call agent long-tail realism. So the models I showed you aim to capture all modes of the distribution, and they reproduce well realistic common behaviors of human users. But it's not clear if they will still capture the tails of the distribution, because that distribution may not appear at all or may not appear much in the training examples. And the distributional metrics may not be sufficiently sensitive to catch that. And so that's a bit of an important limitation because you want to actually simulate long-tail behavior. It's crucial to realizing the full potential. And it's exactly the rare events like collision and conflict situations with others that give rise to collision that we want to be able to simulate the most. And for those, we have the least data. Right? And so there's a concept here I've drawn. It's actually Shimon Weizen, a lead from Oxford on our research team. He popularized it. It's called the donut. So imagine this blue area shows you there's a 2D Gaussian on top, and in the middle is the most common examples. And then you go to the side, you get more and more tail examples. And the middle is the common stuff. And well, you can learn reasonably well to deal with it because you have a lot of that data. And you can also learn reasonably well to test it because you have a lot of data. Now you want to move to the rare, unusual cases. And so there is some kind of area there in between where you have realistic conflict behaviors that you need to model that are rare and still important, but not so rare you don't know anything about them, or at least you don't want to go in the area where you have no data. There you don't even have much chance to learn to simulate, right? So like, how do we cover this donut and how do we make it as wide as possible to test the things we want? And one of the things that we can do is we can build a sim agent model that is controllable via a set of inference time constraints beyond the ones I showed you before. Right, and diffusion model is very well suited for this. And these are constraints that allow modeling of conflict scenarios, right? And how do you model? What are the things in conflict scenario we did not talk about yet? There are things like this: reaction constraints. How long does it take, or it may take certain agents to react, or dynamic constraints. What are physical limitations on their acceleration and turning? All right. So what we want to ensure, right, is that if we have valuable situations close to the log, we want to replay them, yet allow the agents to deviate some, but subject to constraints, right? And then check what happens. And one other interesting phenomenon that I'll mention is hot starting. So hot starting is the idea that you can hold part of the agent behavior in the diffusion process fixed for some time. So let's say we start with the scenario where we had a real collision, and I want to replay this collision. And I have the option for the agent participating in the collision to hold the pose as the situation that generated it, or at least prototyped it for a long time, right? And after a certain amount of iterations, I unlock it and allow the diffusion process still to change things, right? Subject to whatever realism it learned, right? But then what happens is, for a while, if I unlock the process far enough and let the model change the path in the future, most of the time you don't have collisions. So it will deviate from what you saw, and AD will be high, collision will be low. It will avoid it because a lot of the time the agents can learn to avoid collisions. The more I dial and make it the hot starting step to later, the more I push this collision that I expected to happen to actually happen. And so there's interesting trade-off, right? Like you replay this law closer and closer, causing the collision more and more. At some point, it's even unrealistic, though, to replay closer and closer, depending on your actions. So there's some continuum here, and there's some reasonable point to pick if you're studying this. And in the case of reactions, one thing you can think about is you have an agent, and we have a time t, which you can determine either by manually, automatically, which is the first time this reacting agent observes something you do that causes a conflict. And then you can model a certain amount of time where this agent takes to react. And in this time, you still keep the trajectory as it maybe was seen before. And then from here on, you have the reaction, and here you can choose to hot start additionally. So this is the process that allows you to create a lot more collisions and slide along this step, along this continuum of reproducing things in logs versus unlocking just general distribution realism. And so what we can do is ensure that these reactions are dynamically feasible. And that's done with constraints on accelerations, lateral and longitudinal, with a set of polynomial convex dynamics constraints. Convex dynamic constraints, they're not polynomial. What happens, though, is this is an example of the model running. So typically, it predicts the poses, and you can recover accelerations through some polynomial interpolation. But then, as you see, as the model evolves over time, more and more of the states fall inside this convex region of allowed physics or accelerations, and results in realistic responses in the way generated. And then you can generate tailgater collision like this. So if we decide to brake and there's an agent behind us, we can model a reasonable distribution of response time and a reasonable set of behavior subject to those and estimate how dangerous such potential braking can be, right? And that shows you how diffusion can be leveraged further vis-a-vis constraints to push more into this donut of realistic conflict behaviors that are otherwise still not that common in the data. And so I think this will conclude my talk. Sorry, I even took a bit longer, but I presented some of our recent work on machine learning for realistic and efficient simulation and covered some topics: sensor simulation with 3D Gaussian splats, traffic simulation with diffusion models, inference time constraints to model realistic conflict between agents. And of course, one can further push here and combine a lot of these works into yet more compelling coherent whole, which is subject of future work for all of us. But I hope you found something interesting in this talk. A lot of the work we did, you can do yourselves using the Waymo open dataset, which we have released, has perception and behavior data that allows you to do such research. It also helps power some of our research. And you guys should be aware this resource exists. Please check it out if you're interested in similar topics. And we even have challenges that, especially the last one here, they just concluded this year. You can go check out the results and what people did for the various tasks. There's an interesting task here on simulated agents and even maybe 3D semantic segmentation. They can be related to some of the things I showed you in this talk. So suggest to check out this too. Thank you for the attention. I think more resources here if you want to learn more. Generally, I think it's really exciting time to be in the AV space, and some people would call also embodied AI space. I think there is maybe one of the best time to join Waymo and help explore a lot of the concepts for us, either both problems, both the onboard, learn as much as possible from your data to have a good driver, and the offboard, learn as much as possible from your data to have the best simulator, right? So we're exploring all of these. And if you want to come join us on this adventure, please either reach out if you have good, solid work in the space. We're looking and hiring in all these areas. And of course, please come to the Waymo booth to meet a lot more people in the next coming 3 days, starting tomorrow. Thank you for the attention.
Thank you very much. I think we have, or we'll just take time for a couple of questions, I would say.
Yeah, hi.
So I have a question mostly with regards to the agent behavior generation and scene scenario generation. A lot of examples shown in your slides and all of the previous presenter slides are centered around basically vehicles and road graphs and etc. But I have a feeling that this kind of technology can be more generalized for generalized robotics, right?
Yes.
And I wonder, like, for example, if we're talking about like pedestrians, which they follow a lot less of the road graph structure, and you know, in a lot of different kinds of settings, indoors or outdoors, how well this adapts and how useful that is in those kinds of things.
So maybe one thing I would point out is indeed the pedestrians don't often comply with the road graph quite as much as vehicles, right? But the models actually are able to capture that. I think as generic models, they should be suitable for similar tasks, including indoor scene modeling and so on, with some modifications. I think one needs to think exactly what the inputs are that power all these models more carefully, but otherwise the technology is reasonably generic. And maybe the outputs need to be richer. I mean, there's a world in which you want to go beyond boxes into a full skeleton and so on, but then you need the data to power it as well. So given the current public resources, right, this is easier, even though we even have published key points for pedestrians in the open data set. If you want to study that, we have them over time for a bunch of pedestrians, and there's potential to study that too.
It's just a tag-along question. For those papers and those results, are there any of those that are evaluated most on, you know, pedestrian data, like for example, for Waymo open data sets?
So Waymo open data set has a lot of pedestrians, and a lot of our metrics average performance across different types of agents, which can include pedestrians. Even though I would say it's still the most common object in autonomous driving data set is vehicles. That can break if you go to San Francisco after a baseball game, then it switches.
Maybe we can have one or two more questions while we already changed the setup, so we have some time for that. Is that okay for you?
I'm happy to answer a question as long as you guys have the organizers think there's time.
You mind if we plug you?
Yeah, you can. Okay, thank you.
But you can still answer a couple of questions while we set up.
Any more questions?
In this case, the collision is accuracy in real world to help you to generate that, or it's just simply extend from the original model.
Sorry, can you repeat one more time? Sure.
Yeah, it's like in your collision generation, consider real world collision trajectories for you to help generate this structure.
No, you can just generate virtual trajectories, collisions in more straightforward ways. You can start doing different behaviors in the simulator with log agents, which when you're in different positions will just create a bunch of collisions.
Yeah, yeah.
So it's not that hard to create collision, depending on constraints and pre-generated close to collisions, and then you can worry how to do good planning to resolve them. There's many ways to produce candidates. Yeah.
Thank you.
Okay, thank you very much.
Thank you very much.
Just stand next to it.
Yep, thank you very much, Drago. Next, I have the pleasure to introduce Alexander Petiushko, who is Director and Head of Machine Learning at Nuro and Professor at Sofia University. Thank you very much for joining us.
Hey, colleagues. Thanks to organizing for inviting me. It's really a pleasure for me for being here with the brightest minds of both industry and academia. My name is Alex. I'm representing research at Nuro, and today I'm going to talk a little bit about how to bring two worlds together and what are these worlds I'm going to talk about. First, let's have a couple of slides of advertisement. Sorry, I need to do it. Yeah, first of all, Nuro is the company that was founded in 2016, and it's literally the main mission of it is just to better everyday life through robotics. And when you're talking about robotics, I would say this is the easiest path towards robotics is through the autonomous driving as a narrow and very well-defined domain. And this is something aligned with Alex Kendall's yesterday's talk on WAD workshop. So I don't think that we are unique here. Currently, Nuro has self-driving deliveries in California and Texas. And this is one of few companies who is doing and targeting L4 based autonomous driving through the self-driving delivery. Okay. Yeah. Nice. This is the last advertisement slide. Basically, what we have our custom sense and compute engine. Everything is powered by the Nuro driver. I think, again, here we are not unique. Literally every company has its own XXS driver. What's important that we have our custom electric and zero occupant vehicle, and we're trying to push forward the self-driving delivery on the real roads. Yeah, when I'm talking about research, the team is the most important. So I would like to thank our contributors, Jonathan, Kashiar, and Junhong, and especially our former contributors, Wei, Ishan, Vladislav, and Ashwin. Thank you, guys. Let's switch to the real content of today's talk. Yeah, I would like to talk today about open loop versus closed loop. And we already have had a lot of talks about the metrics, about how difficult to transfer the open loop model to the closed loop. Literally, different techniques can be used for either for closed loop or open loop. And let's think how we can do it and how we are doing inside Nuro, how we're bringing these two worlds. Yeah, the talk is not going to be about LLM, but yeah, I was thinking before the workshop that literally everybody would talk about LLM, but this is not the case. But anyway, although LLM is quite nicely fit into this whole framework that I'm going to talk today. But anyway, let's start with the first so-called open loop world, where the king is imitation learning. It's quite exciting that even more than 35 years ago, it was a very interesting and important approach, which is called ELLEN from Carnegie Mellon University from 1988. You can see to the left the rough architecture, basically detailed architecture of the approach. So they used both RGB and range sources through the very shallow neural network. And what is important that they can literally and accurately drive the ego vehicle at a speed of ½ meter per second along a 400-meter path through a wooded area under sunny fall conditions. And we are pretending, we are thinking that we are, as a state-of-the-art guys, we are doing a lot of cool research. But look, it was done more than 35 years ago. Simple behavior cloning, it was already working. Sure, a lot of constraints, a lot of auto-distribution cases, but anyway. Right now, we have a lot of imitation learning-based approaches. We can talk even about the prediction-based models, and currently one of the state-of-the-art prediction models is motion transformer, or MTR, MTR++, from the latest years. And you can see it's quite complex in comparison to what had been done 35 years ago. Very complicated encoder, transformer-based decoder, etc., etc. It provides very good results in Waymo open motion dataset. Yeah, it's sort of state-of-the-art. Why imitation learning is the key, at least for open loop? Because it's very, very simple and constructive algorithm. It's basically supervised learning. We are trying to copy-paste the distribution and in a quite simple way, with simple losses. And it scales with the data, but it's not ideal. And why? Just because it's very hard to stay in distribution, because if we have anything a little bit out of our training data, then error starts to accumulate, and we can ruin the whole thing. It could lead to some collisions, it could lead to off-road situation, etc. Could be very, very unsafe. Yes, there are a lot of ways to mitigate it. For example, so-called dataset aggregation approach, or DAGR. yeah, this is the example. So if you have some deviation from the expert trajectory, error accumulates and you have low collision rate, which is not 0. But you can, for example, redrive some specific failures and add to the data set and retrain the model, and vice versa, vice versa, vice versa. And doing one more time, one more time, and one more time. It's working, it's costly, and it's not scalable. At the same time, we have the other worlds, a closed loop world, where one of the leading approaches is closed loop reasoning, for example, reinforcement learning. And here we can see the famous work of Alex Kendall from Wave. It's online of policy RL PG from 2018. So we have the input, we encoding the state, we have the policy, then we feed it into the Q value, and then we have the reward here. So very simple approach. Yeah, it's not that simple, but that quite doable from the point of view of reinforcement learning. Yes, and why reinforcement learning is good, especially for closed loop, it's really adaptable to unseen scenarios in comparison to any imitation learning, behavior cloning based methods. And this is the real reasoning beyond imitation. We can think about, like, we can do some hypothetical rollouts and then finding out the best trajectory source that is safe, that is not so conservative, and let's do it. But again, this is not ideal approach because one of the hardest things here is how to shape rewards. For example, we could have a lot of heuristic and human-defined rewards, like let's avoid collisions, let's avoid, I don't know, curb collisions, vehicles collisions, let's be physically plausible, kinematically plausible, etc., etc. But basically what we would like to have, we would like to have human-like behavior. And it's very vague definition. So the second drawback here is that in order to really train a good RL model, you need really reliable infrastructure for reliable estimation and scale. That's costing a lot. So let's switch to the probably for today's main topic, how to combine imitation learning and reinforcement learning. So current status quo is that we have a lot of different imitation-based models, either for prediction or for planning or even for both of them. And these models can be of the very different nature. They can be ML-based, they can be heuristic-based, for example, heuristic planners. It could be even some simple geometric rollouts for covering the recall, basically. We can even use LLM-based for high-level reasoning, for some long-tail situations, etc. And the RL policies need to deal with either discretization of the action space or the approximation policy gradients. What if the equation arises? So we can reuse the imitation-based approaches that we already have. Like they could be publicly achievable, obtainable. They could be some like in-house models, but anyway, we have a lot of them. And also we can combine it with the reinforcement learning-based algorithm to select from multiple generators of imitation learning-based generators. So by doing this, we can concentrate on safety because we can do hypothetical rollouts and we can either remove or, for example, downvote the dangerous and non-safe plans. And at the same time, we can provide the behavior realism because this is where imitation-based models are really good. They're very, very well aligned with the human driver. And yeah, let me present our the core approach. This is called SimRL, combining imitation and reinforcement learning. Yeah, we are not so good at naming. This is the best that we've come, but anyway. So suppose we have different imitation based, or not only imitation based, different trajectory generators. They can be of different nature. For example, some planners. It can be some prediction models like MTR or some behavior cloning. There can be some even reinforcement learning based like software vector critic. We can even have here like LLM or heuristic planners. And what is even more important, so this is also applicable to different trajectories outputs from the single model. For example, imitation learning based approach can provide like 10 trajectories or 1,000 trajectories with different internal scoring, but we are not usually rely on them too much because it's still open loop based rollouts. Yeah, and you have, we can see here like the intersection, and the ego vehicle is the light blue one, is going to turn right, and we have two agents. They are going quite slow, but anyway, they're still going from the left to right, and there is a potential school bus, as you can see here. And what does SimRL? It uses, as it's called, safe RL approach, and we'll talk about it a little bit later. So it takes some sort of hypothetical rollouts for timestamp T2, which is even more far horizon in comparison to T1. Yes, and we can see here that actually we could have three different situations. One situation as we are super conservative and we have unnecessary yield, this is at the top, or we can be too aggressive and it could lead to a potential collision at the bottom one because we have the school bus. The dark blue agent is stopping and our ego agent is not able to do the braking in the correct way. But somewhere in between, we could have the not conservative and not too aggressive, a very good behavior. The score is we have here the highest score, so let's choose it. Yeah, and this is the outcome of the algorithm from the very high level point of view. Scoring itself is also not so how to say trivial thing for, because we are going to rely on the scoring of this SimRL algorithm. So again, this is sort of combination the second time. A combination of continuous action space and discrete action space. So for continuous, we are able to provide the scoring for literally any planned trajectory. So we are not constrained on any discretization, basically. But when talking about why we are also combining discrete action space, so we are able to provide the correct probability distribution on top of any finite set of trajectory. Sorry. So yeah, like very simple illustration of continuous RL. So actually the action is the input to the Q function. Discrete approach where vice versa, how to say, we have Q value and the policy are quite independent of each other, and the action is the output of them. And what we are doing, sort of unique and approach something in between. So action, because they are provided for us by some external planners, and they are literally the input to both policy and Q value. So this is how we take the best of two worlds, continuous and discrete reinforcement learning. Advantages, probably here I'm just going to talk one more time about. So scalability, so we can use the benefits of a lot of data that comes along with the imitation learning based methods. That's no objection here. At the same time, we have flexibility because we can use the SimRL approach as a sort of framework that can literally incorporate any imitation learning based planner, any prediction model also as a sort of for prediction for other agents or even for incorporating as a one more additional planner here. And also, I'm not going to show on these slides, but we have approach how to incorporate scores from the models of like of these planners of different prediction models. So we can also use some sort of knowledge from these external trajectory generators as well. So, but what is about why it's safe RL, how it's important, how it is done inside our framework. So basically, it is based on the approach which is called recovery RL. So this is illustration from the original paper, you can consult it. So we have a state, we are sampling the query from the task policy, and we need to evaluate it. So using the specific Q function for the risk. And if it is less or equal than some risk threshold, then everything is nice, we are safe, we are executing the task policy. Otherwise, we are executing some recovery policy or failback policy or contingency policy, doesn't matter how to call it. Yeah, and it could be quite conservative, to be honest. Yeah, and this is the whole overall of the recovery RL. But for when we're talking about real use cases, usually we don't have a single risk. We have multiple risks. For example, it could be vehicle-vehicle collision, it could be vehicle-road collision, it could be some other things, even with different weighting factors. How are we going to deal with multiple streams of risks? So suppose these different actions, basically different trajectories from different trajectory sources. So yeah, and we have, like here, we would have 3 different risks. So let's compare with the thresholds, and we can see that the 4th and the 5th trajectory are not so good. Let's do the same for the 2nd stream of the risk. Only the 5th is bad. And the 3rd risk here, again, like the 5th trajectory is bad. So yeah, that's nice. There still exists some safe actions. Actually, in these cases, A1, A2, and A3, like 3 trajectories, probably like from heuristic planners. And the imitation-based ML-driven solution is not so good here. So what we are doing, we are renormalizing the task policy and sampling from this top stream. But at the same time, it could be some bad cases. For example, for the first risk, we need to remove A2, A4, and A5. For the second risk stream, we need to remove A1, A2, and A5. And for the third one, we need to remove A3 and A5. So in combination, we basically need to reject all the actions. In this case, what we're going to do, we're going to use the recovery of failback policy here. Yeah, and let's test it in the closed loop, because it was our initial goal. And here, big kudos to Waymo team. We tried it to do with Waymax. Sorry, colleagues from other institutions and companies. We're also going to do it, but probably a little bit later. Why Waymax is quite important? Because it can be used for training. And basically, our SimRL is some model is used for training. It's data-driven. It has Waymo open dataset under the hood, and it has TPU and GPU support with JAX. So what we tried? We tried initially, let's use without this additional layer of RL on top of trajectory predictors. So let's try MTR. And with 2 different, slight different approaches. So we're just using top 1 trajectory or just sample from this trajectory, because every trajectory comes with underlying probability. Not all the metrics here we just visualizing, only log AD, collision rate, and off-road rate, because for kinematic feasibility, it's pretty meaningless when we're talking about prediction models. And route progress ratio, we don't have the access to route info, SDC path. Hopefully, we could have it in the near future. But right now, we do not have it. And we can see here that for MTR, doesn't matter which approach we are using, it's quite bad. All the top 1 is a little bit better than the sampling. And it means that MTR provides meaningless probabilities. And here is the illustration why just incorporating the open loop model in the closed loop is not the best idea. This is visualizations from Waymax. So you can see here to the left and to the right, we have the collision. So the blue one is the ego vehicle, and when it turns red, we have the collision. So it looks like it's copy-pasting the behavior, like expert behavior distribution, but still having some problems with interactivity. Okay, let's try SimRL here. And you can see here that in terms of log AD improvement is huge. Also quite significant improvement in terms of collision rate and off-road rate. So it's nice. But also we have for the original Waymax paper, we have waveformer. So we can compare. And it seems even waveform is a little bit worse for log AD, but it's better for collision rate and off-road rate. But again, there is an excuse. Wayformer has access to road info, and we do not have. And we are working, I hope, of getting this road info, so we could update the whole results. Yeah, this is the results of simulation for using VMX. Yeah, but we also have, I guess every self-driving company has a lot of in-house data. It has also in-house simulator and a lot of tools around it. So let's try it internally. Actually, we did initially internally and then tried VMX, but for the sake of brevity, let's have it at the second step here. Okay. So for in-house data, we have some challenging interactive in-house scenes where log pose divergence is usually inevitable. What does it mean? So usually we have the expert driving log, some trajectory that has been used on the road, but at the same time, when we have real interactivity, and just slight differences in the simulated agents, like ego vehicle, could lead to some big divergences in terms of ADE, etc., etc. So in this case, route progress ratio makes sense because we know where we are going to eventually land our vehicle, but log AD doesn't. So here, two main metrics are collision rate and progress rate. And initially, we just tried behavior cloning or some simple imitation learning based approach. And then applied SimRL that is also only trying to, scoring on top of behavior cloning based approach. And so we can see it decreased collision rate and increased the progress rate. But usually in-house, people have also the heuristic planners target towards specific scenes or use cases or DD domains, etc. So, and we can even try on top of both companion on top of behavior cloning or imitation learning based approaches and heuristic planners. And it can also increase the progress rate significantly. It's a little bit worse in terms of collision rate, but it's still better than behavior cloning. And I would say this slight difference is because some collisions can be a little bit unrealistic. But anyway. Yeah, and a couple of visualizations here. This is using our internal visualization tool. So you can see here, yes. Unfortunately, you cannot see that we have a lot of different plans initially proposed for the system, and SimRL just trying to continuously select either heuristic, for example, imitation learning based. Even talking about imitation, it has like a lot of different imitation based proposals. But what it does, so even without specific rules or specific rewards that are going to, okay, you need to wait before this clear zone, keep clear zone. But anyway, it waits and then goes faster. So it's a very reasonable approach. This is also additional example where the model shows how it can creep in the reasonable way. So we have a two-way intersection. We have a lot of congested traffic from the right to left and from the left to right, but we need to go straight. And we are trying, I'm not sure whether it can be seen here. We are creeping, and when it is safe, we go forward. And basically a lot of plan changing from time to time, and it really works. And what is much more important is not simulation, it is the on-road implementation. But the method is not ideal for sure. Why? First of all, reward. We still have some rewards. And reward definition is not that straightforward, but I would say mitigatable. And saying mitigatable, I would refer to the human feedback and learning rewards on top of this human feedback. For example, we can even turn it to the supervised domain by using DPO or similar approaches. Second is we have rare sparse events, and they are challenging to learn. For example, collisions. Yeah, colleagues already proposed today some ways how to do it. I still think it's a problem right now. And especially when we have advanced planners would try to avoid collision as much as possible. So it's sort of a trade-off between super nice planner, which avoids any collision, but we would like to train our model for the collision to be able to reason at least in terms of collision. And simple and efficient, any reinforcement learning-based approach is simple and inefficient, unfortunately. It takes many simulation steps to learn. And yeah, depending on the quality of the line generator. And for conclusions, okay. So first of all, and this is the main goal of my talk, is just to emphasize that CMRL is a really scalable and flexible framework of combining any approaches that you can see in the public domain or internally. Learning selection, this is something that can be a bridge between the two worlds, this closed loop and open loop domains. And unfortunately, there is no such a thing as too much safety. And this is one of the main and like major considerations inside Nuro, how to be as safe as possible. And join our research. And we have open positions, and these open positions are especially about research for the safety, for robustness, for uncertainty, and such similar things. Thanks for listening. Thank you for attention.
Yeah, I think we can take some time for a couple of questions.
It looks like there's quite a bit of collision in the final metrics of 80%. I think those are challenging to see at the end. Which is not surprising, but like any comments on how to trade off the collision rate and rate like route progress? Because I think that's it's this circular kind of thing that your reward function design choice impacts this, and then how you think about these things impacts your reward function design choice.
Yeah, I think it should depend on, for example, on some sort of external thing, like we can understand which is ODD, how this ODD is, for example, either interactive or like safety critical. If it's for example, we could have some sort of interactivity classifier, we could see some sort of potential criticality classifier, and if it could be too critical, probably we can choose more conservative way of thinking here. So yeah, so trade-off is inevitable, and you can, I would say, being too conservative, you will never go through the congested road, but sometimes probably it's needed. You need to be able to reason about it.
Any more questions? I think everyone wants to go to lunch.
Thank you.
Thank you very much. You're turning for lunch, right?
It works.
I,
If I
I have just problems with my internet. Now we can test it.
Yeah, if I speak now, can you hear me? La 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 la. Da, 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 da. Let's see if I have the right settings here. Now let's see screen sharing. Where am I? So microphone seems to be saying microphone. Hello. Yeah, it's giving me a little green thing here. So it seems like it looks like. I'm not sure if no, still you can't. You're not getting any audio from me, are you?
Yeah, I don't know if I'm doing something wrong.
Could be also sometimes.
Oh, audio is working.
Is it working?
Set, yeah.
Okay. Very good. Someone is confirming online that it's working. Yeah, okay, that's great. Thank you, person online. Thank you, and I hope the audience online can hear me as well. Very good. Yeah, it's a pleasure to be here. And like you said, I feel like I am here sort of a little bit like a slightly different person from you guys. I'm not a machine learning or computer vision researcher as such. So I come at this challenge of modeling human road user behavior in a slightly different way. In relation to these things I'm mentioning on the slide here, the behavioral phenomena and cognitive mechanisms. But overall, we sort of have the same goal at a high level. It's all about trying to make models that describe the behavior of these kinds of guys, right? But we do it with slightly different emphasis. So it's sort of interesting when I read papers more from this kind of community. It's very clear what counts as a success in your field, right? It's the bold font in table 1. Yeah, that's always what matters, isn't it? There's almost always a table 1, and almost always the bold font is towards the bottom, showing that this new proposed approach is better than what existed before. And I think that's really cool. It's not something we do in my area, really, most often. But it's nice that it sort of shows that progress has been made, a new paper can be published. And that's great. But it doesn't answer, there are some sort of important questions that it doesn't answer, right? So it doesn't tell you whether this is realistic enough. When is it good enough? And I think that's a pretty important question that perhaps you guys might want to start asking yourselves, because I think increasingly, for example, like the people like regulators who want to regulate automated vehicles, if we tell them that, or if an automated vehicle developer tells them that we know our vehicle is safe because we've tested it in simulation, they're sort of getting clued up to the fact that it should be asking this kind of question. How do you know that your simulation is good enough to make those claims? So I'll talk a bit about that today, and I'll also talk about my kind of perspective on this and how this type of psychology, human factors perspective with these sorts of things, with behavioral phenomena and cognitive mechanisms, might be useful. So hopefully you'll find that a little bit interesting, something slightly different from how you think about these things normally, and maybe there's something useful you can take away from it. That would be my hope. Okay, so but what do I mean then when I say something like behavioral phenomena? What I mean is something like this, that in some subspace of all possible traffic situations, human behavior follows some kind of pattern. So that could be very simple. It could be that in some type of situation described by this subspace, behavior is always pretty much the same. Everyone does the same thing. Or it could be something more variable, where as the situation changes, behavior changes in some predictable way. So for us in our field, it's more about finding these kinds of patterns and trying to understand them. What's behind them? So I'll give you some examples of types of phenomena that we've been looking at and that we've been trying to capture in models. And one of them is something you could call speed-dependent gap acceptance. And what do I mean by that? I mean that when human road users look at gaps in traffic, as a driver, cyclist, or pedestrian, there's a gap that you might fit through, but you're not sure. You get into a gap acceptance challenge, like for example, this pedestrian in our pedestrian simulator. And what you typically find then is this kind of sort of expected pattern, that when the time gap to the approaching car increases, the tendency to accept that gap goes up, right? So this is 2 different data sets. But somewhat more surprisingly, you also get the effect that the speed of the vehicle matters. So for a given time gap to the vehicle, if the vehicle is going at a faster speed, the tendency of the human to accept that gap actually increases, which is maybe a little bit counterintuitive. I mean, it would make sense, right? If the time gap is large enough, we should just cross. But somehow people factor in the speed, and people have been arguing that maybe it's because if you think about it, for a given time gap, if the speed is higher of the vehicle, it means that the car is further away. So maybe it's because we sort of heuristically make use of the distance cue in some way to figure out whether it's safe to cross. Ideally, if we can make an even simpler model in the kind of field where I work, we like that even better. If we can have some kind of mechanism that makes sense, that can explain the phenomenon we see. So my PhD student Kai Tian, he looked into visual looming as one such mechanism. What I mean by that is that if you have some kind of object, in this case, a car over there that is coming towards you at some speed, then on your retina, that object will be projected at a certain size. And as it comes closer, you can imagine this visual angle grows and quicker when it comes towards you. So that's called visual looming. It's been researched in psychology for ages. But what he found was that basically in each of these two data sets, if you, instead of measuring time gaps and speed, you just measure looming, these curves kind of collapse together. So you can just use looming to explain this phenomenon. So it seems like maybe people are speed dependent in their gap acceptance because they're making use of visual looming to decide about whether to cross. And why is this interesting to you guys? I think that one reason why it might be interesting is that ideally, if you're making models of human road user behavior to test automated vehicles, it could be argued that your models should be exhibiting these kinds of behaviors, right? So this has safety relevance. It means that when a vehicle is traveling at higher speeds, the probability that a pedestrian will make a risky, unwise road crossing decision increases. So ideally, if you want to measure safety of AVs with simulations, you'd want to make sure that your agent models have this kind of phenomenon in their repertoire. I'll cover a few more just to give you a bit of a wider idea. So one other would be urgency-dependent collision avoidance braking. There we've looked at data from naturalistic data sets like the SHARP2 data set, where they put loggers in thousands of vehicles to be able to observe some actual crashes. And then you see braking responses like this, some constant acceleration, a ramp up of deceleration, another kind of constant acceleration level when they're trying to avoid this crash, the humans. And if you look further into it, you'll see patterns like this with respect to the timing of when that braking starts, that if the criticality, the urgency of the situation is low enough, this is again a sort of visual looming based metric, then the response time can be quite long. But if the criticality is high enough, you get a quick response, and a quicker response, the more urgent the situation is. That is how humans respond to safety critical, really urgent, in this case, rear end situations. Similarly, this kind of ramp up of braking also is urgency dependent. The more urgent the situation is when people actually start braking, the more rapidly they will ramp up their braking. And to make a long story short, we were able to show that if you make a model that includes some mechanisms from cognitive science, like evidence accumulation, for example, you can sort of capture these behaviors in your models. Evidence accumulation means that so it's a theory of how we make decisions. It's suggesting that to make a decision, we accumulate over time little noisy bits of evidence. And when that evidence reaches some threshold, we make a decision. So if you have strong, clear evidence for some decision to brake, for example, you can make a quick decision. If you have more ambiguous information, it'll take a longer while. So you can use this kind of model to predict what kinds of decisions people will make, and importantly, in this kind of setting, how long time it will take them to make that decision. And again, I think it's important to consider, do models that we use in agent-based testing of automated vehicles, do they have these kinds of behaviors? Yeah, so this is just an example of what it looks like in practice. This is some actual braking from this SHARP2 data set, the black line here. In this case, this is a crash. The gray area here is the driver looking away, looking back, having an oh shit moment, and then actually crashing. In this case, you see this sort of negative bump and an acceleration. And then the blue stuff here is the model predictions, probabilistic model predictions that are sort of in line with the observed behavior. And finally, as a final example, if you think about more interactive scenarios, less safety critical, but important from a perspective of human satisfaction with automated vehicles, there's just loads of different phenomena, right? If you think about what humans do when they start interacting with each other, there's things like people speeding up to assert priority or exaggerating deceleration to tell someone else that they're wanting to yield to them. They start hesitating, even though objectively they might have enough space to cross the road, and so on and so forth. So what we did here was that we asked the question, basically, what kind of model do we need to be able to capture these kinds of phenomena, pulling in, again, theory from cognitive science, and perhaps not unexpectedly, we found that we need quite a lot of different theories. We didn't need a theory about the sort of visual sensory noise of humans, how that gets processed in some kind of Bayesian way in perception, concept of how people consider the value of their actions over a longer period of time, theory of mind about how humans understand the intentions of others and how that is affected by my own actions. And again, this kind of evidence accumulation I mentioned before. So if we do that, we can if we have a model which brings those things together, we can capture these various kinds of interaction phenomena. One way we tested it was in this kind of distributed simulation experiment that I'm showing here. So this is our motion-based driving simulator now connected to that pedestrian simulator. So these two participants can see each other in the virtual world and interact. And then we get behaviors like this. Again, this kind of as a function of the distance or the time gap to the car when they start interacting, the probability of the negotiation sort of working out in the way that the pedestrian goes first, goes up, and even more so if there's a zebra crossing with priority for the pedestrian. And interestingly then, if we took our model that was constrained just by us wanting it to reproduce those phenomena I mentioned without any further parameter fitting, it gave us something very similar back. So that can be one nice aspect of including sort of first principle mechanisms in your model, that sometimes you get some stuff for free, sort of. So yeah, so lots of different phenomena, right? And obviously, I'm just scraping the surface. Of course, as we all know, as road users, there's just so many different things we're up to, right? But what I've been trying to say here is that I think a quite open question in general, and one that it would be interesting to pursue further, and maybe you guys want to do that to some extent yourselves, is to what extent do current data-driven machine learning-based agent models actually exhibit these phenomena? We tend to focus on those kinds of high-level metrics of performance, those metrics that go ideally in bold font in table 1, right? But what's underneath? So we've done a little bit of this ourselves. We've sort of taken some machine learning models that were accessible to us and analyzed their behavior. We did it in the context of merging on highways, and we looked one phenomenon, for example, which is when two vehicles are merging, there's some kind of space sharing conflict at some earlier point in time. They're projected to collide if no one sort of adapts a little bit. So then if you look at, given those current speeds and positions, who has the lead and lag, and what you find is that there's a quite clear, I mean, people are good at adapting who goes first to that lead lag relationship. So if you're quite close in time to the merging location, that lead lag relationship predicts very clearly who goes first. So this very sort of steep sigmoid here tells you that the agent that is in the lead is going first. And if a bit further in advance of the merging time, it gets more fuzzy. There's some kind of negotiation happening in there. But what we see here, and the important point, is that the naturalistic data is this gray line you see behind, and the other lines are three different models. In this case, it's actually not really agent models. It was more like real-time prediction models, but it's the same kind of idea. So yeah, you see that they capture this behavior quite well. They were able to learn from the data set we're looking at that people were doing this. But when we looked at a slightly more nuanced behavior, you could say, something like courtesy lane changes, The sort of thing which might end up looking like this when you're merging was a highway vehicle that originally was kind of blocking you. There was maybe a space sharing conflict, but that guy was nice enough to change lane to let you in, right? So there, what we found was that we could see it clearly in the human data. So if you compare no space sharing conflict with a space sharing conflict, if the humans have enough time, you will see this kind of increase in the probability of a lane change happening. So humans were doing this kind of courtesy lane changing, but the 3 models we tested, they didn't really do that. And the key takeaway is maybe not about these specific phenomena, but the key takeaway, I think, is that that high-level model performance, that sort of summary metric, isn't really indicative of whether a certain phenomenon actually is captured by the model or not. So actually, this model here, which is perhaps the one where you could, if you squint a little bit, say that it's trying to do something along what we're seeing up here, even though it's kind of getting it wrong at the crucial point here. This one actually had the worst high-level performance. So the question is, do the models capture the bits that matter to humans, right? Yes. One way of maybe trying to make that happen, that maybe you guys want to think about it as well, is the possibility of combining some of these more machine learning based methods with some kind of mechanistic assumptions. So that's something we've started to do a little bit. We've done it from a reinforcement learning perspective, where we have that introduce these kinds of mechanistic assumptions about perceptual noise and perceptual filtering and looming aversion and so on. And what we found then, so this was again in a sort of pedestrian crossing situation we looked at in this case. We find these kinds of gap acceptance behaviors again. So this was now the human data. You see the initial time to arrival, the time gap of the car. If it's small, you see the CDF here of when people cross. If the time gap is small, people cross after the car, this vertical line. If the time gap is large, people cross before the car mostly. If it's in between, it's sort of a 50-50 kind of situation. But interestingly, so yeah, also in this data set, we have this speed effect, right? That for a higher speed, people tend to cross more often if the car has a higher speed. And if we take just the simplest possible MDP style reinforcement learning agent, it'll quickly figure out that actually even in this small time gap, it can cross before the car without getting hit. So it'll just cross straight away in all scenarios. But when we introduce these kinds of mechanistic assumptions in the model, lo and behold, it does something quite human-like. And we were sort of surprised to see that it actually does this speed-dependent gap acceptance, as you can see. It's a slightly different kind of assumption. It's not exactly the same as this visual looming assumption I mentioned before. It's related because the sort of noise properties we're using also are angular. But basically what this model result is suggesting is that maybe the reason why people are showing speed-dependent gap acceptance is because it's sort of boundedly optimal given the properties of our visual system. So yeah, by introducing some mechanisms in our machine learning models, maybe we can get some phenomena for free again. Okay, I've been talking about lots of phenomena, and I was saying that this is maybe important to you. We should look whether the models are human-like in these various ways. So why do I think it's important to capture these phenomena? And to make that argument, I think it's important to think about what we're trying to do. If we're making agent models to test automated vehicles or develop automated vehicles, what's the end goal of that, right? We want good automated vehicles, for example, in the sense of what's sometimes called the 3 goals of human factors engineering, which would be safety, efficiency, and satisfaction. So we want automated vehicles that are safe, create efficient traffic, and AVs that humans are satisfied with. We don't hate them. So yeah, so how do we achieve that, and in what situations does this fail with automated vehicles, perhaps? So one way of thinking about it could be like this. If we take an extremely high dimensional space of all the past and current world states, including some automated vehicle and some human, and we in good PowerPoint fashion simplify down to one single dimension, And on the other second dimension, we think about all the possible behavioral responses to those states, right? Then there'll be some kind of subspace in here of behavior that is feasible to a human, where the human can still kind of live to see another day. Whereas if the AV does something which expects a superhuman reaction time from the human, right, to avoid a collision, then this is not something that's feasible for the human. Ideally, humans would probably typically want to stay in an even tighter region in this space, the region of preferred human behavior, because when we're in there, that's when we get this interaction, which is satisfactory, efficient, and safe. But when we push the human a little bit outside these comfort zones, we can start to get an unsatisfactory interaction, an inefficient one, or maybe even an unsafe. So what we want to do is we want to make sure that our automated vehicles stay definitely inside the yellow area and ideally inside the green one. And how do we sort of tell the automated vehicles where these areas are? That's through modeling, right? We're modeling the human behavior. So one way of thinking about the goal of human modeling in the AV context is to promote this type of interaction success by delineating the feasible or preferred human behavioral envelopes. And it also gives us some help in thinking about, I was saying sort of, is it capturing the right things? Because if you take this perspective, you sort of realize that the more sensitive the interaction success is to variations in some aspect of human behavioral cognition, that's where you really need to focus your modeling efforts, right? If the difference between a crash or not is really dependent on one certain aspect of human behavior, but not the other ones, then you really want to get that aspect right in your models. Which then gets us back to this idea of phenomena, because sort of somewhat qualitatively, but anyway, I sort of think the argument works that the reason why we pick up on these behavioral phenomena that I've been mentioning, the reason they're salient to it is that it feels like they are important to interaction success in some way. So this is the kind of argument why I think it makes sense to look at behavioral phenomena and see whether the agent models we have reproduce them. But it sort of gets us into a challenging position in the sense that we need to make long lists of phenomena, right? Need to tick them all off, and we should maybe do that to some extent. I think it would be good to do more of that, but I also think it would be good to see if we can work towards more general ways of seeing whether our models are good enough. And I think one important part there is to think about model accuracy. So I don't know if you're familiar, but there are various approaches out there for trying to estimate the accuracy of the model predictions we're making. And the important point then is whether we can sort of use that to say something about the application, these interaction success outcomes that I was mentioning. So what I mean, just to make it a little bit clearer, is that if we have some kind of metric of how good an automated vehicle is that we can try to estimate in simulation, maybe the frequency of crashes, right? We would typically have some kind of region of that metric that we don't want to be in. We want crashes to be below some kind of threshold value. And then if we run a simulation, we get a value. We say, okay, our simulation tells us that we're below this threshold value of crashes. All good. We say that to the regulators. Our automated vehicle is safe. If the people you're giving that number to is sort of know their things, they should ask you back then, but how certain are you about that prediction, right? So then if this would come from having simulations where we don't only have some kind of unitary prediction of the behavior of the humans, but rather some kind of distribution, we could then feed that back into making the estimates of that interaction success metric. So maybe it looks like this, and this is all peachy, right? There's almost, there seems to be a very small risk that we're in this bad area of number of crashes, or maybe this is the human frustration metric or whatever. If we have that one, but maybe in another case, it turns out that actually there's a lot of uncertainty in our behavior models, which shifts the entire distribution so that this doesn't look so rosy anymore, right? So maybe here we need to either improve our automated vehicle or we need to improve our models to have more accurate predictions from them. Okay, that's what I wanted to cover. I've been talking on this topic of how do we know that our models are good enough, and the main point I want to make with respect to that is basically that I think that's an open question still, and it is an important one that we should work more on. And I've been sketching and hinting or suggesting that maybe some useful directions here is to think about behavioral phenomena and whether our models actually exhibit those. Model uncertainty is another interesting direction because it might allow us to estimate uncertainty in the sort of human factor success metrics. And another interesting direction, I think, is in this kinds of hybrid mechanistic and machine learned approaches. So yes, thanks so much for listening. Here are some of the key papers if you want to check further with lots of authors that worked on this stuff, of course, in addition to myself. Feel free to reach out if you have thoughts or questions, or otherwise, I think we can take some questions now.
Okay, I'll give you some time to think. I actually have a question.
Go ahead.
So if we have all these kinds of different metrics, do you think they're more useful for evaluation or also for training as an optimization target? Or if we were to do this, it would just be something that the model would learn to exploit, to fulfill without actually improving its performance?
It's a very good question. So by model, you mean like the AV policy or something like that?
Yeah, whatever you use to train.
Yeah. No, I think no, I think you're kind of answering the question a little bit. I think it would be interesting to consider using it for improving and optimizing the AV behavior itself. But of course, with any metric, it immediately becomes something you exploit, right? So it is challenging, and I think that we're only just scratching the surface about how people should make the argument that that their simulations are good enough is one part, but even just the question of how do the simulations, what are we getting from the simulations to answer the question about whether the AV automated vehicle is good enough. I think we're not at a clear answer to that even yet, right? Yeah.
Any other questions?
To what degree are there outliers in sort of your human experiments? Like, are there people that just aren't explained by, this looming stuff? And actually, should we optimize for some percentile of sort of regular human preferences or the average? Or how do you think about the variability in even different human judgment?
Yeah. So I think for the Zoom, I should repeat the question. Yeah?
Would be great.
So the question was how to think about whether are there, when we look at the behavior of humans in our experiments, are there outliers, and how do we think about that in relation to modeling and so on? And yes, definitely. I mean, it's always going to be the case when you work with humans that there's a variability to start with, and ideally, we try with these kinds of different models to capture that variability as well as we can, but there's always going to be weird stuff happening. so that does make sense. I think that'll we'll have to content ourselves with doing our best for capturing as much as the variability as possible. But yeah, that's definitely a concern. Yeah.
Okay, then thank you very much.
Thank you.
And the
voice. Okay, no.
All right.
Sorry about that.
No worries. So yeah, in this work, we are concerned with the problem of taking our boring collected autonomous driving data and trying to turn it into something interesting, where we can change our own position and change the position of the other actors to create this sort of safety critical scenarios that we really care about. So when we sat down and created NeuRad, we started to list the requirements we had. Of course, we want state-of-the-art image rendering quality, but we also want to be able to render LiDAR with a high quality. We need some anti-aliased representation to handle these huge scenes we have in autonomous driving. And we also want to be able to handle these surround cameras in autonomous driving. Of course, we need to deal with the dynamic actors, but most of all, we have to be able to change the way they behave in the scene. And last but not least, we want this method to be robust across data sets. We don't want to impose too many assumptions about the data. And we want to be open source, because neural rendering itself is kind of cool, but it's kind of useless if you don't use it for anything. So there are a bunch of great works out there. But when we look at this requirements list, unfortunately, none of them really ticked all of the boxes. So that's why we created NeuRad. I guess I should mention, this might be a requirement list, but our wish list, we don't really tick all the boxes yet, but we hope to address that in the future work. So how does this work? Well, we have this classic nerve setup. We collect some data, images and LiDAR data. We learn some scene representation, and then we hope that we can render new views from that, where we change our own position or the position of other actors. To learn that, we shoot camera rays and LiDAR rays through space, and we sample points and ask a neural feature field about different features there. I won't have time to go into details, come to the poster and ask about it, but you can think of it like instant NGP with some handling of dynamic objects that move rigidly. This will give us features, so not RGB, but features at each location. We do volume rendering, and then have one feature for each ray. From that, we can, for the LiDAR, decode some different properties, like the probability that the LiDAR beam won't return, so ray drop probability, and the LiDAR intensity. For camera rays, we send it for a small upsampling CNN to get the RGB, basically only to be able to shoot these rays at the lower spatial resolution for efficiency. The design methodology when we did this was to keep the method kind of simple, but we found that there's some details that matter when you do this for autonomous driving. So first thing is these cars usually drive at high velocity. We can be on a highway, and then you get issues with rolling shutter. Usually you don't see this in these handheld data sets, but for us, that's a big problem. So we account for that by actually shifting from where we shoot the rays. Also, we have usually surround cameras, and the issue with that is that the same location in space can look different in these different cameras. They may have different eye speed and so on. So to deal with that, we just append a sensor embedding to these ray features to sort of tell a network what sensor we care about. For the LiDAR data, this ray drop probability is really important. Otherwise, you get these too dense point clouds, which then are not realistic enough if you want to use them in simulation. So here we have a small demo of what these renderings can look like from camera and also in 360. And we also did some quantitative evaluation. So what we thought was kind of cool is we just tuned our hyperparameters on this panda set, and then we just applied it on a bunch of other data sets like new scenes, Kitty, Argo, Sod, and it just worked out of the box and achieved state of the art. So we think it's a really robust method. So if you have any questions, come to our poster. We also have the poster session on Thursday afternoon. Make sure to check out our code. We built on top of Nerve Studio, so it should be easy to use, and we hope that you can build some cool things.
Thanks for listening.
Thank you very much. Let me just. I just want to do one thing, namely share. Where do you know where?
This place, this is this place.
Yep. Okay.
You share already?
Nope. Still. Oh, here we are. We'll make this big again. Okay, I think we should be good to go. I'll leave it with you. Perfect.
Yeah, hello everyone, I'm Adam, and I will present how we actually use NeuRad, which was just presented to, are we sharing on the? No. Thanks. Yeah, so I will present how we use NeuRad to perform safety critical simulation for autonomous driving. So, like many speakers have talked about both today and yesterday, safety testing is quite difficult for autonomous driving because you can't really do it in the real world on real roads. So in industry, one way this is handled is by these new car assessment programs like Euro NCAP, where you basically drive your test vehicle to a dedicated test track and you run a bunch of very specific safety critical scenarios which are designed to really test the most important cases using this kind of controlled inflatable dummy. And as you can imagine, it's not very scalable since you actually have to drive a vehicle to a physical test track. And in some sense, at least, it's not so realistic because this is a test track. It doesn't look the same way as a bustling urban environment. So in this work, we propose to take real-world driving logs, like this sequence here from New Scenes, and using NERFs, we can convert this to the same kind of safety critical scenario, which is done in this Euro NCAP tests, but now in a real world, in a real city environment. And if we couple this with a closed loop simulator, we can actually evaluate the current sort of state-of-the-art autonomous driving models on how they perform in these safety critical settings. So I'll very briefly just explain this simulation engine that we built. So we start off with a scenario definition, and this basically just defines the initial conditions for the ego vehicle and the trajectory of the safety critical actor that will threaten a collision. And we feed this to the NERF, NeuRad, which then uses this to produce a set of sensor inputs, which is consumed by the model that we're testing. In this case, we test UNAD and VAD. And these models just output a trajectory, which a controller converts to some acceleration and steering signals, which are used by a vehicle model to propagate the vehicle pose forwards in time, which gives us new camera poses, which are fed to the NERF. And the whole thing repeats until we either pass the scenario successfully or we crash into the safety critical actor. And basically, yeah, so for those of you that are familiar with Euro NCAP, there are tons of different scenarios. We didn't sort of implement all of them. We chose to keep it simple, and we have 3 different scenarios, which are basically self-explanatory here. You have either a stationary vehicle, a vehicle approaching from the side, or a vehicle actually in our own lane driving towards us, threatening a frontal collision. And to gain some robustness, since we're in a simulator, we can sort of afford to spend a little bit more here, so we can run this multiple times with some perturbations on the position and velocity, and basically randomize these scenarios a little bit. And here's how it can look. So we have the same underlying New Scenes log, and we render the 3 different kinds of scenarios here. And this is sort of one random run for how it can look. Around this, we build a dedicated evaluation protocol, which we release open source. We hope people will run it on new models, consisting of 20 different scenarios, which we then run 50 times with these random permutations, also swapping out the actor models, so we can do that in the simulation. And then we score in a similar way that these Euro NCAP certifications are being scored, where you get 5 stars if you don't crash, and if you crash, you get somewhere between 0 and 4 stars, depending on the impact speed. So you're encouraged to basically brake as much as possible.
And now to the most important questions. So how do the state-of-the-art planners actually perform in our new evaluation protocol? So let me play a video. Yeah, so this is UniAD, which was best paper last year, and VAD, another state-of-the-art method. And as you can see, they crash a lot, which is a little bit concerning. It's not super surprising since they're trained on nominal driving. They're not trained on these kinds of safety-critical scenarios. But this highlights that there is a need for some improvements in how these methods are designed and trained. And as you can see, they don't score that well. You want to have 5 stars on this. One very important question, is this actually a problem with the models or is it a problem with our simulator? So we looked into the perception outputs for these models and we find that almost always they detect and predict the future trajectory of the safety critical actor basically perfectly. And nevertheless, they did perform or they output a plan that results in a collision. So this seems to be actually a flaw with these models. And with that, thanks for listening. Come to our poster. We hope that you will maybe use our evaluation protocol and test the next generation of end-to-end driving models. Thanks.
Thank you very much. Max, where did you have to press in order to project it properly?
Slideshow and then session start.
Oh, okay.
All right. So hi, my name is Moritz. I'm working at Zoox, and today I'm going to present our paper "Scaling is All You Need: Autonomous Driving with JAX Accelerated Reinforcement Learning." Overall, what was the goal of this paper? So ultimately, we want to train a policy that is better than humans, so safer than humans, and particularly, and still makes progress towards the goal. In our paper, we do this with reinforcement learning because reinforcement learning showed big success in other domains like video games, and we really wanted to transfer this success to autonomous driving. Overall, why is that hard? So building reinforcement learning on the scale of these large papers like DOTA 2 AlphaStar is already pretty challenging, and I think the biggest factor is why we also have this workshop. You cannot really train in the goal environment, which would be the real world. So it's prohibitive from the safety and scalability perspective. And what we did is basically building up a realistic and really scalable autonomous driving simulator and combine this with a scalable reinforcement learning framework to then train our policies. The main idea of the driving simulator is to use real-world driving scenarios that we gather with our fleet, and then we achieve very high throughput by running this simulation on accelerated hardware, utilizing JAX. Mainly what we do to achieve this, we prepare the data so we can batch different scenarios together, and then we can call the model on batched observations that gives us a reaction, and then also continues the simulation in a batched way. With this, we then define the reinforcement learning problem. So basically, our observations are a subset of the state. And then we define 2 kinds of rewards. First is sparse rewards for safety relevant events like collisions, and then dense rewards for progress and comfort. Overall, our training framework then does 2 stages. First, we do a behavior cloning and follow up with a reinforcement learning stage. The reinforcement learning uses PPO, but due to the large distributed reinforcement learning framework, we have some off-policy data, so we address this with the retrace off-policy correction. Before we can now actually train our policies, we need a data set. Overall, we gathered 3 different training data sets and 1 test set. The test set we target to be as close as possible as in existing baselines. So we took 10,000 scenarios of 10 seconds long, all from human driving in San Francisco. And then similar also on the metric side, we stick close to the baselines that exist and take the failure rate and the progress ratio. I think they have been mentioned today as well already. With this, we then set up different experiments. Mainly, we use these 3 different data set sizes and train them with 3 different model sizes on really large scale, training them up to 2.5 billion agent steps, which is a lot of simulation. And when you focus, for example, at the top right, this is a failure rate training curve. You can see that for all model sizes and dataset sizes, we actually get better over training time, and it's really key to scale it to that many steps to achieve the performance. As you also expect, with larger model size and larger dataset size, our models do improve. When we compare our best policy with existing baselines, we found that we could reduce the failure rate by about 60% while actually getting better progress. Finally, let's take a look on the computational cost. Mainly increasing the model size drives the cost. And however, the data set size is very important for the model performance. So overall recommendation would be scaling the data sets first, then doing more agent steps, and then look into the model size. At the top bottom left, you can see 2 example scenarios of our policy behaving, actually yielding or in both cases very well to the adversarial agent. Okay, I think that's it. Thank you for listening, and happy to see you at our poster.
That's the wrong one. This is you, right? Yep. Why does this? Sorry. Oh.
Hi, my name is Katrin, and I present today Drive-LM Driving with Graph Visual Question Answering. Okay, so first of all, why language and driving? I think that's quite a hype topic nowadays, so I don't need to motivate a lot, I guess, but yeah, still a bit. So of course, like if we use vision language models, large language models, all these foundation models, we can use a lot of like internet scale pre-training, which wouldn't be possible without, because there's just not so much driving data out there. Then we hope that we can solve generalization with it to like unseen situations, unseen objects, and so on. And then also like big topic explainability. So we do like graph visual question answering, but why graph? Like, do we think in graphs, or like there's also a lot of works about like chain of thought thinking and like these kind of things. So I have a small task for you. So everyone who can get like the answer of this 1 + 1 question, please raise your hand now. Okay, some can't answer it, but I think most of you can. And I think there was not much calculation or thinking involved, so you just knew the answer, I guess. And I think that's similar for like some driving, like if there's just a street without anything happening, you don't need to do much. You don't need to think about like driving. So you just do it and you can think about like your pizza or whatever. So same task again. So who can solve this question here? Like 79 × 37, please raise your hand. Okay, no one, yeah. Because like this is much more complicated, but I think if I would give you like a bit of time, every one of you could solve it. But for that, like you need a bit more complex thinking. You would first solve 9 × 7 and then 7 × 3, and then you would add those 2 calculations, and then you already have a graph, right? You do like 2 calculations and then you connect those nodes. So you already had like a graph in your thinking process. And I would argue that's the same for driving. If you have like a really complex driving scene you haven't seen before, or you're a beginner in driving, you really need to think about like all those little steps, like, oh, the traffic light is there and there's this and another vehicle's coming and what do I need to do and everything. So yeah, a bit more like complex there. So that's why we thought about like, okay, what is involved in driving? And we came up with like a small graph here. like about stop signs and traffic lights and the road layout and other vehicles and how do they affect us, and like most like important stuff, and how are like those different things connected. And with this in mind, we build a data set, a visual question answering data set for new scenes and for Carla, which involved like different type of questions. So I already mentioned some types, but basically we clustered them into perception questions about like what kind of objects are visible in the scene. Then about prediction, what are those objects going to do in the future? And then about planning, how do we need to behave based on those objects? So this is basically part of our data set. And for the whole labeling process, we had like for new scenes, we had some human annotator to make sure that we have like really high quality labels. And we did like multiple rounds of quality checks and relabeling and everything. So yeah, that we have in the end like a good qualified data for the new scenes data set. And then for Carla, we have some, because it's a simulator, so we can basically access information on this from the simulator. And then we have some rule-based templates for the question answering. So there was no like human labeling involved, but some human quality checks. So we have basically those two parts of our data set. And then like we have an agent trained on this model, basically, where we give context of previous questions to the next question and train like a vision language model, which is pre-trained on internet scale vision language data on our data. And then we add like we have perception, prediction, planning. And then we also add like the motion planning step so that we can predict waypoints in the end, basically, and do planning. Yeah, very quickly, there are some limitations of our work. Currently, we only have single camera, only front view camera. We only do open loop evaluation, but because we do Carla, we can do closed loop evaluation in the future. And obviously, efficiency is a bit of a problem currently because we have like all these questions and all the iterations of the language model. So yeah, thanks for the attention. And if you have questions, please come to our posters. And yeah, thanks.
Thank you very much. We do have a mysterious red line on the screen. I don't know where it's coming from. In Zoom. How do we? Zoom hit somewhere and I can't find it.
Look up there.
That just doesn't do anything.
This one there?
Ah, here. I'll just stop sharing for a second and I should come back here. Yeah, exactly. It seems to work. Okay. Then next is Drive VLM.
Hi, everyone. I'm Hang from Tsinghua University. I'm presenting our paper, Drive VLM, the convergence of autonomous driving and large vision language models. When I worked on a robotaxi, L4 self-driving for several years. And a couple of years ago, people asked me, like, how do you solve autonomous driving corner cases that's so rare that you only experience it once in a lifetime? Like, for example, this one. This is a case that Waymo showed a couple of years ago. They encountered a woman wheelchair chasing for its duck. And how do you deal with these cases? And then people may challenge me saying that, okay, AGI should happen before self-driving can be achieved. L4 self-driving can be achieved. So then as you know, last year, the emergence of large language models seems to be able to solve this problem. So I think the future of autonomous driving technology is also will be centered around vision and language, where the vision offers very dense observations. Each pixel counts. It tells us the textures and rich attributes of objects. And then the language help us to understand the holistic scene and reason about the relationship of the things we observe and the relationship of their effects on our self-driving vehicles. So we propose Drive VLM. The Drive VLM is basically using a vision model and a large language model together to solve driving tasks, where we have a vision encoder that takes a sequence of images in, and then a large language model that performs chain of thought reasoning. And this the chain of thought reasoning has 3 stages. The first stage is called scene description. It's basically the model tries to describe what it sees in the images. And then the second stage is about scene analysis. It analyzes which object is important to us, to the self-driving, and what effects they have on our self-driving vehicle. And the third stage is called hierarchical planning, where the model tries to decide what we should do in several stages. First, it tries to tell us the decision in natural language. Second, it will also output meta actions within a constrained set of tags or labels. And finally, it will output waypoints for the self-driving vehicle. It looks like a great idea, right? However, we found that Drive VLM is not perfect. It has a lot of problems. First, it has very poor 3D spatial grounding ability. More precisely, its perception is really bad. It has a lot of false positives and false negatives and inaccurate distance measurements, estimations. And second, its planning. The planned trajectories are usually very jaggy and they are prone to collisions. And also, it's very slow. It's hard to deploy Drive VLM directly on a car for real-time inference. That's why we propose a dual system for autonomous driving. The motivation is that when we are driving, 95% of the time we are driving without thinking, using basically with muscle memory. And only for less than 5% or even 1% of the time, we need some reasoning. We need to look carefully and reason about the scenarios. Those are the long tail cases that Drive VLM is really good at. So this system, the dual system is called Drive VLM Dual. Basically, we still have the Drive VLM on the top, and in parallel, we run another system that is the traditional self-driving pipeline or end-to-end pipeline. Both are fine. What we do is we send the 3D perception results, feed the 3D perception results into the Drive VLM so that it gets better reasoning outputs. And then when the Drive VLM outputs its meta actions and reference trajectories, it will be further refined by this traditional planner so that we can get a smooth and safe trajectory that can be executed. And in order to train this model, we find that prompt tuning, directly prompting is not a good choice. So we develop a dataset construction pipeline to get a dataset of around 1,000 scenarios. These scenarios, we got many, many interesting scenarios from 1 billion miles driving experience. Like this, in urban driving, we met a very complicated construction zone that we need to nudge around. And on a highway driving, we met a lot of bisons on the road. And we don't stop. We're gradually driving through this group of bisons. These are the data sets we collected to train our model. And finally, we try to deploy this dual system model on a board, on a real car. On the car, there are 2 Orin X chips. And one Orin X is running an end-to-end planner, and another Orin chip is running our Drive VLM. And they are collaborating, they're running in parallel. The Drive VLM runs at 1 Hertz, and the end-to-end planner runs at 10 Hertz. So they run in parallel to drive the car. There are some insights below due to the limitation of time I will not go through. But let's watch our demos. The demo video is a bit long. If you're interested, you can check out at the poster session. But basically, we're running these two systems on board on this car. And as you can see, we are outputting natural languages while driving. The Drive VLM makes high-level decisions, and the traditional end-to-end planner makes low-level control. Okay, I'll not play the full video. Talk to me if you're interested. Thank you.
Okay, hello everyone. I'm Xiaoyu from Peking University. Today I'm glad to share a walk driving Gaussian, complete Gaussian surveying for surrounding dynamic autonomous driving scenes. So modeling such complex surrounding driving scenes is extremely challenging, especially when we use sparse data collected from virtual multi-sensors with small overlaps across cameras and large gap across time. It suffers from complex geometry and lighting conditions with multiple dynamic objects on the street and move at high speed. So there are some excellent previous works have demonstrated the potential of 3D representation, like Nuro for 3D.js in modeling real-world scenes, but they have fallen short in representing complex large-scale driving scenes, leading to low visual quality, blurring on details and dynamic objects as shown on video. So in response, we introduced driving Gaussian, the first 3GS-based framework for reconstructing surrounding driving scenes, and we proposed some effective modules for static background and dynamic objects with geometry priors and result in photorealistic rendering and construction quality on autonomous driving datasets. And overall, we just employ images from multi-cameras, for example, 6 cameras, and use the LiDAR point, which is commonly provided in the driving datasets. And we also use a set of composite Gaussians to model the whole driving scenes and rendering surrounding driving scenes. So, so here are some key steps. So first of all, we first decompose the whole scene to static background and dynamic objects using the ground truth labels or pre-trained pre-trained foundation models to detect moving objects. And for the static background, one straightforward operation we perform is to segment the long distance background into many bins, and we then incrementally add the subsequent bins into the previous ones to obtain a more detailed Gaussian representation. And for the multiple dynamic objects, we use a dynamic Gaussian graph to organize them, which is inspired by NSG, and optimize their Gaussian separately. We then integrate these multiple dynamic objects into the whole scene based on their attributes and obtain the final reading results through the global rendering. And next, LiDAR is used to help recovering more precise geometry, and they can sort of solve the image degradation problem across different cameras because they have a better consistency in the 3D space. So driving Gaussian enables reconstruction of complex driving scenes and also enables corner case simulation as shown on the figure. We can simulate a fallen person during the car's journey to test the safety of the autonomous driving system. So experiment results show that driving Gaussian achieves photorealistic reconstruction and rendering quality on Newton's dataset, which has surrounded images, and also not specially designed for multiple scenes or methods, so shows good performance on multiple driving scenes like Kitty. So here are some here are some view results, and we obtain good consistency across multi-cameras and also dynamic objects across time. So here are some video results. Okay, and you can see here that our method models the whole driving background while maintaining high-speed dynamic objects in good detail compared with our best methods. And here are more video results. Okay. Okay, that's all. Thank you. And if you have any further questions, welcome to our poster session on Friday morning. That's all. Thank you.
Thank you very much.
Good afternoon, everyone. I'm Zhu from Conning University, and this is Xu from Shanghai Jiangheng University. We are excited to present our work, chat sim, edible scene simulation for autonomous driving via collaborative large language model agents. As you know, data is crucial for street view perception tasks. However, current data sets like sufficient corner cases, which are vital for ensuring the safety of autonomous vehicles. Using a simulator, we can generate and customize more data for training purposes. Current simulators fall into three main categories: rendering engine-based, video diffusion-based, and scene reconstruction-based. Rendering engine-based simulators like Color have the drawbacks of being not photorealistic enough and having a steep learning curve for users. And video diffusion-based simulators face issues such as limited image quality and controllability, along with occasional spatial and temporal inconsistencies. Scene reconstruction-based simulators struggle with incorporating external 3D assets and require complex editing steps. To address these challenges, we propose a novel driving simulation system that's controlled by language commands. Our system simplifies the addition, eliminating the need for complex coding. Instead, users can modify scenes using detailed language commands. Additionally, our system produces multi-view consistent photorealistic images and allows the integration of external 3D assets into the rendered scenes. Here is an overview of our multi-agent collaboration framework. Basically, the user's command is assigned to a project manager agent, which interprets and dispatches the commands into subtasks for various technical agents. We have 3 agents dedicated to foreground rendering, including 3D asset selection and vehicle motion generation, and 3 agents for background rendering, including vehicle adjustment and vehicle deletion. This is a sample design of our agents. We first provide a task description and interpretation of details, return format, and some examples to prompt the language models. And the agent then returns the representations in specific format. For background rendering, previous neural rendering methods suffer from camera pose errors and exposure inconsistencies. We address these issues by proposing MacNerve, which accounts for exposure time in the volume rendering process and renders images in HDR space. For the foreground rendering, we estimate environmental light information from multi-view camera images. For sky dome, we train a network to return the HDR sky dome light. And for the surroundings, it can be obtained directly from our proposed MacNerve The entire environmental light map is then used by the Blender renderer to properly light the 3D assets. The sky dome light estimation process is divided into two steps. First, we reconstruct the sky dome LDR from camera inputs, and then we train a network to reconstruct the HDR from the LDR images. Okay, this video demonstrates the results and they're complex and makes the commands. Our system actually captures each specific demand and provides flexible editing functionalities. Okay, here is another example, the output from the system under an abstract command, where the command is broken down into several executable operations. Okay, our system also supports multi-round interactions with user commands, allowing users to edit the previous output by providing more information. These are qualitative results of our MacNerf and MacLight, which shows that the foreground and background scenes can be rendered photorealistically. Our MacNerf also quantitatively outperforms previous nerf-based methods. This ablation study illustrates the effectiveness of our two contributions in neural rendering. It clearly shows that the significance of our contributions. And further experiments demonstrate that MacLight achieves the state-of-the-art performance. And okay, thank you, and feel free to stop by our poster on Thursday.
Thank you very much. And we have one more.
Hello everyone. I will present distill nerf, perceiving 3D scenes from single glance images by distilling neural fields and foundation model features. And for autonomous driving, various perception tasks are designed for perceiving 3D worlds with 2D observations. For example, detections, tracking, segmentations, and occupancy predictions. However, those tasks are hard to scale with a large amount of data. Although we have the industry have collected tons of data for the autonomous driving, however, data annotations very painful and labor intensive and need a lot of human labors to annotate it, every 3D bounding boxes and every workflows for this perception task. On the other hand, using neural radiance field is a promising direction that is self-supervised learning approaches that could model the 3D scenes with the input images and LiDAR point cloud and without any manual annotations. So it is very popular and fast-moving topic. And recently there are a lot of works are trying to address the autonomous driving scenes with the neural radiance fields. However, when applying the neural radiance fields to the autonomous driving scenarios, there are still some challenges. The first, they need for modeling the dynamic driving scenes, that requires a large amount of overlapping images. However, our autonomous vehicles, they only have like 4 to 6 cameras, and they cannot have high overlapping viewpoints during the driving process. And also, nerf is good, but it is a post-optimization process. That means that you have to optimize everything. And this optimization process will take a long time. Usually it will take several minutes for optimizing a single scene. And this makes it hard to use for onboard driving, because for onboard driving, we have latency requirements. So we usually only have like 0.1 seconds of latency, and for the on-vehicle on-vehicle computations. So can we bring the nerf online and generalizable to the new scenes? So here we propose distill nerf. So this tuner is an online model that leave the 3D features, leave the 2D features to the 3D, and they can rendering the both the images and the depth image without the test time parsing training. So how do we do that? So the first step is we lift the surround view images to the 3D using the by pixel lifting to the 3D space. And after that, we get the 3D representations. We use differentiable rendering to render the 3D representations to the 2D images. And in addition, we also, in addition to rendering the images, we also rendering the depths and the feature maps from the foundation models. So in this way, we can distill the knowledge from the foundation models and also the depth information to our 3D representations. And during this training, we are able to, our onboard model is able to capture the rich semantics and can be further used for the downstream autonomy steps. So here we show some capabilities of our distilled nerve models. So given a single frame input, so we can do the 3D scene reconstruction like other method. We can also building a feature field by learning from the foundation model features using the neural rendering techniques. And because we have foundation models as representations for our onboard models, we can also do various downstream tasks, for example, the occupancy predictions and also open vocabulary queries. We can also perform the novel synthesis without the test time parsing optimization, just giving a single frame of images. So thanks for listening. If you have more questions, please come to our poster at 181 today. Okay.
Thank you very much. Yes, with that, the lightning talks are done. The posters are in the other building. As I said before, there's free coffee, and the poster locations are 157 till 181. And we'll continue here in about 40 minutes.
Use this laptop. You can mute your laptop.
Yes, I have to.
I think it's like if you click the Zoom above, the mute audio is the first.
Okay, so we will slowly continue with the workshop. We have 2 more exciting talks coming up, and then we will finish with the panel. So first, it's like my pleasure to welcome Jamie Shotton, who's a chief scientist at Wave, working on foundation models for autonomous driving, such as, I guess, Gaia, Lingo, but also data-driven simulation environments, such as GhostGym and recently Prism. And I'm looking forward to hear the latest, greatest from Wave.
Great, thank you very much, and good afternoon, everyone. Hope you've been enjoying the workshop so far. A pleasure to be here, and very much a subject close to my heart. I've always been a huge fan of simulation, and particularly of data-driven simulation. So hopefully this will be fun. You can't have failed to sort of notice the incredible progress in AI of the last few years, and indeed the accelerating rate of progress across all sorts of tasks, be it hand recognition, speech recognition, computer vision, object recognition, language, etc. Right? This is just phenomenal, and it's only getting faster. And I'm very excited because I really think driving is next, and it's going to be transformative for society. But driving is hard. This is just one of many examples that are not edge cases pulled from our corpus of driving around London. And the point here is that it's we're interacting with the real world. We have enormous complexity in there. We have enormous unpredictable things moving around, i.e. humans and indeed vehicles in that space. And we need to be able to deal with all of that complexity. But let me just close that. The opportunity here is incredible, and of course we've all seen examples from science fiction over many years now of the future of embodied AI, of various embodied robotics that act in the world, act in the physical world, and help us and help us achieve more, help us do things better, make us safer. And this is as I say, this has been science fiction for ages, but we're finally on the cusp of actually solving some of these challenges and deploying robots in the real world. And I think that driving is going to be first for various reasons we'll see in this talk. So, looking back over the last decade plus, you kind of fail to see the enormous progress in especially computer vision and NLP, starting with large data sets, unlocking large scale training, new architectures like AlexNet, new architectures, and then in the space of NLP like the transformers, opening up huge new avenues for progress in this space. And again, this next frontier is going to be robotics and embodied AI, autonomous driving in particular. So looking at this, busy scene of London, again, not a particularly edge case example, and the enormous complexity of this very unstructured environment. It's been clear to us since the get-go that this is really an embodied AI problem. It's a decision-making problem. It's not just a perception problem. We need to know how to act in this world. We need to know how to maneuver around these vehicles, negotiate with them, deal with roadworks, and understand how to get from A to B. A traditional AV stack, as we all know and love, looks like this. And while very capable, and has absolutely been proved it's technically possible to build these and make them work, it's very hard and expensive, and so far has not been turned into a viable, scalable business yet. And there's a number of reasons for that. The expense and brittleness of a supervised perception stack, the fact that you have this strong information bottleneck here around perception. So the example I like to give is Imagine you had a perfect head-mounted display that gave you full surround vision, had no artifacts at all. Would you get in a car and drive in that with that display showing you perfect perception bounding boxes? I don't think I would as a human, because you don't know what you don't know. There's always something unexpected, and I would want to trust the raw data when I want to do my decision making, not those outputs. The architecture is complex, and with that complexity comes brittleness. A reliance on HD maps, they're great if you've got them, but again, and they do add value, of course, but they're really expensive and hard to scale up. And of course, we've got to integrate this into consumer vehicles, and the automotive sector is very price sensitive. And so, yes, additional sensors help in theory, but do they actually add meaningful value? And can you integrate them efficiently? And so instead, at Wave, we've been taking a different tack from the get-go, trying to think about a low-cost approach that's going to scale. Whether that's a flexible use of different sensor sets, including just cameras, if that's really what a customer wants, to of course, the primary thing, just using an end-to-end neural network that takes pixels in on one side and outputs driving plans on the other, followed by a control system. And this approach has many exciting promises. Especially in terms of deployment, right? It's computationally homogeneous. This is just a bunch of, transformer blocks and ultimately sort of floating point matrix multiplication. That's easy to deploy on diverse hardware. We've shown increasingly the ability to rapidly generalize and expand our ODD to new cities, new countries, new vehicle types, all powered through data. It doesn't need a change in our architecture. We don't need to reprogram a bunch of stuff. We just need to add the right additional data into this. As we said, it's scalable and economic in terms of the sensors and the HD mapping. And increasingly, we're getting evidence that it is superior in terms of performance and ultimately safety compared to more traditional approaches. A few examples of what this looks like. In the streets of London. So, top left is an interesting negotiation scenario where the car sees the vehicle approaching, pulls over, and lets it pass before it decides to move on. Negotiation was something I was sort of unclear whether we'd solve that using end-to-end when I joined 3 years ago, and turns out it's not a problem. Here's another similar example where we're very polite. We see this car indicating and pause for it to turn around before we move on ahead. Bottom left now, we're getting a bit of an unusual edge case here where a car is deciding to reverse up all the way back up the road to park. Again, handles it effortlessly and then lets a pedestrian pass before proceeding to the junction. And bottom right, bins tipped over in the road. Now, none of these are individually that exciting or groundbreaking, but the fact that they all emerge through data-driven learning is what's exciting here. Another example of generalization through data here, where we've been building our approach to generalize across different vehicle types. And the video on the right is the same neural network driving two different vehicle platforms, a car and a van, one following the other in this example, around the streets of London. But I'm going to spend the majority of my time talking a little bit about frontiers in AI research, in particular simulation, of course, the focus of this workshop, but also a little bit on multimodality and foundation models. So simulation. Well, if you're doing end-to-end autonomous driving, you better be thinking about end-to-end autonomous, end-to-end simulation. And that poses some pros and some cons, right? It's going to be a bit harder to do, but I think there are some real opportunities if you can solve this. So here's just a few of the simulation systems that are out there today across the industry and across academia. And lots of great stuff to be said there. I think I've always been a fan of simulation, as I say, and it's great to see continued investment in this space, pushing the boundaries. When I look at autonomous driving, end-to-end autonomous driving and simulation for that, the things that I think are important are these desired outcomes on the left, right? We've got to, you can't just simulate just the perception or just the behavior. You need to do both and close that domain gap. You've got to be able to deal with the complexity of the real world. And this often gets glossed over in terms of things like the deformable objects in the scene, the pedestrians and the cyclists, for example. Pretty crucial that we're able to simulate those. Of course, you've got to simulate the full embodied AI platform and not just the sort of visual rendering. It's got to be scalable, and that's really where the sort of data-driven aspect comes in here. I think that's one of the key ways to make simulation scalable. And finally, controllable. You've got to have some level of control over this to make it do what you want. And I think with Ghost Gym, as we'll see, we're getting close to satisfying all of these. So we started from a premise of trying to resimulate the world, because it really helps with a bunch of those things. You know, a few years ago, we started looking at novel view synthesis, using NeRFs initially to turn a video in the top left into a reconstruction, essentially. And once you've got a reconstruction, then you can start to turn that into a simulator further. And that's what Ghost Gym is that we talked about on our blog recently, which is, you know, essentially taking that reconstruction and turning it into a closed loop simulator with everything that you need in terms of the simulation of the robot stack itself and sensing, etc. And the little video there is just a few of the collection of scenes that we reconstruct. So this was great, but you know, the examples I've shown so far have all been very static, and that we knew that wasn't enough, and so we've been investing in reconstructing the true dynamic parts of the world, and just yesterday we've launched Prism 1, which is scene reconstruction especially tailored around dynamic urban scenes. And this is a self-supervised 4D non-parametric representation of that scene. And so here's a couple of examples from of a street in London and a street in the Bay Area. And, you know, at the first glance, you could be confused and think these were videos. They're not. The other thing you could miss are things like the brake lights coming on the vehicle there. That's what happened in the world. We captured that on video. Now we're able to reconstruct in 4D the fact that those are happening. Same for pedestrians walking down the street on the right there. Here's another example where we've got these cyclists, and we are, again, able to reconstruct their deformable dynamic behavior as they cycle through the scene. Same for the pedestrians on the left, the reflections in the puddle, and of course, all the static environment in the vehicles as well. Here's an example where we're now deliberately perturbing the camera path in this sinusoidal path, and some really cool stuff to see here. Obviously, we've got a pedestrian with this umbrella, which is pretty exciting. You've got complex lighting conditions here, reflections of the ground. You've got the traffic lights there changing from red to green as it goes through, and you know, beautiful reconstruction there as well. Here's another example of a construction zone where we're just going to pause the camera, translate it, rotate it, and again, show that this is not just a video playing, but this is a controllable simulation. Here's another way of looking at that reconstruction, where instead of moving the camera now, we're moving the time dimension. So we're freezing where the camera is and letting time roll forwards and backwards a little bit. And you can see, you know, the vehicle's moving. It's obviously slowed down here. The vehicle's moving. You can see the traffic lights changing, all the shadows and lighting working pretty well here. And a couple more examples showing some complex lighting conditions, the reflections on the wet ground on the left, and the lens, the sort of reflection of the building there Again, really small details seemingly, but these can often make the difference between, you know, trusting that this is simulating what actually happened and not. As part of the development of Prism, we had built a data set internally that's tailored to this specific task of 4D reconstruction of complex dynamic urban scenes. And I'm delighted that we're also releasing that. You can download it from the URL at the bottom. And we've really concentrated and dived deep onto the diversity of this data set. So there's not that many scenes in number, but they're really interesting and rich sources of different challenges. So, you know, a few different lighting conditions to illustrate here, from sunny to wet to night. Or more interestingly, some of these really quite challenging urban scenes with lots of dynamic actors, especially the top one. That might be the most extreme one in the data set. But again, these are not unusual edge cases. And if our simulators are truly to represent the world, we need to be able to deal with this level of complexity. So I'd very much encourage you to go have a look and see if this data set could help you in your research. Now, the last thing I said around simulation is that we want to be able to control this somehow. And I think particularly for edge cases, it's really important that we can, you know, we can expand the reach of the data that we have. So last year, we released something called Gaia, Generative AI for Autonomy, which is effectively a generative world model. So if you think of Prism, what I just showed you, as reconstructing what really happened in a particular scene, Gaia is all about generating new stuff that never happened. And we approach this with a very relatively standard approach these days of next token prediction. You predict the next token in your image, and then do some video diffusion on top of that. With that, you're able to generate a rich set of data, as we're going to see in a moment. It's become a very hot, crowded space here, and here's just a few of the other great pieces of work in this space. So this is what Gaia does when it's left to its own devices. So again, unlike Prism, where we're reconstructing real parts of the world, in Gaia, we are just creating new worlds from scratch, at least in these examples. And note that it's able to generate realistic, static scene, realistic traffic, lighting, even perspective and, 3D. That's all manufactured, that's all learned from this next token prediction. Another thing you can do with Gaia is to unroll the future multiple times from the same starting point. So in this example, this is just two different unrollings of the future. With the left one, the car reverses to let us through and we drive through. On the right, the car decides instead to pull forwards and we brake and give way to that car as it pulls up. But it is a world model. It's not just a purely generative model. It's a one that we can condition on action. And so in this example, we're conditioning this, we're steering it, and we can tell it. So this is where it starts to feel a bit more like a simulation. And we can steer the vehicle towards the right into this oncoming vehicle. And lo and behold, the world model inside Gaia realizes that's not a good thing, and it takes that vehicle and then and gets that vehicle to pull over to the side. Where it gets really interesting, though, when it comes to controllability, is when we start to combine the best of both worlds of Prism reconstructing real parts of the world and Gaia generating new things. So in this example, what we're doing is we're taking a real scene on the left, and we're saying we want a car where that cuboid is. And Gaia will then go render that and create that car photorealistically with the right lighting, the right composition, the right shadows into that scene. Here's a couple more examples where we've asked for a bus on the left and a couple of vehicles there. And of course, we can do this in video form as well. And this example, all of the dynamic agents here have been placed there manually, and we can control those. And moreover, we can generate not just single images and videos, but multi-view images that are consistent across space and across viewpoint. And the last example I'm going to give here of controllability in this space is back to Prism, where we've got a real scene on the left that we've reconstructed in Prism, and now we're editing it. We're taking out that pedestrian, and because it's a 4D representation that has disentangled the static and dynamic elements of the scene, this is relatively straightforward to do. And so we can essentially just erase this pedestrian. And this gives us this wonderful lens of counterfactual testing for end-to-end driving, where you can change exactly one thing and see what happens, see how the driving model changes. And because you changed exactly that one thing and left everything else the same, you know that that thing is the thing that has caused the change. And so that gives you this really interesting causal relationship and set of tools to explore. So this is just the beginning here, and really excited to see what comes in the next few months as we scale this up. So 2 more topics to just quickly touch on. The first is multimodality, and really this boils down to, can language help us with the driving task? And here we're looking at this from a few aspects, whether it's explainability and interpretability of what's going on in these things, whether it's actually improving the driving itself and the driving policy using language and the knowledge encoded in LLMs. And can we use this to help build trust and safety in this technology? So last year we launched Lingo 1, our first foray into this space, which was really ultimately a grounded VQA system. And it was able to do things like you see on the left, providing live commentary, maintaining my speed. I'm slowing down due to a jaywalker. I'm slowing down in preparation for the upcoming left turn. And the more interactive thing where we could provide it a snippet of video and ask it questions about what's going on in that scene in a more interactive ChatGPT style, and get meaningful answers back about the driving task, about what it's seeing, about why it's making its decisions, about what the rules of the road are, etc. We extended that with Lingo Show and Tell, where we added referential segmentation. So not only would it tell you what it was doing, but it would also show you. It would say, okay, this is the bit of the scene that I'm paying attention to when I'm giving that answer. This is the car I care about in that bit of text, to build further confidence in that grounding and understanding here. And most recently, we've launched Lingo 2, which is where we take that to the next level. And instead of just taking a driving scene and outputting text, so video to text, this is a system that can actually drive our car. It is one of our end-to-end driving models, but it can also output language and also input language. And so here's an example here where the policy driving the car is Lingo 2, but Lingo 2 is also outputting this text at the bottom here. So turning right to follow the route. Reducing speed for the cyclist. Slowing down for the upcoming turn. Turning right to follow the route. Keeping left to follow the route. Turning left, etc. Here's another example. Turning right, reducing speed for a turn. Staying on the planned route, increasing speed. Reducing speed due to jaywalkers, moving past a parked vehicle, increasing speed to meet the speed limit. And here's one more example. Open road, keeping the same speed, maintaining the same speed, the zebra crossing is clear, keeping the same speed, the road is clear, etc. So that was great in terms of the live commentary of this system as it was able to drive, but we can also control it with language, that would be the input side. And now we didn't do this in the real world for safety reasons. We don't want to deal with anyone could ask it to do things that it really shouldn't be doing. But in simulation, we absolutely can do this, and we can start to see, is it listening to the language as a way of commanding it as well. So on the left, we take a ghost gym simulation and we ask it to stop behind the bus, and lo and behold, it decides to stop behind the bus. On the right, take the same simulation and say, overtake the bus. And lo and behold, it continues to drive. We can also look at these counterfactuals and the idea of changing one thing. So here's an example where we've taken a real driving scene up at the top, and we're now inserting vehicles, as I showed you with Gaia, into the scene and seeing what happens, both from what's the driving plan, how does the driving plan, what does the driving policy change, but also how does the language change. And so, top left, it says increasing speed to match the speed limit, and you can see that that red line represents the driving plan. Bottom left, it says slowing down to match the lead vehicle's speed, and the driving plan has also changed. Top right says stopping due to the red light. Bottom right, where we've inserted that vehicle, stopping behind the stationary traffic. So building more and more confidence that these things really are connecting the right things in the scene with what's going on inside this end-to-end model. And my very last topic today is on foundation models for embodied AI. And a foundation model really is a model that's trained on a diverse set of data that can be adapted to a wide range of downstream tasks. And we've seen a huge amount of progress on this, of course, especially around language and vision coming together over the last few years. And more recently, language and action and vision coming together in the space of embodied AI, with some really, really exciting results, especially around cross-embodiment, where you learn from two different types of robot and they help each other, right? It is better if you train on them jointly for each individual task than if you train each one just on its own data. And I think this is a super, super exciting result and direction. Of course, embodied AI poses some additional challenges when it comes to foundation models. Just how do you get the data? Where do you get it from? The compute involved, and the fact that you're physically embodying this, and you have to get this to deploy at low latency on an embedded chip in an unconstrained environment. But the promise is really exciting because this allows us to unlock huge scale data from internet scale videos and other forms of embodiment, which are obviously available much more cheaply than the highly specialized expert driving data that is what you train your actual policy from. And yet there's really interesting information embodied in those kind of videos. So just as a few examples. And while you might think that they're kind of tangentially, not all of these are related to driving, there's a lot of knowledge about how the world works, how humans work, how physics works, that you can embody, you can learn in these embodied AI foundation models and get benefit, hypothesis, get benefit for driving. And so we believe that multimodal foundation models are going to help unlock safe and generalizable autonomous driving, and hopefully well beyond that. So I'll wrap up there. Thank you for listening. Embodied AI is the next frontier of AI. Self-driving is going to be the best path to build it in terms of access to data and a meaningful way to deploy it. We can simulate complex dynamic scenes using techniques like Prism that really handle the complex, the diversity of those deformable agents that we see in the real world. We can start to build trust through multimodality, and these embodied AI foundation models are really an interesting and exciting direction to push the field further and faster. With that, I'll wrap up and say thank you.
Okay, so thank you, Jamie, for the great talk. I think we have time for one or two questions from the audience. Please repeat the questions. Okay, yeah, please go ahead.
Yeah, hi. I was just wondering, when you train your models, what's the ground truth? What's considered good driving?
So the question is, what's considered good driving? What is the ground truth? We use expert drivers who have been highly, highly trained in driving, and we get them to drive around and demonstrate what's going on.
Let's say, if in the simulation, did you use reinforcement learning or something along those lines, or what?
So if you were wanting to train, then you could do something like reinforcement learning. There are many different ways to approach this as well.
Yeah, we have time for one more question, maybe behind. There was a hand.
Amazing stuff.
A lot of people have blown a lot of their lives on things like real-time ray tracing, as I'm sure you know as well. I know you can imagine the pros and cons of both. You know, you could have different kinds of real-life transfer of both. But let me just shortcut all the ways I can explain that. And just Waymo today showed a fantastic example of avoiding what could have been a head-on collision from behind an collision. Is there a way you'd like to describe why something like Gaia, which is, you know, didn't have to learn a vehicle dynamics model in the traditional way, didn't have to worry about real-time ray tracing, why that would have advantages over what we might think of as the more traditional technique, which is perhaps more like what Waymo is?
So there's a long question there, so I'm not sure I can repeat it sort of verbatim, but why do I think essentially something like Gaia or a learned approach is going to be able to deal with those situations better, I guess, is that the gist of it?
Yeah, I want to let you answer whatever way you want, nerding out on it.
So I think there are many ways to answer that. And I haven't seen that specific talk, so I don't know exactly what was said there. But ultimately, there is like everything needs to be data. I think everything needs to be data driven ultimately, and the more data you can get into this thing, the more realistic you can make it. The more of these edge cases you can see. Some of those you can program, you know, in advance to sort of give you a leg up, to bootstrap you, to get you further along faster, because you don't see those very often. But ultimately, I think, as we were saying with the foundation model section, there is a ton of really valuable, sad, but really valuable data, crash cam data, dash cam data of crashes and things like that, that we should be able to leverage and embody that information into the foundation model, such that you can then, sorry, I've lost the mic, but such that you can then learn from that in a way that doesn't require sort of you to assume rules about how the world works, because for every rule that you make, there's always another rule that another special case that breaks it.
Okay. Thank you, Jamie, for this amazing talk.
Thank you. Yeah, I'll just.
Okay, so this brings us to the last talk of today's workshop. And it's my pleasure to introduce Kashyap Chita, who is a graduating doctoral scholar at the University of Tübingen. And there he also leads the Tübingen AI autonomous driving team, which has won multiple challenges in the last couple of years, as you're probably aware. And Kashyap will talk about synthesizing simulation environments with generative models. And I really hope that the microphone doesn't die now, because otherwise we have a problem. So Kashyap, the floor is yours.
You're still muted, Kashyap.
Yeah, you should be able to hear me now. Okay, yeah, thanks for the introduction. I hope the audio is okay.
Yeah, that sounds good.
Yeah, I'm really excited to be presenting some of our recent results on generative models for simulation. So let's get right into it. By now, I guess at the end of a workshop on simulation, it must be clear that simulation is important for autonomous driving. I wanted to start by talking about the open source simulators we have out there to work on driving these days. The most predominant set of these tools are graphics simulators, and these are great for research. I think like most of the work I've done in the last 4 or 5 years have been on graphic simulators like Carla, and they let you train or test driving models for arbitrarily long like routes and simulation durations. You can go up to like several minutes or hours of simulation, several kilometers. You do have access to sensor inputs in these simulators, so you can build end-to-end planning algorithms, which we've seen are currently very much in favor. And overall, they're like quite established, but there are some downsides to graphic simulators. The main one among them being that usually you end up with just handcrafted road layouts and scenarios. So there is a big domain gap, especially when it comes to planning, with regards to the type of challenges you face in a graphics simulator compared to the real world. They're also quite compute heavy, and results are not very reproducible sometimes. You may need to rerun your experiment multiple times, which further adds up this problem with heavy computation. So something that has recently become available to the community and is like gaining more and more traction is data-driven simulations, specifically what I call log replay simulators. And NuPlan was the first like large-scale one available of this type, which came about a year and a half ago. And more recently, we have Waymax as well. So like this area is now getting more attention. What these simulators do is they start off with a real-world data set and either initialize or replay a real-world scenario within a more lightweight simulator that typically only supports planning. So they look something like this. You have access to a bird's eye view world, and you can plan in a realistic scenario where the other vehicles move as they did in the real world, or at least are initialized as they were in the real world. Some of the shortcomings, though, are that because of this reliance on real scenarios, these simulators are often associated with logs, and the logs can be quite difficult to store and just search or sample from. So for NuPlan, for example, you need to download 2 terabytes of logs to get access to the official sets for working with. And even with such a large set of log data, these simulators currently only support very fixed routes and short durations. So you can just imagine that if you try to go in a different direction than where the vehicle drove in the log, you're going to end up in a place in the simulation where you have no traffic information anymore. So this kind of limits these simulators to short 15-second or so evaluations. And what I'm going to talk about today is using generative models to enhance these sort of replay-based or data-driven simulators. There's an emerging idea. We've seen like the use of generative models in very different parts of the simulation pipeline already today. There's like work on generating sensors or camera data, or doing like a completely end-to-end generative simulator. There's also a lot of people working on generating traffic behaviors with generative models within simulators. What we work on specifically, though, is synthesizing the entire scene that your simulator can initialize its state with and start a simulation with. So something that we visualize on the right looks like this. And this sort of scene is generated with a trained model, which enables us to have some degree of realism because it's trained on real data. The scenes look like real world scenes, even though they are not exactly real world scenes. That adds a lot of diversity. You can have arbitrary duration and route styles, which I'll talk a bit later on how we're achieving that. So there's these advantages. And finally, the compression of this entire set of logs into a generative model makes the simulator itself much more compact. So if you want to work with this generative simulator, you only need to download the weights of the model that generates these road layouts and agents, which makes it very compact. It's just 3 or 4 gigabytes as opposed to the 2 terabytes you need to get started with NuPlan and generate challenging scenes with NuPlan. So yeah, that's what we're trying to get to. So I will talk a bit more about how we managed to build this sort of simulator. All right, so obviously, like, generative models are quite hyped right now and everyone's working on them. So one natural question is like, how come a generative simulator doesn't already exist? Why is this not solved yet? Like, I think one of the main reasons this problem in particular was not studied as extensively as other generative modeling tasks is because the scene elements you have in a driving simulator are vector-based. These are very diverse. So you can have like objects like vehicles, pedestrians, static objects, can also have lanes, and these are represented usually in different representations. So you can have bounding boxes, polylines, these have different dimensionality, different counts per scene, and most of the generative models we have today aren't really compatible out of the box with these sort of diverse elements if this is the output space. So what we do is we kind of try to adapt the tools we have in generative modeling today to work on this specific problem, which is very relevant for driving and developing driving algorithms. So the first thing we do is like we take this set of diverse entities and map it into a simplified fixed size representation by basically rasterizing each type of entity into optical flow channels. So this looks something like what I've shown here. You can take for any type of entity all of the information that's contained in its attributes and represent it on a rasterized grid without loss of any information through some heuristics. And this is quite standard, but what is interesting and what is crucial to actually get this to then be useful for a simulator is mapping this sort of rasterized representation back to the entities or the vector elements that we need for initializing our simulator. So how we do this is we start off with this rasterized scene flow image, which is 12 channels, just like I showed on the previous slide, pass it through a ResNet, and the output of this ResNet is a feature map. It's, in our case, an 8x8 feature grid. There's a little technical detail here that we split the channels of this feature map into 2 groups. And this separation is related to bringing controllability, which has been mentioned a few times as like something important for simulators. So I'll talk a bit about that later, but we have these 2 channel-wise separated chunks of feature vectors coming out of this ResNet, which we then pass to a transformer decoder. This is very much like almost exactly the DTER object detection architecture, if you're familiar with this, which uses learned queries. So these are embeddings that are initialized randomly and learned during training to use information from the keys and values that come from these feature maps and generate discrete vectorized outputs. So we have these 6 types of learned queries corresponding to the 6 types of scene elements we have in our simulation. This can easily be extended or adapted based on the complexity you want your simulator to have. And the first 3 types generate polylines. So these are basically the lane graph and the traffic elements, whereas the next set generate bounding boxes. We also have this ego vehicle speed query, which kind of initializes the ego state, which is also an important part of a simulation environment, which is the state at which you started with the ego vehicle. And about this whole separation and controllability, what we do is we build a custom mask in our transformer decoder that allows the lane queries, so the things generating the lane graph, to only attend to the lane channels of the feature map, whereas all the dynamic queries corresponding to different types of objects can attend to all the agent-related channels of the feature map. What this does is it lets you later adapt one of these while keeping the other fixed. And this enables a lot of downstream applications. So you can like have a fixed lane graph and generate different agent configurations, or the other way around if you've separated out the latent maps, right? So in the end, like this is the most complex part of our simulation setup, which is essentially a mapping from this rasterized representation we created back into the native discrete representation used by the simulator. And once you have this sort of raster to vector autoencoder, you can use a standard diffusion transformer. This is like something that's gained a lot of interest now that it's being used to generate high quality videos, things in 4D, 3D, and so on. But this architecture works really well also for our task of generating these simulated entities. So you just denoise a initially noisy sample of latent maps into a latent that can be decoded by the frozen pre-trained VAE decoder. And that gives you a set of entities that you can then plug into any existing data-driven simulation framework like NuPlan, which can then generate the traffic behaviors or calculate the metrics and all the other nice functionalities that are already available in these data-driven simulators. So really what we're doing is we're getting rid of having explicit logs and transferring all of that information into a generative model here. Just a couple of more details on how this actually works. So we used the NuPlan dataset and we sampled around 500,000 frames from this dataset, which covers 4 diverse cities. And we need to train these 2 models to set up this simulator. The first one was the VAE. This is trained with the standard Dieter Hungarian losses and a KL divergence term for the variational part of the autoencoder. And the diffusion transformer, which is the like main component that draws a lot of the training compute, takes about 2 weeks to train. And this uses the standard diffusion denoising objective, which is the mean squared error on the noise that was added to the input. The result of this is we get a model that gets really good at replicating the logs. I'm showing here some random samples of generated maps. So I'm only showing the lane channels without any of the agents for now, for some different baselines that existed for this task. And like I said, this was not very popular, or like there weren't that many baselines for this particular tasks. The first one is just using our VAE as a generative model without applying the diffusion model on top. You can see this like barely gets the structure right, because the VAE makes like really strong assumptions, and it's very hard with this model to handle the complexity of these maps. There is a method from 2021 called HDMapGen, which uses a graph neural network, a graph recurrent attention network, to generate these maps 1 node at a time. So you kind of generate these segments autoregressively. This does get some structure. You can see that it has a lot of difficulties getting the lanes to be straight, and overall still not really usable to start a simulation with. Another idea is to directly use a diffusion model on the raster images. That's the third baseline. And while this does sort of get the drivable and non-drivable areas properly distinct from each other. There's lots of issues with connectivity because in the raster space, it's not very clear that these endpoints are important and these entities need to be connected to each other. And our approach is on the right here. So it does give you maps that do look reasonable for simulation and look very much like real maps in the NuPlan dataset. We also have some quantitative ways to evaluate this HD map generation task. So once you've generated the map, you can sort of subsample nodes at a fixed distance and then further subsample these to what are called key points, where the degree of connectivity of these particular key points is not equal to 2. So they have either just one connected neighbor or they have 3 connected neighbors. And with these key points, you can calculate these Frechet metrics. So here I have a table with the same 4 baselines we've seen in the slide from earlier. You can see that with the key points, we can calculate different kinds of metrics. These metrics are actually taken from the HD MapGen paper, which are related to statistics on these key points, like how many key points do you have in a fixed region, or how many points are connected to the key points on average. And we have these Frechet distances on these statistics over a set of real maps and the set of generative maps. And we see that we outperform everything out there by far on this map generation task. Now, the cool thing about this model is that even though it's mainly trained for just generating the entire scene, it can also do other tasks because diffusion models are so versatile and flexible. So you can do agent inpainting, which is using a encoder to get the latent vector for the road layout and generating a bunch of different traffic states and actors for this exact road layout. So you see here different traffic light states and different vehicle configurations for the same map. And the same way you can hold some of the channels fixed like we did in the previous slide. So there we had the map fixed and generated the vehicles. You can also have some spatial area fixed and generate more spatial area. We call this outpainting. Again, this doesn't need any retraining. You can use the exact same model and sort of condition on some part of the input which is visible. So these the latent vectors associated with this crop of the entire image are encoded with the VAE encoder and kept fixed, and the rest is generated by the diffusion model. And you can keep doing this to generate a long route. So this lets you iteratively extend the map and add more agents over a large spatial area. So putting this together, like we now have a way to replace the logs. We also need a way to actually do longer simulations beyond the 10-15 seconds, which I mentioned of NuPlan, to actually make full use of this generative model. So what I mean is, like in a log replay simulator, I'm showing like the exact initial state in the log. Because you have traffic only in one direction, you can't change the route, for example, to turning right. But with a generative simulator, if you know you want to turn right, you can generate agents along that direction iteratively. Yeah.
Microphone has died.
Can you hear me?
Yeah, I can, but the room cannot.
I will wait for a second.
Okay, it should be good now again.
We're good? Okay. So, yeah. I guess, long story short, we have 3 different simulation modes now in our new simulator that is based on this generative model. You can still load up logs, but you can also just generate agents while using maps from logs, or you can generate both maps and agents from logs. And the key trick we do to enable like really long simulations of like few hundreds of meters or like even up to a kilometer, the way we do that is by only simulating vehicles within a local radius of the ego vehicle. So let's say you have a kilometer long route. You don't want to simulate all the vehicles at every frame of the simulation. So you only simulate the things within 64 meters as the hyperparameter we use, which basically means that the state of all the other generative agents is kept fixed. So you generate everything at the beginning of the simulation, but you keep everything fixed until your vehicle approaches a certain radius of the other agents. So let's quickly look at how that works. It's not a long video and I hope it works okay. So on these long routes, you can see we have a vehicle moving, making way for a pedestrian, keeps going straight on the left. We also have a scenario on the right, which is one where the map is generated along with the agents. And this sort of long simulation was something that was not really possible with the new plan simulator. And it's like really important to evaluating fairness, as I'll show in a minute. So the experiment we did that kind of showed that these long simulations are important is testing the state-of-the-art planner for NuPlan. So sort of the simulator which has short simulations called PDM closed on these new longer scenarios. And there's a lot of numbers here, but like let's focus on the left block here of the lane to agent mode where the maps are taken from the logs. The failure rates of the planner account for collisions, going off-road, or making less than 20% progress. So really strong failures. And by default, you have very low failure rates at low distances. So the planner gets 94% success or 6% failure in something like the default configuration. But we see that by extending the simulation length and the route length, you can already make the state-of-the-art planner fail almost 5 times as much. This is just using replayed agents and maps. When you start using generated agents, you get similar statistics showing that the generated agents are actually following realistic distributions. But the cool thing about the generative model is you have way more controllability than the replay. So you can resample multiple instances of agents, like I showed in this in-painting slide, until you get high traffic density. And this lets you have a more challenging evaluation with denser traffic, which increases the failure rate. Or you can also generate routes that explicitly have a lot of turns when you extend the scenarios with the styling procedure. And adding more traffic or adding more turns can give you more interesting edge cases. Right. I don't have much time, so I might skip this. It's just a video that shows some of the failures that you get with the new longer routes. Yeah, let me skip over this and go here. So yeah, these are sort of my takeaway messages from this. So with generative models, you can have long traffic simulations. The vectorized scene generation task, which is important for this sort of simulator, is possible with latent diffusion models. So the key step is creating this autoencoder. And our simulator enhances control because you can do things like add turns or increase the traffic density. And this is even before explicitly making our diffusion model very conditional. You can also start conditioning on text or conditioning on images and other things. And I think like the most nice thing about this is that you can have a very accessible and easy to use simulator where you can get started by just downloading a 3 GB model, which requires 500 times less storage than you plan. So I don't have much time, but I would like to take a minute to also mention a couple of other works that are relevant, maybe, but I couldn't really talk about today. So one is like we have this huge data set of driving videos called OpenDB2K, which was released as part of a CVPR paper. It's the biggest driving video data set that's publicly available, and you can catch the authors on Thursday in a poster session. But the other is that we trained a driving world model on this data set, which basically does a lot of the things which Gaia does that Jamie talked about just now. But this model is completely open source with open code and weights. So if you're interested, you can check that out by going to this link. And yeah, just playing one of the videos generated by this model. So it's super high resolution, long duration videos, and 3D like seems to be quite consistent and so on. So yeah, that's it from me. Thanks, and I'm happy to take questions.
Thank you, Kashyap. So I think we will have time for 1 or 2 questions from the audience. So please stay online. Do we have some questions from the audience before we move to the panel discussion?
Last chance.
Awesome.
Did you hear that? Someone shouted it was awesome.
I couldn't hear that, no.
Okay, well, someone shouted it was awesome. Also, you didn't see it, but let me turn you around for a second. You were talking to a full room.
All right.
Well, now everyone is sleeping, but and also it's to note that Kashyap is in Europe, so it's past midnight for him. So I would say a loud round of applause for him for staying up for that one.
All right, yeah. Then I will stop sharing here. Thanks a lot.
Thank you.
And yeah,
Talk to you
I
soon.
will. All right, bye-bye.
All right.
Okay, okay. I hope the online people can hear us. And then, Tanya, I hand this one over to you. I hope online is somewhat understanding what we're saying. Yeah, and stage is yours.
Thank you. Can you hear me? Yes, in the back? Yeah.
Yeah, very bright.
All right, can you hear me in the back? Yeah, okay, great. Maybe we can start with testing. You know, we've seen a lot of really good simulators today, but we haven't really talked about correlation of the metrics you get out of simulation with the real world. You know, any kind of thoughts on that? Do these, you know, simulators do it justice? Do you know, kind of like what's missing maybe to really make them powerful? Guess I'll just hand this around and you guys can take it.
And just a high-level statement, right? You want the outcomes in your simulation to match ultimately the outcomes when you do real-world driving, whether it is with driver assist people or fully driverless. And I think our companies are striving, and I think iterating, a lot of us for many years, at least at Waymo, this is true, on making sure that our simulator produces predictive signal of the rates of issues we actually see in the world. But how exactly we do this, I think, is more difficult to discuss, right? I think that touches on Waymo specific technology in many cases.
I guess maybe just a point to this. Not every simulation is going to be perfect, right? But in the end, you want the metrics to be somehow reflective of reality.
Yes, I think in the evaluation, you need to take into account potentially there is some domain gap. And subject to that, or potentially imperfect outcomes in the simulator, you need to derive evaluation signal. And that one maybe has two sides. One is a hill climbing signal of some kind, of finding bugs in changes that you made. But there's another one where you actually want it to be predictive of rates of incidents that you care about in the real world. And that one is quite difficult to achieve and takes often a long time.
So this mic is probably not working too well. I don't know whether this improves it by.
You have to be close to this.
To this also, okay.
So maybe just speak up a bit, it's possible.
Yeah, a bit. You can try to do that as well.
Yeah. That one is, or yeah, I tried.
Yeah.
You have to eat it.
I can also speak loud, but it's hard to gauge.
Yeah, I want to probe in the things that there are a lot of metrics, all of them are imperfect. And from my personal point of view, you really need to look more and more into this reference-based measure, because this is mostly how we are evaluating the results. Like basically, sometimes we need to be human data, and whether we could have sort of learned rewards or learned metrics on top of it, it would be really a nice thing. So good, do this real hill climbing based on these rewards. But I think that it was. Thanks. And I think maybe that's another thing. We also have to still work on the simulators. I think adding some of the parts and components that we typically or oftentimes ignore stacks like latency and making sure that the simulator gets as close as possible to a real system on real hardware on the embedded stack is absolutely essential. So there's still a long way to go too. Nevertheless, I also don't think we get around deriving the signal from the real driving data, which is absolutely essential that real true end-to-end signal, which is that state. So you don't get around triaging and testing to a certain extent, but hopefully minimize that and do as much as possible in the cloud, having a fully digital way of training and validating this stack. But we need to validate that the simulation itself is adequate. So testing is something you do not get around, which is also in the traditional model. Well, I have to go back to the traditional model. I think the testing and validation is necessary there. So you have to, in the end, do the validation with the dropping on the to make sure that there's no systematic issues in your simulator. So,
yeah, like what you said, if I understood correctly, Alexander, you were talking about sort of, you say preference, you mean in terms of human, like the experience of the interaction with the automated vehicle. To me, that would seem sort of coming from a human practice perspective, like something which I very rarely see mentioned. So I'm curious whether anyone is actually doing that at the moment. I think it's very easy to, it's much easier to define what an incident is when we're talking about safety, right? But when we are making some sets in traffic, how do we modeling sure that I think that's an interesting question. I don't know if anyone want to say something on that.
Not on that specifically, just to the original question. I mean, I agree with a lot of great points here. I do think that actually this is one of the cruxes of the whole thing, simulation. If you solve this, how do you measure the quality of the simulator problem, you can make great progress. And every time that we've come up with some improvement in how we measure the simulator, we've massively then been able to accelerate how well the simulator works and how useful it is down the line. So, you know, I think there's still plenty of room in the community for further work in that space.
So even though they're still a little bit faulty, there's still lots of signal there that is helpful for development. Is that generally true?
I think, you know, in a sense, simulation and autonomous driving, simulation of autonomous driving and the autonomous driving problem itself are in a rough equivalence class of difficulty. If you had the perfect simulator today, you could then just run RL in that and it would give you the perfect policy. And the fact that nobody has yet got the perfect policy means that nobody has yet got the perfect simulator.
But also, when you say run RL, you presuppose you can define the reward for the driver.
That's what I mean by perfect simulator. So it has perfect rewards. The perfect simulator would.
But this one has good realism and perfect reward. So there's two requirements, and I think both are interesting and both are difficult and require work, right? We need more realism in the simulator, and we need better work in potentially defining more complex notion of rewards beyond the, even though the simpler one have driven the space a long way, like, you know, no collision, no road, more progress, and a few other things. I think as you go to more and more complex situations, potentially some of this reward design becomes prohibitive too if you have to define it explicitly, so you need to work on that.
Small addition, yeah, we have autonomous driving, we have simulation, there are two of a kind. But I would like to put one more missing key piece here. This is like of the trial. And basically here evaluation itself is of the same complexity. Like again, it comes to the rewards, and it comes to how we are close to the real humans on the road, etc. So evaluation versus simulation versus on the driving, they are the same difficulty. So that's why we don't have good simulator. That's why we don't have autonomous driving. That's why we don't have evaluation.
Speaking of good simulators, how important are the pixels? You know, versus behavioral simulation only, which is probably more understood, and how important is to have, let's call it reactive pixels, right? Not just replay. Who wants to take that?
So I'm biased, but I think the pixels are super important because you want to look at modules in your stack that are early on the stack because there's a lot to gain. I think this is something we're going to scratching the tip of the iceberg at the moment, but rethinking traditional parts of the platform, such as the ISPs, the sensors, how complex systems are overall, and so is something that's very essential. So it's even before the pixels in many ways that you, I think, can still gain a lot when you're looking at the next phase of this, hopefully when it scales and gets at lower costs and when the stacks have to reduce complexity as well.
Stuff you close. Go ahead.
We just needed to be biased in the other direction and say, well, the behaviors are very important as well. So I think a challenge. I mean, it's some awesome stuff presented here, and the pixels are looking really good. But I think it's maybe important then sometimes to go a bit deeper on the behavior. So that's the slide I would represent, like I was saying, and talk about really drilling down into what are these simulated agents behind the pixels actually doing, and what roles is it to things that humans care about in reality.
So maybe just a comment that some pixels matter, right? I would say a lot more than others. We can agree on this. Graphic light pixels really matter, like 3 pixels don't matter. Also, I think it's also fair to say that a lot of research is done partly because of limitations of public data set on road graphs, vectorized road graphs and boxes. it's also fair to say this is definitely not sufficient to model the rich complexity of the real world. So you need to move beyond it. And whether you go all the way back to the pixels or some derivatives from the pixels, I think over time the simulator has to move in that direction clearly. And we need to work on it, right? And but there is a design space there still to be understood. And last point is, I would love to see a well-established planning challenge still. They're still evolving, even in the research community with the simpler setups. We're not there yet, even. So that may be a good start.
Don't worry about it.
Yeah, I can add one little addendum to what you said. Well, of course, right, the tree pixels don't matter and the traffic light pixels do matter much more. You equally, have to prove that your system knows that too. And if you're doing that with simulation, then of course the tree pixels do matter because you need to be able to prove that.
But maybe Jamie, just a follow-up. So I think last year you guys had this more graphics-based simulator, and now you just really snurf. Like, what's kind of your thought on how realistic, realism of pixels, maybe of content, just to counter? Why are you moving more towards this neural?
So it's a great question. So yeah, we had previously been using a more procedural graphics-based simulator, and we've moved to a more, NeRF-based resimulation, reconstruction-based simulator. And there are a number of reasons for that. Actually, a lot of it coming down to how do you measure the quality of the simulator. If you're in that procedural world, there are some metrics, but they're very, very indirect to measure the quality of that simulator. And I actually believe you can do that, and I think you can probably make that work, but it's a lot more expensive, and the data-driven approach, I think, has a lot more promise.
I think there is metrics to measure the realism of a simulator, but certain things easier than others, right? So if you looking mostly at the pixels, you can check if you reproduce the same behaviors when you replace the one with the simulator. That's easier. When you go to agent behaviors and potentially exponential set of possible diversity in the agents, then it becomes harder, right? But there's techniques for all of them in some way or other by in the community to try to address and hill climb. That's not simple.
I'd like to complement a little bit here, just saying the funny thing, it depends on at what purpose the autonomous text are you working. If you're working on perception, you're treating like pixel as the most important ones. If you're working inside behavior, like behavior is the king. But based on my observation, recent amount of problems inside behavior, but contains got more cases or safety critical cases in comparison to the perception stuff. Just my subjective point of view, but
yeah, I mean, I think the several pieces would completely agree. You do have to combine them though, right? Because if your stack is imperfect on the perception side, and you have IT switches, for example, you do kind of want to consider those really carefully in the rest of the stack. So there's big caveats for separating. From an engineering point of view, it's awesome because you get the compartmentalization and the individual teams, but they're pretty dangerous if you don't do it in the right way.
Maybe just to follow up on this behavioral question, because like how much of that unexpected behavior comes from the fact that the world is not rich enough, that you just having the behavior part, traveling boxes on a map, maybe they don't have enough information that actually cause the actors to behave in certain way. So there's no way, that can be, where do these pixels start mattering?
Okay, let's say a little bit about behavior. Yeah, first of all, a lot of the things that I'm talking about uncovering some critical cases come from the more and more data. Basically, with the real data, we can uncover the unknown, realistic unknowns, not synthetic unknowns. With synthetic data generation, we can do like adversarial data generation, adversarial agents, etc. But I don't think we can trust them 100%. That's the thing. So if we can really do a lot of adversarial generation stuff, we can be robust against them. Okay, I'm not sure that this specific adversarial behavior we can something that we can see on the road. That's
And I think if I'm understanding the discussion correctly here, I think this area of the rarer, unexpected, difficult kind of behaviors, I think that's a space where this kind of mechanistic modeling, the rest of the panel here is very much more from the sort of data-driven side, whereas I'm more from the mechanistic cognitive modeling side of things. I think that's a space where we could come together more, I think, and do to try to model realistic behavior in these rare situations. We might want to leverage mechanism more than just data, because we don't have so much data in that space.
I guess my question was if some behavior on the road happened because the driver in some of the car wasn't paying attention, was talking to, that's probably not encoded in this traveling box in the map. And, it's very, hard to predict. Well, in pixels it might be, right? The camera have maybe, as a human, you might see that, right? Eyes, cameras.
Maybe. So I think that's the kind of thing that you could, in principle, and I realize it's quite far from the current kinds of methods, but I think it's an interesting direction to think about whether you want to model things like attention specifically. Would make a lot of sense to try to do include some kind of mechanistic layer in these models.
So there's this question, right? When you test for the real world, there are inevitably situations you want to test that you never observe, right? And it's not likely to even stage them. Their simulation is key. And so there's the part that, so you have to be able to do these things in some way and go from first principles to make an environment, which is one interesting property. The other one is in line with what Jamie was saying. They are related tasks, at least as viewed by a machine learning engineer in the following way. The rare things are the hardest, the most need to test potentially in the system, and they're the ones that you have least data to even build realistic simulations from, right? So this in Waymo research, and I was saying in my talk, there's Shimon writes, and he's like, there's the donut. You have the common cases and it's not interesting. So there's a hole in the donut. Then there's all the meat where the simulator really helps and you try to extend it. And beyond a certain amount, simulator can't even help you, right? And you need to do yet more. And that's one area where it's potentially arguable simulator, because you need to cover all this space one way or the other, could be harder than just driving. Because maybe your data makes you so that you cover them. It just happens that it just works, but you have to test it, and that's more work.
Can we go deeper in that? So it seems like you're saying that for data-driven simulation, rare cases are hard because you never observe them, but those really are the ones that matter. So what's kind of the frontier here? How can we make this work?
So I mean, in terms of research, right, I'll even start with our sim agents challenge. So what have we made a challenge to do? It's a distributional realism. What is distributional realism? Agents behave like what you observe, but that's the head and the torso of the distribution, the fat part still of the Gaussian. But honestly, tons of headroom even to develop this. So it's a good challenge and timely. But that's not what we actually want. We ultimately want what people call adversarial agents, so like rare risky situations, the agents may still do. And those are harder, right? And we don't actually even have in the sim agent challenge yet metrics articulated for it. But we need to move towards testing things that actually lead to interesting outcomes we care about. And I think as a community, we should think more in this way, as opposed to pure distributional realism, even though I'm saying this is one that provided a benchmark on distributional realism. In the first place, I'm aware it will run out of headroom, even though we can even improve this benchmark 1 or 2 more times, it will run out of headroom, but it's a prerequisite. If we don't conquer even the head and torso, which there's still headroom, the other part is yet hard, right? But we can think about it.
So another way to answer this question is around you know, it may be really hard to actually drive your autonomous vehicles and experience the world in all its richness at scale until they're so ubiquitous that everyone is every single car is doing this. But in the meantime, there is a ton of data out there on the web, dash cam footage that is very, very varied and does include a huge number of sort of edge cases and long tail scenarios. So if there is a way to take that information and condense it into something that can then be used for various forms of simulation, that starts to be very interesting.
Any thoughts, guys?
Makes sense.
Probably, in addition to general percent, especially when talking about this very rare like collision or near collision cases that we can find in different places on the internet. It's not only about how can we test such a case, but also it would be nice, for example, to make our system sort of future could be trainable in future manner. So, for example, we can infer a specific thing. And I think right now this LLM-based decoder can provide us capabilities, but I'm not sure whether anybody has tried to tackle this specific problem of near collision cases, how we can fine-tune this. It would be really nice to see.
Yeah, so I think we're still probably not there. If you look at most representations that we have today in our simulators, they're all bird's eye view based, right? Or most of them are. Then if you go at, for example, rand behavior, right? Then maybe you don't have that in there. And even for a data fusion model, which I've never seen that data, you'll probably not be able to simulate it. So it's kind of baked into, and this perhaps also an overlap to what you were touching on before. We probably perhaps need to rethink some of these biases or impacted biases that we have in our models and so on.
Maybe I can sort of follow up a little bit. I'm again sort of a little bit different in the approach from the rest of you guys. So I'm very also curious what you think. So you mentioned, for example, like a distraction as one kind of thing that would make a difference, of course, safety critical situation. But of course, there's lots of other things which are even less visible in pixels, like drowsiness or some kind of wrong driving or whatever. But I wonder what your guys' intuition is. To what extent does that need to be represented implicitly or explicitly in some way in simulators? Those kinds of things.
Something. Generally, when you test, right, there's a discussion of persona or model of human reactions, and that typically can be modified to cover some of these considerations and fit to at least some data that you have. So, of course, it may be a simpler model and fit to less data because it's rare, but there are things that can be done to ultimately test in any situation. There is no one outcome. Bad thing happens or did not happen with probability 1 or 0. It's always probabilistic outcome depending on the state of the human on the other side. And that can be modeled and estimated as such. Then maybe also need to go beyond just a collision to what's the severity of this collision, they matter, and the difference between matter, right? All of this requires a certain amount of rigor to think about.
I think it's an interesting thing to, or an interesting case to think about. I think for the drunk driver, you can probably learn this somewhat okay just from boxes, but you, as a human driver, definitely make the deduction differently. Right? You probably also look at the vehicle, you look what's inside the vehicle, you look how the vehicle, in what shape the vehicle is. Right? There's additional cues that the models could also learn in the future and not included in the models at the moment.
Might be very hard to simulate, right, in pixels. For these rare cases, I guess, Jamie, you mentioned internet has a lot of knowledge, right? What do you guys think about LLMs for kind of authoring versus human authoring these rare cases? Is there some opportunity there, or is it still hard?
There's definitely opportunity. I think it's probably relatively early days of like proving that out. But you know, in terms of authoring, you know, tests and calling out specific things, sure, yeah, you could, you know, get people to describe things and then, convert that into simulation cases. But ensuring that the sort of diversity and realism of those is sufficiently high, that's still an unsolved problem yet.
Has anyone tried it? Just what would be the challenges? No.
And you can try state-of-the-art video engines at least on the public side and see what they do. And sometimes pretty funny things happen. They flip cars on the spot and car drives. I mean, let's just say off-the-shelf models don't necessarily do a great job generating these cases with prompts yet. That doesn't mean that if exposed to actually our domain a lot more, the headroom is very big. So I think this is still being experimented with in the community.
I'm pretty confident we'll get some of that interesting in the next very little while as a community.
Something good to work on, I guess. Okay. Do you guys think that AV simulation is actually harder than autonomous driving itself? It seems like you need to model the world to drive well. Kind of like a chicken and egg, right? But in order to drive well, you maybe need to simulate. So, like, what's your thought on simulation versus driving, or building simulators versus building driving policies?
I somehow feel simulator is a little harder. It's more diverse set of agents you need to do. You need to worry about a lot more cases. You can't shirk the responsibility of actually trying things by assuming it may just work, right? And you need to be more mechanistic beyond a certain amount. And maybe you need to embody more agents than one fully, which depends from what perspective. But the moment you have a lot of close divergence, embodying those agents becomes challenging, right? So there is a lot of these. I would say the community spent maybe less attention on building powerful simulation and base physics too, which is yet another. And there is latency. And so it would maybe there is room to focus more yet on that compared to necessarily just deriving a policy from some video, and which is potentially more straightforward in some ways until we get to the simulation.
Yeah, we definitely agree here, especially on talking about controllability. Yeah, we have seen a lot of work on controllability, but what we really need sort of a very thorough sort of controllability, aggressiveness, conservatism, etc. How to put it like in some formal way. It's unclear that right now there are some works in terms of thinking, let's do it this way, but the realism of it is far from being verified. So that's the part of realistic controllability is still in the equation.
Yeah, would also completely agree. And you have to imagine many different futures, right? And as there is possible outside of that domain that you described before. So I think that makes it by design more challenging, more difficult. But that is also the chance, right? If you can correct this nut and build a really diverse simulator that has all of these outset scenarios that we don't have in our data sets and in our testing sets, then this makes the driver also so much more superhuman than with whatever experience you could get to.
Yes, we might have touched upon it a little bit already, but I've also, in addition to building the simulator, I guess it's also the question of determining whether the simulator is good enough for whatever purpose. It's just related to the question on determining of the AV is good enough, but yeah, I don't know if others have thoughts on that. It seems like that's not really been discussed so much yet.
So something is said resonated with the point that was in the document, which is that it's not obvious there's one simulator to serve the whole community. Right? I think the simulator and its design and approach is tightly tied to actually how your system is designed and approaches things, and including what even the rewards in your system in some cases are, and so on. And so it feels that, and that makes it more difficult because now each of us may have a certain simulator that fits best our needs, and the lowest common denominator is sensor simulation with agents in it, right? And people can build those worlds to some level, but even for those, you need to know what artifacts are needed to be produced and how to aggregate them. And it becomes a difficult system design problem beyond a certain level, even though there are certain common things we all can build and share in space.
So if building simulators is harder than building autonomy, how do we even go about this, right? It seems like, how do we make it useful as part of our development process? And, you guys have scale. Is simulation still important? What, importance of simulation during development, importance of how good it is as you develop? Maybe some comments on that.
Yeah, I mean, it sort of continues on what you said, Drago, on sort of thinking about the actual application of a simulator. I think, it's easy, in one sense, it's easy to say that making the simulation is really, really difficult, because I guess when you ask that question, it's easy to think that we have to reproduce everything and so on, right? But maybe if there's some, I'm really amazed by all the talk I've heard today. But if there's something I'm maybe missing from the entire workshop here, is that focus on how we actually put the simulators to use for something. Because if we think about that, what are the actual metrics we're going to pull out of them, and how we're going to say whether those metrics are good enough, then I think that helps us kind of derive what we need from any given simulator for a specific application.
Yeah, for sure, the simulation is imperfect. It's far from being perfect. But my personal point of view that we should evolve our autonomous vehicle drone at the same pace, at the same cadence as our simulation evolves. So we don't, for sure we could wait until we have the perfect simulation, and then we can build our model, train and say simulation. That's not the case. So, and vice versa. So we don't need to wait until we have a perfect vehicle, and then let's, I don't know, adopt those models. We need to do them continuously, evaluate both of them. And that's why I guess every company has its own simulation, it's their own behavior agents, etc. So we are just constantly evolving them to be on par. And that's
there's a co-development aspect to it.
Yes, because doing better ego at the same time doing better simulation.
And I guess it's not the one will be all of all you out just to have a simulator that's good, right? And I think even if you look at the safety methodology we published, many things can go wrong, including in hardware, including in fallbacks. And you can do, ultimately, you can test it in many ways, including in custom, we have Castle where we can stage things. Obviously, it's key to always ground everything in real world examples. In some cases, you can use human judgment for certain scenarios. You need to put it all together, right? Because no one tool is perfect. And I don't think there's one tool that just solves all your safety case. It's a huge palette of different approaches covering all the potential failure cases. They need to put it together in some kind of offering. That said, simulator is fascinating because there's a lot of headroom to do more and more here. And so both on the behavior and the sim side, and even how to use all of this, right? So all of these are great topics.
I agree with that. I think there's an opportunity there to try and consolidate that, right? Because maintaining many different tools that all do slightly different things, and especially when there's manual effort involved, I think there's a big opportunity to, over time, gradually consolidate those as much as possible.
Maybe Drago for you, because you probably have the most data out of the panelists, right? You guys should. What's the role of simulation once you have just a ton of data,
No, but so here's the thing, right? Our system is tested in closed loop in the real world. And so to approximate its behavior, so you evolve the system, right? So you have new releases. The new releases will have new outcomes in closed loop. And so you don't want to necessarily test all that in the real world without the driver, right? So simulation still plays a key role to ensure that in closed loop, you can test all the things. And another really key role simulation plays, if used correctly, is it should be able to find a lot of bugs in the new system that may have seeped in, whether as a result of training on different data or as a result of humans introducing something. Simulation is a key tool to finding it, because maybe when the data is in the real world, it may be more open loop metrics. They're good at checking if you do something in the thing you explicitly saw. but they're not as good necessarily in discovering new things that you could see, because you never drive enough on the new policy potentially without being in the simulator at least a bit. So I always feel there is a place for a simulator in the release cycle.
Okay. Like, suppose that Nuro has a lot of data. This is probably not the case, but suppose. Yeah, and I would say, especially when thinking about like using simulating the training loop, it comes to whether we are going to build L2 based system or L4. If you have really concentrated about around safety, then I guess closed loop like reasoning is very important while you're doing this simulation. When you're talking about imitation, this cause of total driver, probably it's, and if you have a lot of data, like more than any employer on the road, probably it's, you know, you can do you can really do a lot of it just super low time.
Yes, so I completely agree. A key part of the release cycle, but even if that wasn't a problem and I had infinite resources, I would still argue that I would want a simulator, because ultimately a differentiable simulator could maybe enable me to solve inverse rendering and then have explained vision and have solved a lot of key problems. So I still would want a simulator, even if I had all of these resources and all the data available.
Maybe last question, just to give something to the audience, like what kind of research problem should the researchers be tackling? That's super important to make this usable, scalable, deployable. Any advice for the audience? Go for it.
Yeah, second, very top of my mind, like for realistic, like rewards for realism. For example, interactivity realism, like anything for, because it's very, very like on the beginning stage of research here. It's realism of everything. So.
How do you measure realism?
Yeah. And this is the question.
That's let's just do a round, yeah. I hear thoughts of everyone.
No, I think very similar to that sort of behavioral realism, and how to, like I was saying in my talk, how the evaluation of the models tends to stay at this quite relatively high level, whereas there's lots of scope to drill down and look at what the behaviors actually look like, and try again connecting it to the application. Are we getting those behaviors right that really matter for the humans, ultimately that matter for the safety, that matter for the kind of experience of the interaction and so on?
Yeah, would also completely agree. I think in the loop, research is absolutely key in many ways to validate the simulation itself, validate and find rewards, but also going a little bit deeper, like maybe the bigger questions that I mentioned before. Can we solve inverse rendering with simulators? And we think some of these problems further than just validation, training data generation, and closure of pulling down.
I think for me, it'd be coming back to the point I was making earlier about, okay, well, we've got all this dashcam data out there. How do we turn that into meaningful, realistic simulations that we can then use to deal with a lot of these really hard cases that are very, very rare just in the real world.
So for you, it's like taking freeform videos and reconstructing environments. They're real to sim with freeform videos and then being able to pull signal out of them.
Exactly.
Right. And there's a good amount of work in the past trying to do this. That said, freeform videos come in all kinds of shapes and, noises. I mean, to me, there's headroom in most of these key areas. So there is sensor simulation. There is recent technology have made it dramatically more practical and realistic. And I think there's a lot of headroom here, but I always think a lot more on real to sim. So be able to take any scene we draw and turn it into a simulation environment. I think that is really powerful and scalable, right? And then extra bonus if we can do it from the scene someone else drew, right? That's even better. Then another one is, yes, behavior realism is key, but I think there we need to align better on whether the metrics of relevant behavior that is useful for testing. And that one needs more work and thought beyond just the realism of the agents. And once you get to the realism side, I think what is still missing to a reasonable extent is richer inputs for the agents in the world. So we actually did ship for our data LiDAR and camera for the open data set. So when you predict the agents, you have the history of 1 second at least of sensor data, and we could make even more in the future available if that's helpful, even though it will blow up the data set even further, which always was a big concern when we did any of these things. But people are not using this yet much at all. I think even going from just the boxes and the road graph to also LiDAR and some image embeddings, that's a pretty big lift for a lot of people, right? And maybe more people can try this, so maybe we can come up with yet more appealing things. Maybe we should just do a bunch of videos if that's what people prefer. There's headroom here, but I think we should move towards, when we move model agents, move beyond the boxes as a community, and also what are the agents supposed to do as opposed to what is just purely distributional agent that mostly doesn't collide and doesn't do interesting things. These are some of the top of my.
Great. Yeah. Thank you very much to all the panelists. This was a great discussion. Next.
Thank you.
Thank you for the questions. Yeah. There was so much back and forth with this guy.
Thank you. When you everyone say I think you say everyone because people maybe principles can particularly you know, and democracy things to please get a simple and check on all we were just yeah, okay. Business simulator well, it's exciting. So and then we have to match my very different. Just go Yes.